Every day, 120,000 commercial flights take off worldwide. A Boeing 777 weighs 280 tons at landing. An Airbus A380, 575 tons. The moment those wheels hit the runway, all that metal, fuel, and passengers slam into the tires at 185 miles per hour. In a fraction of a second, the tire heats up to nearly 400 degrees Fahrenheit. The load on each one is like stacking dozens of cars on a single piece of rubber. And it doesn't burst. Every flight, every day, 120,000 times. But here's the crazy part. An aircraft tire isn't built to survive just one landing. It has to last at least 200 full cycles before replacement. 200 times at 185 miles per hour. 200 times, hundreds of tons pressing down. And it can't fail. Not once.
That's not a suggestion. It's an international standard. And without meeting it, a tire doesn't get certified. How is that even possible? What's inside this black shell passengers never see, always tucked behind metal doors? Today, we're going inside an aircraft tire factory. What's in there will completely change how you see landing. Let's start with this. An aircraft tire isn't just a bigger car tire. It's fundamentally different. Take the main landing gear tire on a Boeing 737, the world's most common airliner. Diameter, roughly 50 inches. Weight, anywhere from 220 to 265 pounds. Internal pressure, 200 pounds per square inch. Your car runs at 36 pounds per square inch. An aircraft tire inflates almost 6 times harder. That's why when one fails, rare but real, the explosion is violent enough to damage the airframe. In 2000, exploded tire debris punctured Concorde's wing and triggered the catastrophic Paris disaster. That's the cost of failure. The smoke on landing, that white puff you see in videos, isn't burning rubber. It's a tire accelerating from 0 to 185 miles per hour instantly. Before touchdown, it's stationary. At contact, instant violent spin-up. Friction, heat, smoke. The tire survives. Now, here's where it gets interesting. The tire must be both super strong and super light. Every extra pound means extra fuel every single flight, multiplied by thousands of flights yearly over the aircraft's lifetime. This balance, strength versus weight, defines absolutely everything in manufacturing. Engineers obsess over grams. Weight is money. Weight is physics. Get it wrong and airlines lose millions. The raw materials for aircraft tires aren't the same as truck tires. The main ingredient is natural rubber, not synthetic, natural. That's because it has a unique molecular structure that lets the material deform and bounce back thousands of times without fatigue failure. Synthetics can't handle that stress. Here's the thing. All natural rubber for aviation tires comes from plantations in Malaysia, Indonesia, and Thailand, from rubber trees. A farmer makes an incision in the bark. White sap flows out. Latex. After coagulation, pressing, and drying, you get dense blocks of raw rubber. Those blocks get shipped to Michelin, Goodyear, and Bridgestone factories, the trio making nearly every aircraft tire worldwide. But rubber is just the start. The second key component is nylon cord, special threads thinner than human hair that create the reinforcing skeleton inside the tire. A regular car tire has 4 cord layers, an aircraft tire, 30 to 40. And this is where something transforms plain rubber into an aviation tire. But before we get to manufacturing, here's something most people don't know. Aircraft tires aren't filled with air. They're filled with pure nitrogen. At 40,000 feet, the temperature outside hits minus 76 degrees Fahrenheit. Regular air contains moisture. At that temperature, moisture freezes, pressure jumps unpredictably, and the tire can behave on landing in ways engineers never intended. Nitrogen is dry and thermally stable. That's why it's in every aircraft tire in the world, from a small regional ATR to the massive C5 Galaxy.
But nitrogen is the final step. First, you have to build what holds it. Aircraft tire production starts with cord. Nylon threads are woven into fabric, then impregnated with rubber compound.
The result is a sheet material, strong, flexible, capable of holding enormous pressure. From these sheets, layer by layer, the tire carcass is assembled by hand, not by robots, because every layer has to be stretched with precise tension, aligned, pressed down, every air bubble removed. One bubble, the size of a coin, and the tire is scrap. The operator works on a spinning drum, like a potter with clay. Only instead of clay, he's handling sheets of rubber cord, layer by layer, 30, 40 layers, each one at a precise angle to the last. This crosshatch pattern creates the strength to hold 280 tons. Building a single tire carcass takes several hours. It's handwork demanding experience. No automated line replicates this precision yet. A skilled builder spends years learning to feel the material. Next, mounting the bead ring. This rigid steel ring locks the tire onto the wheel rim, keeping it from blowing off under 200 pounds per square inch of pressure. It gets wrapped in rubber and fused into the carcass on both sides. Then the blank goes into the press mold. Vulcanization begins. Under pressure and 340 degrees Fahrenheit, rubber's molecular chains cross-link, forming a three-dimensional lattice structure. That gives the rubber its elasticity and shape memory. The tire stays 10 to 20 hours under these conditions. That's not a typo, up to 20 hours per unit. While it's in the oven, nothing can be undone. If there's a mistake, they'll only find out at inspection. Every aviation tire goes through multiple inspection levels before shipping. First, visual. A specialist with a magnifying glass examines every inch of the surface, looking for cracks, bumps, foreign contaminants. But the real inspection is invisible. X-ray imaging. Every tire gets scanned, like airport luggage, only far more powerful. The image reveals everything: how cord layers sit, where steel rings are positioned, and whether there are any air pockets inside. Even one bubble larger than allowable size, the tire gets scrapped. No exceptions. Next, ultrasonic scanning. Sensors sweep the entire surface, detecting material delamination the X-ray might miss. Every millimeter, automatically. Results get recorded in that tire's passport. Finally, dynamic testing. The tire gets inflated to working pressure and spun on a test rig, simulating landing loads. Only after passing all three levels does a tire receive its certificate and serial number. Every tire is fully traceable: manufacturer, date, raw material batch, assembler's name. If something goes wrong, they'll find the source within hours. Ever wonder why tire-related aviation incidents are single-digit cases per billion landings? That's why. Because the cost of failure isn't a warranty claim or lawsuit. It's catastrophe. Every year, the world produces about 1.5 million aircraft tires. Michelin controls roughly 60% of that market. A single tire costs $1,500 to $5,000, depending on aircraft type. Airlines replace tires every 200 landings, or sooner if wear becomes critical. But they don't throw them away. They retread them, cut new grooves, re-vulcanize the rubber, run full quality control again. One tire can go through 3 or 4 retreading cycles before it's finally recycled. That tire under your plane may have already survived several hundred landings and still passed every inspection. Next time your plane touches down and you feel that thump and rubber squeal, you'll know exactly what just happened. Hundreds of tons of metal and people entrusted to 4 pieces of rubber. Rubber that dozens of engineers designed, operators assembled by hand, X-rayed, tested with ultrasound, and ran on test rigs. Rubber that in decades has almost never failed. 120,000 times a day.
every day. Subscribe to the channel. This is where we go behind doors that are usually closed. 300 tons of steel, 1 locomotive, 3 days, nothing. A machine that hauled 10,000 tons becomes scrap in 72 hours. Wheels that rolled 2 million miles sheared off in one motion. A 20-ton engine ripped from the frame by crane. The diesel tank holding over 1,300 gallons sliced in half in 10 seconds. This isn't an accident. This is scheduled decommissioning. The most precise, cold-blooded, calculated process in global industry. Today we're showing you how locomotives die. Why behind every death lies exact mathematical calculation. And where the metal goes when a train reaches the end of the line. On the edge of an industrial city sits a massive concrete lot the size of an airport. Rows of dead machines stretch beyond the horizon. Diesel locomotives, electric engines, freight cars, tankers, refrigerated units, several hundred strong. Each one's a former workhorse, run into the ground. A TE-10 series locomotive weighs 276 tons. Over 40 years, it traveled more than 4 million kilometers, 100 laps around Earth. A hopper car, 78 tons empty plus 100 tons of cargo every trip. Now they're tapped out. Metals fatigued from constant vibration and temperature swings. Corrosion ate through load-bearing beams. Wheel set bearings hit their limit. Repair cost more than replacement. Economics beat engineering. So the machine gets put in line for total disassembly, down to the last bolt, the last rivet, the last square inch of steel. Stage 1 of recycling is prep, the most dangerous part. A single locomotive's fuel tank holds up to 7 tons of diesel. The lubrication system, half a ton of industrial oil. The cooling circuit, thousands of gallons of antifreeze. Electric locomotives transformers, special dielectric oil that releases toxic fumes when burned. All fluids get pumped out with industrial equipment. Work runs 8 hours straight. Fluids go into separate tanker cars for processing. Diesel gets filtered and sold as industrial fuel. Used oil regenerated to commercial grade. Antifreeze cleaned and back into service. Not a drop wasted. One stray spark, the entire yard goes sky high. Open flames banned, spark-producing tools banned, even regular cell phones banned. Only when the locomotive is bone dry does real teardown begin. First, they strip out whatever can be sold whole. No cutting, no torches, no press. Battery packs, tons of pure lead. Traction motors, pounds of pure copper in the windings, sold as complete units. Power transformers from electric locomotives, copper coils weighing up to 2 tons apiece. Cable harnesses, miles of copper wire, spooled into coils. Instruments, sensors, control computers, all sold as parts to keep working locomotives running. Next, the wheel sets. Alloy steel, hardened to near diamond toughness. One set weighs 2 tons and sells as premium scrap for casting new wheels. Then they pull the cooling radiators, aluminum blocks the size of a small truck, each weighing about a ton. They remove the air compressors and unbolt the high-pressure fuel pumps. Incredibly precise devices machined to within 1/100th of a millimeter. After that, they yank the engine from the frame. The D49 diesel, 20 tons of metal, 4,000 horsepower. An overhead crane lifts it through a roof opening. It's headed either for full overhaul or straight under the press. Now the locomotive's down to a bare steel skeleton. That's when the real monsters come in. Hydraulic shears, the scrapper's main tool. Crushing force up to 1,500 tons. They cut through an 8-inch steel beam like paper. One movement, no sparks, no flame, almost no noise. Where shears won't fit, tight spots, complex welds, they bring in the torch. The oxyacetylene flame heats metal to 3,000 degrees. Steel melts instantly. The cutter, in fireproof suit and dark mask, guides the jet along the seam with surgical precision. Sparks fly 30 feet in every direction. A 100-ton body breaks down in 2 working days. Cab, separate. Frame, separate. Shell, separate. Fuel tank, separate. Engine covers, separate. Every piece gets its own number and goes to its own pile.
Metal gets sorted by type, the most critical step. Sorting accuracy directly determines the final price. Ferrous scrap, standard carbon steel. Non-ferrous, copper, aluminum, brass, bronze. Stainless steel, separate pile. Engine block cast iron, separate pile. Alloyed steel from wheel sets, separate pile, worth almost 10 times more than regular steel scrap. Sorted metal gets pressed. A 2,000-ton hydraulic press crushes bent steel sheets into a dense cube about the size of a household fridge. One bale weighs up to 5 tons. Density nearly matches solid steel. Bales get loaded into rail cars, the very same freight cars that will one day end up here themselves, then shipped to the steel mill. There, at 1,600 degrees, steel melts in an electric arc furnace and gets cast into fresh billets. One retired diesel locomotive yields roughly 200 tons of pure metal, enough to build the shell of a brand new locomotive. The circle closes. A machine that hauled freight for half a century becomes the rail another machine will roll on. A wheel that traveled 1,000,000 kilometers becomes the wheel for the next million. A beam that bore thousands of tons becomes the beam of a new bridge. That's the secret of industrial recycling. Nothing vanishes. Steel outlives any locomotive, any factory, any engineer who forged it. It simply changes shape and starts a new life. Every year, tens of thousands of rail cars and thousands of locomotives reach the scrapyard. Each transforms into new rails, new bridges, new trains, carrying the next generation of cargo across continents. The endless cycle of steel in industrial civilization. Subscribe. We show you how real industrial scale actually works.
Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything from selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are microcracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer, and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1/1000th of a gram. Excess or shortage means danger for the shooter and weapon. 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. But installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics. Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast's force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture.
From stone to wool. Sounds like science fiction, right? But here's the reality. The world cranks out over 8 billion square meters of mineral wool every single year. That's enough to insulate and soundproof millions of buildings. Ever wonder how chunks of rock, basically useless on their own, transform into one of the most effective insulation materials out there? Today, we're going inside the world's largest mineral wool factory to unlock the secrets behind this cutting-edge manufacturing process. About 1,000 years ago on the Hawaiian Islands, in the heart of the Pacific Ocean, something amazing happened. Streams of molten lava, stretched by the wind, formed thin fibers that wove together into a natural insulating blanket. According to legend, these were the hairs of the goddess Pele, torn from her head each time a volcano erupted. In the early 20th century, a group of scientists also discovered the extraordinary insulating properties of this volcanic material. And from this knowledge, rock wool was born. But to insulate millions of homes, Hawaii's lava alone wasn't enough. Humanity had to recreate the forces of nature through industrial processes. In the United States, states with large basalt deposits like North Carolina, Missouri, and Utah became the primary sources of raw material for large-scale rock wool production. To produce stone wool, the first thing you need is raw material, rock. The most common types are basalt and dolomite, hard minerals that can withstand high temperatures. At the Cardinal Aggregates open pit quarry in Ohio, USA, over 700,000 tons of stone are extracted annually. The first step is removing overburden with giant excavators. For every 10 feet of removed earth, about 1,600 tons of basaltic rock are uncovered. Next comes drilling and blasting. Powerful drill rigs cut through stone at nearly 5 feet per minute, creating a grid of boreholes. Then, 15 to 30 holes are carefully loaded with explosives. Under the supervision of blast engineers, each explosion releases 15 to 25,000 tons of raw stone. After crushing, the stone is delivered to the crushing plant, where massive blocks are ground down to pieces smaller than 10 inches. Each bucket is weighed electronically before being dumped into waiting trucks. On peak days, over 400 trucks leave the quarry, delivering 16 to 18,000 tons of stone daily to production facilities. From these very blocks, in the next stage of melting and spinning, the stone is transformed into millions of thin mineral fibers, the foundation of modern stone wool insulation for buildings.
Heavy trucks loaded with basalt from the quarry roll into the plant's receiving zone, marking the beginning of a massive industrial journey. Uniform-sized stones head straight to the production line, while rough chunks and impurities continue along conveyors toward the crushers. On to the dosing conveyor, alongside the basalt stones, glossy black coke particles are evenly distributed. Adding coke doesn't just provide intense heat for the furnace, it also regulates the chemical composition, helping the basalt melt faster and more uniformly. Next comes the melting stage. The basalt and coke mixture gets fed into a massive furnace where temperatures climb above 2,700 degrees Fahrenheit. Under this intense heat, everything dissolves into a glowing red stream of lava rich in silica, aluminum oxide, calcium oxide, and magnesium oxide, transforming into a thick liquid almost identical to volcanic magma. When the molten stream pours out, sparks fly in every direction, and workers in ceramic fiber suits and metal masks step forward to check working conditions. These furnaces run non-stop, 24/7, because shutting them down not only burns through massive amounts of energy to restart, but also shortens the lifespan of the refractory lining. From the furnace, a stream of glowing lava flows onto high-speed spinning wheels. When the molten material hits the rotating surface, it flies outward and stretches into fibers thinner than a human hair. At the same time, a stream of hot air follows the rotation, carrying the fibers outward and rapidly cooling them in the air, locking in their thin yet strong form. The result is a rain of mineral fibers that settles into a light, fluffy mat with remarkable heat resistance and sound-absorbing capabilities. Rock wool fibers are collected immediately after formation, carried by a stream of hot air, and laid down evenly on large rotating drums or wide conveyors. Layer by layer, the thin strands form a continuous blanket of mineral wool. Powerful fans and suction channels are precisely calibrated to distribute the fibers uniformly. At this stage, the material is still soft and fluffy, like a flowing sea of white fibers. The rock wool takes the shape of a block, but the initial fiber streams are only a few inches thick, so they need to be layered continuously. The rock wool stream moves forward to the layering stage, where fiber mats are stacked one on top of another to increase thickness. This process typically increases the depth of the sheet from a few inches to 8 to 12 inches, depending on its end use. After layering to the desired thickness, the mineral wool mat feeds into a massive system of roller presses. Here, even pressure is applied across the entire surface, compressing the loose fibers into a sheet with precise dimensions.
At the same time, mechanical arms along the sides of the conveyor repeatedly press the edges, holding them tight and preventing the material from spreading outward. The result is a densely compressed block of mineral wool with a uniform thickness of 8 to 12 inches.
Once the mineral wool block is tightly compressed and stabilized, it passes through a high-speed cutting system. Blades trim away the excess edges, creating straight, even sides that match the desired shape. Then, additional cutters slice the thick blanket into individual panels or blocks, each with identical dimensions. By the end of this stage, the mineral wool transforms from a loose mat into neatly formed insulation boards. Each block is cut into standard panels, typically measuring about 2 feet by 4 feet, with thickness ranging from a couple of inches for residential applications to nearly 12 inches for heavy industrial insulation.
The stone wool boards are ready now, but they've got to pass one crucial stage: quality control. Part of this process involves checking their hardness, where pressure tests are applied to make sure the boards can withstand mechanical loads without losing their shape or density. And since mineral wool is both fireproof and insulating, a fire resistance test is mandatory. Here, they use a flamethrower that scorches the surface to temperatures of around 2,200 degrees, while a person can sit right behind it, reading a newspaper, feeling nothing. After inspection is complete, the stone wool insulation boards are carefully wrapped in heavy-duty plastic film, then loaded onto trucks and shipped out to construction sites.
Every year, the world extracts over 8 million tons of gray, unremarkable ore. But only a tiny fraction of it undergoes an incredibly complex, almost alchemical journey to become a metal capable of withstanding even spaceflight. Titanium isn't just a metal, it's a substance born in hell from fire, chlorine, and magnesium at temperatures exceeding 1,000 degrees Celsius. Its first form looks like light ash, but from it they create the invisible skeleton of aircraft, eternal implants, and rocket engines. How does a chunk of dirty rock transform into a material stronger than steel, yet lighter than aluminium? Watch to the end, and you'll see how an ordinary stone passes through chemical purgatory to become the heart of modern civilization. The history of titanium is the story of a ghost metal that remained hidden in plain sight for decades. In 1791, British clergyman and amateur geologist William Gregor, while studying black sand on the Cornish coast, discovered traces of an unknown element within it. But only 4 years later, in 1795, the great German chemist Martin Klaproth independently discovered the same element and named it titanium, after the mighty Titans from ancient Greek mythology. However, despite its thunderous name, the metal remained elusive. For nearly a century and a half, it slumbered in chemistry textbooks, resisting attempts to isolate it in pure form. Only in the 20th century, thanks to breakthroughs by American chemist Matthew Hunter and Dutch scientists, did humanity finally manage to touch pure titanium. From the mid-20th century, with the onset of the Cold War and the space race, titanium transformed from a laboratory curiosity into a strategic material. The United States, recognizing its colossal potential, invested enormous sums into its production. Titanium became the foundation for the legendary spy plane SR-71 Blackbird, capable of flying at the edge of space, and found its place in the construction of Apollo spacecraft. Titanium production begins with mining its ores, ilmenite and rutile. These minerals are found in the sands of Australia, Canada, and South Africa. After extraction, the ore undergoes multi-stage enrichment. It's washed, screened, separated from waste rock using magnets and gravity, yielding a dark, heavy concentrate. But this still isn't metal. This is merely titanium oxide, where it's firmly bound to oxygen. To break these molecular shackles, the concentrate is sent to chemical hell, into fluidized bed reactors. Here, at temperatures of 1,000 degrees Celsius, gaseous chlorine is blown into a boiling layer of ore and coal. A fierce chemical reaction begins. Chlorine tears titanium away from oxygen, forming a volatile compound, titanium tetrachloride. This caustic, toxic substance is then repeatedly distilled, purifying it from impurities to near-perfect purity. The next stage is the heart of the entire process, named after its creator, William Kroll. Into a sealed steel sarcophagus filled with inert argon gas, molten magnesium is placed. Then purified titanium tetrachloride is slowly fed in. A chemical duel begins. Magnesium, being a more reactive metal, literally rips chlorine atoms away from titanium. As a result of this battle, pure titanium settles at the reactor's bottom, but in the strangest and most unremarkable form imaginable. This is sponge titanium, a porous, lightweight, gray mass that looks like frozen foam or pumice. It's brittle and utterly unlike strong metal. But inside this ugly porous sponge lies all the future might. This sponge is extracted, crushed, and then pressed under enormous pressure into dense briquettes. And only then is it sent to its final transformation, into the melting furnace. To transform sponge briquettes into a monolithic ingot, they're melted in vacuum arc furnaces. This is necessary because at high temperatures, titanium absorbs oxygen and nitrogen from the air with incredible greed, instantly making it brittle. Inside a sealed chamber, a powerful electric arc, like lightning, melts the briquettes, and liquid titanium flows into a copper, water-cooled mold. To achieve perfect uniformity, this process is repeated twice, sometimes even thrice. The result is a gleaming, silvery ingot of pure titanium, ready for further processing. Just look at this incredible transformation, from porous, lightweight sponge to dense, shining metal. But pure titanium is merely the beginning. To create materials for aviation and space, it's transformed into alloys. To molten titanium, like spices in a chef's dish, other metals are added. Aluminium for lightness, vanadium for strength, molybdenum for heat resistance. Thus is born, for example, the most famous titanium alloy, T6Al4V, which became the workhorse of the aerospace industry. These alloys are remelted several times to achieve perfect uniformity. The next stage is mechanical processing. Giant ingots are heated red hot to make them malleable and sent under presses or rolling mills. With incredible force, machines bend the metal to their will, transforming it into sheets, rods, beams, and wire. From these semi-finished products, the most complex parts are then cut, turned, and milled. But that's not all. In recent years, additive technologies, or three-dimensional printing, have entered the game. Special printers sinter the finest titanium powder layer by layer with lasers, growing parts of such complex geometry that traditional methods cannot achieve. This allows creation of lighter and stronger components for aircraft and rockets, saving up to 40% of weight. Every finished part undergoes the strictest control. It's X-rayed, scanned with ultrasound, checking for the slightest internal defects. In aviation, titanium has become indispensable. From it, they make up to 15% of a modern passenger airliner's weight, landing gear, wing elements, and of course, engine components. This significantly reduces the aircraft's overall mass and increases its fuel efficiency. In the medical field, roughly 70% of all implants, such as artificial hip joints or dental prosthetics, are made from titanium. Its unique biocompatibility means the human body doesn't reject it, allowing bone tissue to literally grow into the implant surface. This is a metal that becomes part of a person. Thus, having passed through fire and chemistry, an unremarkable stone transforms into high-tech material that pierces the heavens, explores space, and restores people's ability to move. But titanium conquered not only the sky, but also the darkest ocean depths. At the height of the Cold War, Soviet engineers created something unthinkable: submarines of Project Lyra, known to NATO as Alpha. Their hulls were made entirely from titanium. This allowed them to dive to depths unreachable by the enemy and develop underwater speeds exceeding those of torpedoes. These goldfish, as they were nicknamed for their incredible cost, became underwater phantoms, invulnerable to magnetic detectors and capable of escaping any pursuit. Titanium is the only material capable of withstanding the colossal pressure at depths of 800 meters whilst remaining sufficiently light. Moreover, its absolute resistance to corrosion in salt water makes it an eternal material for the marine element. So what's titanium's main secret, promised at the beginning? It's not just its strength or lightness. Its true magic lies in its ability to self-heal. Every time titanium's surface is scratched, it instantly reacts with oxygen from the air or water and covers itself with the thinnest, invisible, yet incredibly strong film of titanium oxide. This is a sort of invisible armor that instantly regenerates when damaged. It's precisely this film that makes it absolutely inert, preventing it from reacting with the human body or aggressive environments. But this superpower has another side, another secret. During mechanical processing, if proper technique isn't followed, fine titanium swarf can spontaneously ignite. This white fire burns at such high temperatures that it's impossible to extinguish with water or sand. Taming titanium is playing with fire in the literal sense, and only those who've mastered this art can make this mythical metal serve humanity.
What if the most dangerous part of a suspension bridge isn't what you see? Because inside the main cables, which look like solid metal, there's a structure made of tens of thousands of wires, each one vulnerable to destruction by even a drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can see it? The Golden Gate Bridge in San Francisco has two main cables, each about 37 inches in diameter. Inside each one, 27,572 individual wires. If you unwound all these wires and connected them into one line, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one of these cables? Around 24,500 tons. That's comparable to the mass of a small cruise ship. Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made of many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of kilometers. Stay till the end. You'll learn a secret that even bridge engineers don't talk about. Picture the classic example, San Francisco's Golden Gate Bridge. It's got two main cables draped over towers and anchored into massive concrete blocks in the rock. Each cable's about 37 inches across. That's not a cable anymore. It's practically a pillar you'd need 2 or 3 people to wrap their arms around. Inside, 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and link them end to end, and you've got roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. One cable weighs around 24,500 tons, comparable to a small cruise ship or several hundred fully loaded semis. Why so many wires instead of one giant solid rod? Steel handles tension beautifully, but it doesn't tolerate flaws well, especially in large cross-sections. When a cable is made up of thousands of individual wires, each one can give a little, taking on a bigger share of the load in some spots, a smaller share in others. If one wire happens to corrode or weaken for some reason, its contribution to the overall strength is minimal, and you won't even notice it in how the whole cable behaves. Plus, it's way easier to create a flexible shape out of tens of thousands of thin elements. A cable can smoothly wrap around towers, forming a big parabola across the span, whereas a solid rod of that diameter just can't be bent without permanent deformation. The process of making the main cables for a suspension bridge is nothing like how regular steel cables are made at a factory. Nobody ships a pre-made coil a yard thick and thousands of feet long to the construction site. A monster like that would be impossible to deliver or lift into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary working cables between the towers. They run a traveling cart along them that can zip back and forth across the entire span. The cart carries a coil of steel wire. Each trip of the cart means threading another wire between the shores. One end of the wire gets fixed to an anchor on one side. The cart hauls the coil across the span. The wire gets secured on the other shore, and the excess gets cut off. Then the next wire, and so on, tens of thousands of times. To keep this insane marathon from turning into chaos, the wires get organized into what are called strands or subcables. For example, several hundred parallel wires get bundled into one strand of a specific diameter. First, all the wires get tensioned with a little slack. Then special jacks even out the tension, so each little wire carries roughly the same load. Then the bundle gets clamped with rings or special bands to keep it from spreading apart. When there are enough of these bundles, they get brought together and compressed again into a single cylindrical structure. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold incredible force. Picture a bridge deck suspended from it, a steel truss or box girder carrying the road surface. This deck structure transfers the load to the main cables through suspenders. Any vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or multiple trucks together. Wind pushes against the side of the structure with a force that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally just a few inches along their entire length while staying within the elastic range. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The modulus of elasticity and tensile strength of these cables are specifically chosen so that working stresses stay well below ultimate limits, even accounting for wind gusts, temperature swings, and heavy traffic flow. During the design phase, engineers model every possible loading scenario. Both lanes completely filled with trucks, sudden braking, seismic events. The result? An acceptable range of cable elongation and sag
within which the bridge remains safe and comfortable for users. Here's the fascinating part. Despite all that rigidity, the main cables aren't absolutely static. They breathe with the bridge. On a hot sunny day, the steel expands and the cable sags slightly. At night, as temperatures drop, tension increases and sag decreases. In windy weather, you might notice a gentle oscillation in the deck. The cables themselves are actually moving too, though it's invisible to the naked eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters in bridge building history, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic: protecting cables from corrosion. Steel fears moisture and salty fog, especially in coastal regions like San Francisco. If water and aggressive contaminants get inside a cable, reaching each of the tens of thousands of individual wires, corrosion can silently eat away the cross-section for years until it's too late. That's why immediately after strand spinning and compacting are finished, cables get sealed. First thoroughly painted, then the coating is periodically refreshed. Modern bridges employ additional systems: wrapping with airtight tapes, filling gaps with dehumidified air or nitrogen, monitoring humidity inside. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods, which allow engineers to understand the condition of the wires without opening up the cable. All of this is done so that a single strand of infrastructure can safely serve for decades. The cables of the Golden Gate were designed for a service life of tens of years, but thanks to proper maintenance, regular repainting, and monitoring, they still do their job today, holding up the main span of over 4,000 feet. If you add in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire stretched across rivers, bays, and straits, keeping millions of cars suspended in the air every single day. Using main cables made from thousands of steel wires is standard practice for large suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge across the Hudson in New York. It also has two main cables woven from tens of thousands of steel wires. The total length of all that wire is measured in thousands of miles, and the mass of each cable runs into tens of thousands of tons, just like the Golden Gate. The same technology was used on the Brooklyn Bridge, though it's older and combines a suspension system with cable stays. There, the main cables also consist of a large number of thin wires spun on-site rather than brought in as pre-made rope. Modern giants are built using the same principle. For example, Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made from many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of miles, and the design tension reaches hundreds of thousands of tons. A similar approach is used on numerous bridges in China and South Korea, which have been actively building long-span crossings over bays and wide rivers in recent decades. All these bridges share one technology. The main cables are spun on-site from tens of thousands of individual wires, each one tensioned, aligned, and compressed into a unified structure. This technology creates cables of incredible strength and flexibility, capable of holding thousands of tons and handling dynamic loads from wind, traffic, and temperature changes. And so, traveling from a coil of steel wire through tens of thousands of trolley trips across the void, through hydraulic jack tensioning and compression into bundles, through wrapping with protective wire and coating with anti-corrosion paint, the main cable of a suspension bridge is born, a structure of 27,572 individual wires, weighing 24,500 tons, able to stretch several inches under load but staying within elastic deformation, holding in the air a bridge over 4,000 feet long, carrying millions of vehicles every single day. Each wire is a separate element, and if one weakens, it's barely noticeable to the whole system. But if moisture and salt get inside, corrosion can silently destroy wires for years. That's exactly why modern bridges are equipped with humidity monitoring systems, regular inspections, and non-destructive testing. So these giants of steel and concrete can safely serve humanity for centuries.
Imagine a gas capable of changing the course of history. It can disinfect water, create plastic without which modern life is unthinkable, and at the same time become a deadly weapon. This is chlorine. Annually in the United States, over 12 million tons are produced, as much as 120 Gerald Ford aircraft carriers weigh. But the real mystery isn't in the numbers. It's hidden in the technology itself. How does simple salt water, with the help of electricity, give birth to three products that support entire industries? Watch carefully. At the end of this video, you'll learn a fact that will forever change your understanding of this invisible foundation of modern civilization. The United States is one of the world's largest producers of chlorine. Annually, factories in the country produce over 12 million tons of this gas. This figure simply doesn't fit in one's head. Imagine the weight of the Gerald Ford aircraft carrier, the world's heaviest military vessel. That's about 100,000 tons. This means that in 1 year, American industry produces as much chlorine as 120 such carriers weigh. Everything begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. It's either mined in mines or, much more efficiently, pumped from underground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated saline solution called brine. And it's precisely this concentrated salty solution that's our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals. Therefore, before the main show begins, the brine undergoes thorough purification. It's passed through an entire series of tanks where, with the help of chemicals, all impurities are precipitated and filtered from it. At the output, we obtain a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. These are electrolyzers, or cells. It's precisely here that all the magic will occur, or more accurately, all the chemistry. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure saline solution is poured. And into this solution are immersed two electrodes, a positively charged anode and a negatively charged cathode. Now to these electrodes is applied a direct electrical current of colossal force. And here the breakdown begins. The salt molecule in water breaks down into positively charged sodium ions and negatively charged chlorine ions, and the electrical field forces them to move. The positive sodium ions, like a magnet, are attracted to the negative cathode, and the negative chlorine ions to the positive anode. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together and on the anode surface begin to appear tiny bubbles of greenish-yellow gas. This is our chlorine. The main resource for chlorine production is electrical energy. The chlor-alkali industry is one of the largest consumers of electrical energy in the United States. To produce 1 ton of chlorine requires approximately 2,500 kilowatt-hours of electricity. Now, let's multiply this by 12 million tons per year. It turns out that this industry annually consumes about 30 billion kilowatt-hours. That's more than the annual electricity consumption of entire states such as Vermont or Wyoming. But they don't transform into metallic sodium. Instead, electrical current splits the water molecules present in the solution into hydrogen and hydroxide ions. At the cathode are released bubbles of pure hydrogen. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming sodium hydroxide, or caustic soda. This is our second incredibly valuable byproduct. But here arises an enormous problem. We've just obtained 3 substances: chlorine, hydrogen, and caustic soda. And they must not be mixed under any circumstances. Chlorine and hydrogen together form an explosive mixture. And chlorine and caustic soda react, forming bleach, which we don't need at all. This membrane, made from special polymer, resembles a bouncer at a nightclub. It allows positive sodium ions through, permitting them to pass to the cathode, but blocks negative chlorine ions, preventing them from entering the cathode space. Thus, chlorine is born and collects in one part of the cell, whilst hydrogen and caustic soda collect in another. Now we need to gather our harvest. From the anode chamber is continuously pumped wet, hot, greenish-yellow gas. First it must be cooled. Then it must be dried. Chlorine is incredibly aggressive, especially in a wet state. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. It's compressed under enormous pressure and simultaneously cooled. Under this double assault, the gas transforms into a transparent, amber-yellow liquid resembling oil. This liquid chlorine is far more convenient to transport and store. It's poured into special thick-walled steel tanks or railway wagons. Every step of this process occurs under conditions of absolute seal, because leakage of this gas is deadly dangerous. And what about our byproducts? They're no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the factory itself or sold. And the caustic soda solution that formed is pumped out, concentrated, and sold. And so, from simple salt water, passing through it an enormous quantity of electricity, people have learned to obtain 3 extremely important substances at once, which are the foundation for thousands of other products. Now let's look at where all this enormous quantity of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's merely a drop in the ocean. In reality, less than 5% of all chlorine is used for water disinfection. And where does the remaining 95% go? It's a key building block for other products. About 40% of all chlorine goes to producing this universal plastic. Vinyl windows in your house, water pipes, medical drips, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% approximately is used for creating thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. And chlorine is also a key component for bleaching paper, giving it that very clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we obtain approximately 1,100 kilograms of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business.
Picture a metal that's everywhere in nature, yet remains one of the most expensive and difficult materials for industry to work with. That metal is titanium. It's abundant in the Earth's crust, but producing it is so labor-intensive, energy-hungry, and technologically finicky that the aviation industry literally fights for every quality pound. And that's not an exaggeration. Without titanium, there'd be no modern jet engines, no critical aircraft components, no landing gear parts, no structural elements where you need high strength, low weight, and corrosion resistance all at once. But the journey of titanium from black sand or ore concentrate to an aircraft part is remarkably far from conventional metallurgy. You can't just melt it down, reduce it with carbon, and pour it into a mold like steel or iron. Titanium is too reactive. It bonds with oxygen way too easily. It's too sensitive to contamination. And that's exactly why producing titanium for aviation isn't just mining and smelting. It's one of the most complex sequences of chemical and metallurgical operations in modern industry. In nature, titanium almost never occurs as pure metal. Industry extracts it from minerals, mainly rutile and ilmenite. Very often, these ores aren't mined in classic deep mines, but in what are called mineral sands, placer deposits that form along coastlines and in ancient sedimentary zones. This means the first stage of titanium production looks totally different from the typical picture of miners and mine shafts. Here, they might use dredges, excavators, washing systems, gravity and spiral separators that separate heavy minerals from lighter waste rock. But even after processing, what you have isn't metal yet. It's just titanium-bearing raw material. And this is where the main paradox kicks in. Titanium is extremely abundant, but extracting actual metallic titanium from its oxides is way harder than smelting many far rarer metals. That's exactly why titanium is expensive, not because it's rare in nature, but because turning ore into aviation-grade metal is brutally complex. The next stage is converting the ore into a chemical form from which pure metal can actually be extracted. For titanium, this is especially critical because the usual heat-based reduction doesn't work here. While iron or copper can be processed using relatively straightforward metallurgical methods, titanium is a different beast. Its oxide is too stable, and the metal itself, at high temperatures, binds too aggressively with oxygen, nitrogen, and carbon. So industry takes an indirect route. Titanium feedstock is first converted into titanium tetrachloride, a volatile chemical compound that can then be purified. To do this, the concentrate undergoes high-temperature chlorination in the presence of a reducing agent, and then the resulting product is sent for purification. The key advantage of this approach is that titanium tetrachloride can be purified through distillation, removing a whole range of unwanted impurities. Essentially, this is the moment when rough mineralogy transforms into chemically controlled feedstock for the metal to come. And it's at this stage that it becomes clear. Titanium production isn't classic smelting. It's a chemical, metallurgical process with extremely tight purity requirement. Once the purified titanium tetrachloride is ready, one of the industry's most critical processes kicks in, the Kroll process. This is the fundamental industrial technology that makes modern mass production of titanium for aviation, aerospace, and other high-tech fields even possible. Here's how it works. Purified titanium tetrachloride reacts with molten magnesium inside a sealed reactor. The result? The metal breaks free from chlorine and forms what's called titanium sponge. This isn't a solid ingot or finished semi-product yet. It's a porous, brittle metallic mass that looks like hardened porous rock. After the reaction, leftover magnesium and byproducts get removed. Then the sponge is sorted, crushed, and prepped for the next stage.
At first glance, you might think the sponge is almost finished metal, but really, it's only halfway through a long journey. Aviation doesn't just need titanium, it needs material with precise chemical composition, high uniformity, and predictable behavior under stress. So next, this sponge still has to be transformed into a full-fledged structural metal. The next major stage is remelting the titanium sponge into a dense, homogeneous ingot. And this is where production gets especially tricky again. Molten titanium aggressively absorbs oxygen, nitrogen, and other impurities from the surrounding environment. Even slight contamination can make the metal brittle and unsuitable for critical aircraft components. That's exactly why titanium remelting doesn't happen in a regular shop floor atmosphere. It's done in a vacuum or a controlled inert environment. One of the key methods is vacuum arc remelting. For this process, they form a consumable electrode from titanium sponge, alloying additives, and sometimes a portion of quality scrap returns. Then, this electrode is gradually melted by an electric arc, and the metal collects drop by drop in a water-cooled mold, forming an ingot. For critically important aerospace applications, a single remelt like this often isn't enough. So the metal may go through double or even triple remelting to achieve maximum structural uniformity, stable composition, and the absolute minimum number of defects. But aviation doesn't just need pure titanium. In most cases, the foundation is special titanium alloys, and the most famous of these is Ti6Al4V, also known as Grade 5. In this material, titanium is alloyed with aluminum and vanadium to achieve a combination of properties that's practically impossible to replicate in many other metals. This alloy is noticeably lighter than steel, yet it has very high specific strength, good fatigue resistance, and outstanding corrosion resistance. That's exactly why it's used in compressor discs and blades of aircraft engines, in landing gear components, structural load-bearing elements of the aircraft, and other assemblies where every pound matters. But for titanium to become a true aerospace material, it's not enough to just melt it into an ingot. What follows is forging, rolling, heat treatment, microstructure control, and mechanical property verification. In other words, aerospace-grade titanium isn't just a metal, it's an entire series of carefully sequenced operations, each one affecting the final reliability of a part that will later operate under enormous loads. This is where it becomes clear why titanium is so expensive. First, production isn't continuous, it's largely cyclical. The Kroll process is slow and energy-intensive. It requires magnesium, chlorine, sealed reactors, and complex purification afterward. Second, almost every hot stage demands a vacuum or inert atmosphere. Why? Because the metal reacts too aggressively with oxygen. Third, titanium itself is a nightmare to machine. It has low thermal conductivity. Heat doesn't escape into the chips. Instead, it concentrates on the cutting tool. This accelerates tool wear, slows down machining speeds, and drives up the cost of every finished part. On top of that, titanium semi-finished products require extremely precise control of structure and chemistry, and tolerances in aviation are far tighter than in mass industry. The bottom line? Titanium isn't expensive because it's rare in nature. It's expensive because the entire chain, from ore to aerospace-grade alloy, is extraordinarily complex, long, and sensitive to any deviation from the process. There's one more reason titanium is so valued specifically in aviation. It fits perfectly into the philosophy of modern engineering,
where weight savings directly translate into efficiency gains. A lighter aircraft burns less fuel, carries more payload, and its engine and structural components operate in more favorable conditions. But titanium isn't a universal replacement for steel or aluminum. It's used where it truly justifies its cost, in hot sections, highly stressed components, corrosive environments, and parts where the combination of strength and low weight is critical. That's why titanium production for aviation isn't just metallurgy for the sake of metal. It's an industry where every step serves a single purpose: to create a material that will perform reliably in an aircraft at high speeds, under cyclic loads, vibrations, temperature swings, and with enormous responsibility for safety.
When you look at titanium's entire journey, you're witnessing a nearly perfect example of modern high-tech manufacturing. First, heavy mineral sands or ore concentrates get separated from waste rock. Then, chemical processes transform the raw material into purified, volatile compounds. Next, through the Kroll process, they obtain porous titanium sponge. After that, it's remelted into ingots under vacuum, alloyed, structurally and chemically refined several times over, and only then transformed into semi-finished products and parts for aviation. In other words, titanium's journey is a path from dirty natural mineral to a material that can work inside a jet engine or an aircraft structural assembly. And perhaps that's where titanium's real power lies. It seems like just another element in Earth's crust, but actually becomes a true engineering marvel only after incredibly complex technological processing. That's why aviation-grade titanium isn't just a metal. It's the embodiment of how far industry can push when it needs the perfect balance of strength, lightness, durability, and reliability. The Caterpillar 3618 engine, 18 cylinders, 88 gallons of displacement, 7,200 kilowatts of power, 9,655 horsepower. One engine weighs 79,000 pounds. The piston in this engine, 11 inches in diameter, 11.8 inches of stroke, 50 pounds in weight. This is Caterpillar's largest piston. How do they make it from liquid aluminum? Today you'll see the complete production cycle of a giant piston, from an aluminum ingot to a part that moves at 33 feet per second and withstands 2,685 psi. If you want to see how they make the heart of a giant engine, subscribe to the channel. Here we show you the factories that move the world. The Caterpillar 3618 engine is designed for high-speed marine vessels, ferries, patrol boats, yachts. A single engine produces 9,655 horsepower at 1,050 revolutions per minute. It's a V18 four-stroke diesel. Cylinder bore is 11 inches. Stroke is 11.8 inches. Displacement per cylinder is 1,130 cubic inches. 18 cylinders total, 20,330 cubic inches. Compression ratio 12.6 to 1. Maximum cylinder pressure 2,680 psi. That's 185 atmospheres. Combustion chamber temperature 3,600 degrees Fahrenheit. Mean piston speed 34.4 feet per second. The piston travels 11.8 inches in 0.028 seconds. Up and down 1,050 times per minute. 70 million cycles over 10,000 hours of operation. The piston material has to withstand all of that. The piston is made from an aluminum alloy. Aluminum is lightweight, density of 169 pounds per cubic foot. That's 3 times lighter than steel. Aluminum conducts heat well. Thermal conductivity of 133 BTU per hour per foot per degree Fahrenheit. That's 5 times better than steel.
They use alloy 2618. Composition: 92% aluminum, 4% copper, 1.5% magnesium, 1% nickel, 1% silicon. Copper provides strength at high temperatures. Magnesium increases hardness. Nickel reduces thermal expansion. Silicon improves casting properties. The alloy arrives in ingots. Shape: a cylinder 12 inches in diameter, 3 feet 3 inches long. Ingot weight: 353 pounds. Before forging, the ingot is cut into blanks. Blank length: 12 inches. Weight: 84 pounds. This is the blank for one piston with extra material for machining.
The blank gets loaded into an induction furnace. Temperature: 895 degrees Fahrenheit. Heat time: 30 minutes. The aluminum softens. Doesn't melt. Melting happens at 1220 degrees. We need plasticity for forging. The heated blank transfers to a forging press. Hydraulic press. Force: 10,000 tons. That's 100 meganewtons. The blank sits in the lower die. Die made from heat-resistant steel. The upper die descends from above. The press creates pressure. Aluminum flows, fills the die cavity, takes the shape of a piston. The process is called backward extrusion. Metal flows upward around the punch, forms the piston skirt. Pressure climbs to 10,000 tons. Forging time: 12 seconds. Metal densifies. Grains align along stress lines. This makes the piston strong. Forging increases strength 30% compared to casting. After forging, the press opens. Piston extracted. It's hot, 750 degrees. Weight: 66 pounds. Shape's close to final, but machining still needed.
Heat treatment. The forged piston goes into the hardening furnace. Temperature: 986 degrees Fahrenheit. Hold time: 8 hours. Copper and magnesium dissolve into the aluminum. The structure becomes uniform. Then, rapid cooling in water. Water temperature: 68 degrees. Cooling rate: 180 degrees per second. Copper and magnesium don't have time to precipitate out. They're trapped in the lattice. Strengthening zones form. After quenching, the piston is soft. Hardness: 60 on the Brinell scale. Artificial aging is needed. The piston is heated again. Temperature: 374 degrees. Time: 16 hours. Copper and magnesium precipitate from the lattice as fine particles. They strengthen the aluminum. Hardness climbs to 135 on the Brinell scale. Strength reaches 65,000 pounds per square inch. Elongation: 10%. The piston is strong and ductile at the same time.
Machining begins with the turning operation. The piston gets clamped into the chuck of a CNC lathe. The chuck diameter is 19.7 inches. Spindle speed is 300 revolutions per minute. The cutting tool is carbide, tungsten carbide. They machine the outer surface of the skirt. Final diameter is 11.02 inches. Tolerance: plus or minus 0.0008 inches. Skirt taper: 0.002 inches per inch of length. This compensates for thermal expansion. Cutting speed is 490 feet per minute. Feed rate is 0.008 inches per revolution. Depth of cut is 0.02 inches. They remove 0.28 inches from the diameter. Machining time is 20 minutes. The surface is smooth. Surface roughness is 63 micro-inches. Then they mill the ring grooves. 3 grooves. Width of the first is 0.16 inches. Second is 0.14. Third is 0.2 inches. Depth of the first is 0.31 inches. Milling cutter diameter is 4 inches. Spindle speed is 1200 revolutions per minute. Groove accuracy plus or minus 0.0004 inches. They're drilling the hole for the piston pin. Hole diameter, 4.33 inches. Depth, 7.87 inches. Carbide drill bit. Rotation speed, 500 revolutions per minute. Feed rate, 0.006 inches per revolution. Drilling time, 8 minutes. After drilling, reaming. The reamer brings the diameter to 4.3302 inches. Tolerance, plus 0.0004 inches, minus 0. Surface roughness, 0.315 thousandths of an inch. This is an interference fit for the bronze bushing. The bushing gets press fit with 10 tons of force. Interference, 0.0012 inches. They mill the oil channels. 2 channels, diameter 0.47 inches, running from the crown to the skirt. They carry oil away for cooling. They drill the oil jets. Diameter, 0.079 inches. 8 of them around the crown circumference. Oil sprays through them onto the inner surface. Cooling is critical. Crown temperature hits 662 degrees Fahrenheit. The oil carries the heat away. Machining the combustion chamber. The piston crown gets milled on a 5-axis machine. The combustion chamber has a complex shape. A toroidal cavity, diameter 7.1 inches, depth 2 inches, chamber volume 0.3 gallons. The shape's optimized for mixing fuel with air. Ball nose cutter, diameter 0.8 inches. Spindle speed 3,000 revolutions per minute. Tool path spirals from center to edge. Spiral pitch 0.02 inches. Machining time 40 minutes. Surface roughness 0.00016 inches. Then chamber polishing. Abrasive paste, 3-micron grit. Polished with a felt wheel. Speed 1,000 revolutions per minute. Time 5 minutes. The polished surface prevents carbon buildup. Final operation, honing the skirt. Honing creates a crosshatch pattern of micro grooves. Angle 60 degrees. Groove depth 0.00012 inches. Width 0.0008 inches. These grooves retain the oil film, reduce friction. Honing time 10 minutes. Coatings and inspection. The crown gets a ceramic thermal barrier coating. Thickness, 0.3 millimeters. Material, yttria stabilized zirconia. Thermal conductivity, 2 watts per meter Kelvin. That's 100 times less than aluminum. The coating drops the crown temperature by 100 degrees. Applied by plasma spray. Plasma temperature, 10,000 degrees. Particle velocity, 1,000 feet per second. The skirt gets a graphite coating, anti-friction. Thickness, 0.015 millimeters. Cuts friction by 40%. Reduces wear at startup. Ring grooves get hard anodized. Hard anodization. Layer thickness, 0.05 millimeters. Hardness, 500 Vickers. Protection against ring wear. Every piston gets inspected. Diameter measured at 6 points. Laser micrometer. Accuracy, 0.001 millimeters. Weight gets checked. Scale accurate to 1 gram. Tolerance, plus or minus 5 grams. Weight variance in a set, no more than 10 grams. For engine balancing. X-ray checks internal defects, cracks, porosity, inclusions. Rejection rate, 0.5%. Finished piston weighs 51 pounds. Diameter, 11 inches. Height, 13.8 inches. It'll run 10,000 hours, 70 million cycles. Handle temperatures of 350 degrees. Pressure, 185 bar. Speed, 33 feet per second. That's how Caterpillar makes the biggest pistons. From aluminum ingot to a component that holds 9,000 horsepower. If this was interesting, hit that like button. Comment what engines you know. Subscribe. Here we show you how giants get made.
Imagine a substance that doesn't melt, leaves not a single drop of water, and simply vanishes into thin air. It can freeze anything within seconds, create thick white fog that rolls across the ground, and even stop life itself if handled carelessly. Dry ice isn't just cold, it's a controlled force of nature that humans have learned to harness. Deep beneath the hum of compressors and swirling clouds of white vapor lies a process that seems like magic, where gas transforms into solid matter at -78 degrees. But where does this gas come from on an industrial scale? And why is dry ice production considered a genuine environmental miracle? Watch until the end and you'll see how something so cold can become one of the hottest businesses in the world. Industrial dry ice is nothing other than solid carbon dioxide, which freezes at the extreme temperature of -78.5 degrees Celsius. Put simply, it's the very same carbon dioxide we exhale with every breath, which plants absorb and which gives fizz to your favorite carbonated drinks. Unlike ordinary ice, which melts into water, dry ice possesses a remarkable property: sublimation. It transitions from solid state directly to gas, bypassing the liquid phase entirely. That's why it's dry. It leaves no puddles behind, simply disappearing into invisible gas. This unique ability to cool instantly and evaporate without trace has made it indispensable across dozens of industries. In medicine, dry ice is a genuine guardian of life. It's used for transporting vaccines, donor organs, and blood, where every second's delay and every extra degree could cost a life. In cryotherapy, it's applied for targeted freezing and removal of warts. In the food industry, it's become a guarantor of freshness. Frozen products, meat, and ice cream are transported in containers filled with this cold wonder. And in the world of entertainment, dry ice is the chief instrument for creating magic. The thick, heavy fog rolling across stages at concerts and theatrical performances, or smoking cocktails in bars, all of this is the work of dry ice, which creates impressive visual effects when it contacts hot water. Dry ice production takes place at cryogenic plants. These facilities occupy enormous industrial areas, comparable to several football pitches. At the center of the site stand gigantic cryogenic tanks, steel towers up to 50 feet high, capable of holding up to 100 tons of liquid carbon dioxide. Inside the workshops, there's a constant hum, powerful compressors and hydraulic presses at work. From the giant tanks, liquefied gas flows through thick, frost-covered pipes into the very heart of production, the pressing installations. These machines are absolute monsters, capable of compressing up to 500 kilograms of dry ice in a single minute. When liquid carbon dioxide under enormous pressure bursts from the nozzle into a chamber at normal atmospheric pressure, rapid expansion occurs. This process, known as the Joule-Thomson effect, causes the gas to cool and freeze instantly, transforming into loose, snow-like dry ice. A cloud of thick white vapor rises above the pressing chambers as powerful hydraulic presses, with force measuring hundreds of tons, compress this snow into dense, heavy briquettes or fine pellets. Conveyor belts move continuously, carrying away the icy blocks. They pass through refrigerated tunnels where temperature is kept below -40 degrees. Automated machines slice large slabs into smaller pieces or transform them into pellets the size of peas. Packaging machines work at lightning speed. Precisely calculated quantities of dry ice are poured into special polystyrene thermal containers, from small 1-kilogram packets to enormous containers holding hundreds of kilograms. Automatic sealers hermetically close the packages to slow the sublimation process. In 1 hour, a single such plant can produce about 5 tons of product. Now imagine the working conditions in this frozen kingdom. In zones where presses and packaging lines operate, temperature stays below -40 degrees. Workers here resemble polar explorers. They're dressed in multi-layered thermal insulation suits wearing special gloves on their hands, since direct contact with dry ice causes instant and extremely painful burns. On their faces are protective goggles and masks, as high concentrations of carbon dioxide in the air can cause dizziness and suffocation. Because of this, powerful ventilation systems must operate in the premises, constantly refreshing the air and maintaining safe oxygen levels. To avoid hypothermia, workers labor in short shifts, alternating work in cold zones with breaks in warm restrooms. Many processes are maximally automated to reduce human presence in extreme conditions. But even with such protection, work at these plants demands incredible endurance and the strictest adherence to safety procedures. So where do plants obtain carbon dioxide in such colossal quantities? The secret is that they don't produce it specially, they collect it. It's a byproduct of other major industrial processes. The main sources are ammonia and fertilizer plants, breweries where gas forms during fermentation, as well as petroleum refining and cement works. Rather than releasing this carbon dioxide into the atmosphere, it's captured by special installations. The gas then undergoes multi-stage purification from impurities, is dried and compressed under high pressure, transitioning to liquid state. This process is the brightest example of industrial symbiosis and circular economy, where waste from one production becomes valuable raw material for another. But for all its usefulness, dry ice is a substance requiring extreme caution. Its temperature is so low that it can cause serious burns upon contact with skin. But the main danger lies in its sublimation. Whilst evaporating, dry ice displaces oxygen from enclosed spaces. Being in an unventilated room where large quantities of dry ice are evaporating can lead to suffocation. Tragic cases are known where people suffered fatal poisoning using dry ice to create fog and enclosed swimming pools. Therefore, working with it requires strict adherence to safety rules, good ventilation, use of protective gloves and goggles. Now let's glimpse into the future, because dry ice has an incredibly exciting one ahead. Right now, scientists and engineers are developing technologies where dry ice plays a key role. For example, in fire suppression. Unlike water or foam, dry ice doesn't conduct electricity and leaves no traces, making it ideal for extinguishing fires in server rooms, museums, or power stations. Dry ice pellets are sprayed onto fire, instantly cooling it and displacing oxygen. Another direction is cryogenic cleaning or blasting. Tiny dry ice pellets are fired under high pressure at contaminated surfaces. Striking them, they instantly evaporate, and the micro-explosion caused by rapid gas expansion literally blasts off dirt, paint, or rust without damaging the surface itself. But the most fantastic prospect is terraforming planets. Scientists are seriously considering the possibility of using carbon dioxide, which in solid form covers Mars's polar caps, to create an atmosphere. By melting Martian dry ice using nuclear explosions or gigantic mirrors, one could trigger a greenhouse effect that would warm the planet and make it habitable. So this cold, smoking material that we use today for cooling drinks might one day become the key to transforming the red planet into our second home. This proves that even the most ordinary-seeming substances conceal within them boundless potential that humanity has yet to unlock.
This is Duisburg, Germany, and right in the middle of this city stands the ThyssenKrupp steel plant, the biggest steel complex in the European Union. 15 square miles, 26,000 workers, 10 million tons of steel a year. That's more than entire countries produce. Every third car in Europe runs on steel that was born here. Every other refrigerator, every rail, every tin can, here. Today we're walking through this plant from start to finish. From a chunk of iron ore to a gleaming sheet of steel that tomorrow becomes the hood of your car. It doesn't start in Duisburg, it starts thousands of miles away, in the mines of Brazil, Australia, and Canada. Iron ore isn't pure metal. It's rock where iron is mixed with sand, clay, and dozens of other minerals. Average iron content in the ore runs between 60 and 65%. The rest is waste rock that has to be removed. The ore gets crushed in massive cone crushers down to a size of about a 1/4 inch to 3/4 of an inch. Then it heads to the sintering plant, the first processing stage right at the Duisburg facility. Here, fine ore dust is mixed with coke breeze and limestone. The mixture gets laid down in a layer on a moving belt pallet conveyor and ignited from above by gas burners. Combustion temperature hits 2,200 degrees Fahrenheit. During sintering, the ore particles fuse together, forming porous chunks. Sinter. This isn't dust or sand anymore. These are solid porous lumps 3/4 of an inch to 2 inches across, perfect for loading into a blast furnace. The porosity of the sinter is critical. Hot air needs to flow freely through it during smelting. Every hour, the sintering belt produces between 800 and 1,000 tons of finished sinter. While agglomeration is happening at the plant, coking runs in parallel. Coke isn't just coal, it's chemically processed coal that releases carbon monoxide when burned, essential for reducing iron from ore. Regular coal won't cut it, it burns too fast and leaves too much ash behind. ThyssenKrupp's coke batteries are rows of vertical chambers, 23 feet tall and about 20 inches wide. Each chamber gets loaded with 25 tons of coal and heated to 2,000 degrees Fahrenheit without any air. The process takes 18 hours. During that time, tars, ammonia, hydrogen sulfide, and benzene evaporate out of the coal. These gases get captured and processed. They become fuel or chemical feedstock themselves. What's left is pure coke, silvery black porous chunks, hard as rock. When the chamber door opens, a special ram pushes the glowing coke onto a quenching car. A column of fire and smoke shoots up 65 feet. The car races to the quenching tower, where thousands of gallons of water come crashing down on the red-hot coke. Steam and smoke engulf everything around. Within minutes, the coke cools to 200 degrees and it's ready for the blast furnace. The blast furnace is the heart of the entire plant. ThyssenKrupp in Duisburg has 4 of them. Each one is a cylindrical steel tower standing 260 feet tall, lined on the inside with refractory brick. From the top, they continuously load the charge, layers of sinter, coke, and limestone in precisely calculated proportions. From below, through tuyères, openings about 3 inches in diameter, superheated air at 2,200 degrees Fahrenheit blasts in at nearly 60 pounds per square inch. When that scorching air hits the coke, it ignites at temperatures exceeding 3,600 degrees. Oxygen from the air reacts with the carbon in the coke and forms carbon monoxide. This gas rises up through the charge and reduces the iron oxides, strips the oxygen right off them. The iron is reduced and, in liquid form, trickles down to the bottom of the furnace. Slag flows down there too, a liquid mass of molten limestone and rock. Every 4 to 6 hours, they tap the pig iron through a tap hole, a special opening in the lower part of the furnace. First, they drill through a plug of refractory clay with a pneumatic drill, and from the opening, streams of liquid metal at 2,700 degrees come gushing out with a hiss and a shower of sparks. One tap yields between 200 and 300 tons of liquid pig iron. Every day, each blast furnace produces between 4,000 and 5,000 tons of pig iron. Molten iron pours into massive ladles, cylindrical vessels with refractory lining that hold 300 tons. The ladle heads to the desulfurization station. Iron from the blast furnace contains up to 0.6% sulfur, a disaster for future steel quality. Sulfur makes metal brittle. It cracks during rolling and welding. Through a submerged lance, they blow in magnesium powder, or a mix of lime and calcium carbide. Magnesium reacts with sulfur, forming magnesium sulfide, solid slag that floats to the surface. A scraper removes the slag from the top. In 20 minutes, sulfur content drops from 0.6 to 0.02%. That's 30 times less. Now the iron's ready to become steel. They pour it into a basic oxygen furnace, a massive pear-shaped vessel holding 300 tons. From above, an oxygen lance descends onto the molten iron. From it, a jet of pure oxygen blasts out at several times the speed of sound. Ignition is instant. Temperature in the reaction zone exceeds 2,000 degrees. Carbon oxidizes, forming carbon dioxide. It bursts from the furnace with a column of flame and sparks. The whole process in the converter takes 20 to 25 minutes. During this time, the carbon content drops from 4% in pig iron to 0.2 in steel. At the same time, phosphorus, manganese, and sulfur residues are removed from the converter. The slag is poured off by tilting the converter. Then it's tilted the other way, and through the tap hole, the finished liquid steel is poured into a ladle. But that's not the end. The liquid steel goes to a secondary metallurgy unit. Here, alloying elements are added: chromium, nickel, molybdenum, vanadium, depending on what grade of steel is needed. For automotive sheet, one recipe. For pipeline steel, another. For packaging material, a third. ThyssenKrupp produces over 900 grades of steel. In a vacuum unit, dissolved gases, hydrogen and nitrogen, are removed from the steel. Hydrogen is especially dangerous. It diffuses into the metal's crystal lattice and can cause internal cracks hours after rolling. After vacuum degassing, hydrogen content drops below 0.02 cubic centimeters per 100 grams, a safe level for any application. The finished liquid steel heads to the continuous casting machine. This is the longest unit in the plant, almost 650 feet from start to finish. The liquid steel gets poured into a mold, a water-cooled copper form that sets the shape of the future blank. Coming out of the mold, the metal already has a solid shell about an inch thick, but inside it's still liquid. Gradually cooling on rollers, the continuous metal ribbon fully solidifies. Then it's cut with gas torches into slabs, 26 to 40 feet long, up to 6.5 feet wide, and 6 to 10 inches thick. One slab weighs 15 to 30 tons. ThyssenKrupp's continuous casting machine has a capacity of 500 tons per hour. The new fourth line, launched in July 2025 after 800 million euros in investment, significantly improved casting precision and metal purity. Hot slabs weighing 20 to 30 tons travel by roller table to the hot rolling mill. But first, the reheating furnace, a walking beam furnace 650 feet long. The slabs move slowly through it for 2 hours until the temperature equalizes throughout the entire cross-section to 2,300 degrees Fahrenheit. Uneven heating is catastrophic. If the center is even 125 degrees cooler than the surface, internal tears will form during rolling. After the furnace, the slab passes under the descaler. Water jets at 2,200 pounds per square inch blast away the scale, a layer of oxidized metal. Scale 1/10 of an inch thick, if not removed, gets rolled into the surface and leaves defects. Then roughing begins. A reversing stand with rolls 4 feet in diameter presses on the slab with a force of 80,000 tons. In 7 to 9 passes back and forth, a slab 8 inches thick transforms into a transfer bar, 3/4 to 1 1/4 inches thick. Length increases tenfold in the process. From a 26-foot slab emerges a 260-foot strip, racing at 10 feet per second. Absurd. Finish rolling is 7 stands positioned one after another, 50 feet apart. The strip passes through all 7 without stopping. In the first stand, thickness is about 3/4 of an inch. In the last, from around 1/20th to 3/4 of an inch, depending on the order. Speed builds from stand to stand. If the strip enters the first stand moving at around 3 feet per second, by the time it exits the 7th, it's already hitting 65 feet per second. That's 45 miles per hour. The strip flies like a silver ribbon. Tension is maintained between each pair of stands. If it drops, the strip runs off the mill and triggers an emergency shutdown. After finish rolling, the hot-rolled strip feeds onto a coiler, where it's wound into a coil weighing up to 30 tons and measuring up to 6.5 feet in diameter. Before coiling, the strip is cooled on a roller table with a water spray. Temperature drops from 1650 down to 930 to 1100 degrees. This coiling temperature is critical. It determines the metal's structure and therefore its mechanical properties. Each coil is automatically measured, weighed, and marked. The hot rolling mill at the Duisburg plant produces over 5 million tons of hot-rolled steel per year. Some of the coils go straight to customers. Construction companies, pipe manufacturers, shipbuilders. But a significant portion goes further, to cold rolling. Cold rolling is needed where a thin sheet of perfect quality is required. Automotive, appliances, food packaging. First, the coil is unwound and run through a pickling line. The hot-rolled strip is covered with an oxide film, scale. It's hard, abrasive, and interferes with further processing. The strip is pulled through baths of hydrochloric acid solution at 176 degrees Fahrenheit. The acid dissolves the scale but doesn't affect the metal itself. Then the strip is rinsed with water, neutralized with soda solution, and dried. Clean, shiny surface. Now it's ready to roll. A cold rolling mill is 4 or 5 stands in a line. Unlike hot rolling, where the metal is pliable from heat, here it's rolled cold. Roll pressure. Up to 100,000 tons per meter of strip width. The sound in the shop? Continuous metallic thunder. Vibration felt through the soles of your boots. From a thickness of 2 to 4 millimeters, the strip is stretched to 0.6 to 1 millimeter. That's a reduction of 4 to 6 times. Rolling speed at the exit on up to 30 meters per second, 67 miles per hour. Cold rolling strengthens metal but makes it brittle. This is called work hardening. The crystal lattice deforms and stops the movement of dislocations, and dislocations are what give you plasticity. To restore flexibility to the metal, you anneal it. At ThyssenKrupp, they use bell-type furnaces. Coils are stacked vertically on stands in groups of 3 to 4, covered with an inner bell and an outer hood. A protective gas, a mix of nitrogen and hydrogen, gets fed inside to prevent surface oxidation. The furnace slowly heats the coils to about 1,300 to 1,400 degrees Fahrenheit. At this temperature, the metal atoms get enough energy to restructure the crystal lattice. Deformed grains get replaced by new ones, smaller and more regular. This process takes 18 to 24 hours. After heating, the furnace cools slowly, another 24 to 36 hours. You can't rush it. Uneven cooling creates residual stresses and warping of the sheet. After annealing, the metal's soft and pliable again. But the surface has gone dull. The rollers left behind micro-roughness. For automotive bodies, that's unacceptable. The final rolling stage is skin pass rolling. It's a light pass with a reduction of just 0.5 to 2%. The goal isn't to reduce thickness, but to give the surface the right roughness and finally flatten the sheet. Skin pass rolls have a special surface that transfers onto the strip. Automotive sheet needs minimal roughness. It has to stamp well and be perfectly smooth under the paint job. Roofing steel needs more roughness so paint grips better. After skin passing, the strip gets cut or left in a coil, depending on the order. But most of the sheet goes further, to the coating lines. The most common coating is galvanizing. The continuous hot dip galvanizing line. The strip unwinds, gets cleaned in an alkaline solution, passes through an annealing furnace, then plunges into a bath of molten zinc at 840 degrees Fahrenheit. A zinc coating forms on the surface, 0.3 to 1/1000th of an inch thick on each side. Air knives, jets of compressed air, blow off excess zinc and even out the coating thickness. This coating protects the steel from corrosion for 20 to 30 years. It's this galvanized steel from Duisburg that covers the bodies of most cars in Europe. Finished rolls of galvanized steel head to the warehouse and out to customers. Each roll comes with a quality certificate, 20 to 30 pages long. It lists the chemical composition down to thousandths of a percent, mechanical properties, yield strength, tensile strength, elongation, hardness. It documents the temperature and duration of every single production stage. If a problem pops up a year later at a customer's plant, engineers can trace the entire production history of that specific roll down to the minute. Every year, the Duisburg plant processes 40 million tons of raw materials and produces 10 million tons of finished steel. 234 years in one spot, and the plant still beats at the very heart of European industry. If you found it fascinating to see how steel is born, from iron ore to the perfect sheet for your car, hit that like button on this video. Drop a comment if you knew that 1 ton of steel hides an entire factory of chemical reactions inside it. And subscribe to the channel. Here we open up the industries that quietly hold our world together.
Picture a chunk of metal weighing 130 tons, the size of a 3-story building, spinning at 100 revolutions per minute. This is a supertanker's propeller, the most powerful driving force ever created by humans. Every second, this propeller pushes 200,000 tons of cargo forward. A single sweep of its blade generates the power of 50 cars. But here's the most incredible part. This giant is cast as a single monolith. No welding, no bolts. One solid piece of bronze or steel. How did humanity learn to cast metal structures the size of a house? You'll discover why a propeller like this takes 2 weeks to cool, how it's machined for 3 weeks, and why the tiniest crack could send a ship to the bottom. Watch until the end. The finale reveals the scale of engineering madness that moves the oceans. This is the story of how titans of the seas are born.
The history of the propeller began in the early 19th century. Before that, ships moved either under sail, by oars, or using paddle wheels. Paddle wheels were inefficient. Half the energy was wasted. In 1836, British farmer and inventor Francis Pettit Smith patented the screw propeller. The idea was simple. Rotating blades screw into the water like a corkscrew into a cork, pushing the ship forward. Early propellers were small, 4 to 5 feet in diameter, made from wood or cast iron. But as ships grew larger, so did the propellers. By the early 20th century, steel steamships over 300 feet long appeared. They required propellers 10 to 13 feet in diameter. And with the arrival of supertankers and container ships in the mid-20th century, propeller sizes reached incredible proportions. Modern ocean giants stretching 1,300 feet need propellers 26 to 33 feet in diameter. That's the height of a 3-story building.
The world's largest propeller was built for the Emma Maersk container ship, one of the biggest vessels on the planet. The propeller's diameter? 31.5 feet. Weight, 131 tons. That's 2 tanks combined, or 17 elephants. The propeller has 6 blades, each the size of a car. Total blade surface area, about 750 square feet, like a big apartment. The ship's engine produces 109,000 horsepower. All that power flows through a single propeller. At full speed, the blade tips slice through water at 125 miles per hour. Water pressure on the blades, dozens of tons per square foot. Any crack, any casting flaw, and centrifugal force rips the propeller apart. The ship's dead in the middle of the ocean. That's why manufacturing these propellers is the pinnacle of metallurgy and engineering. The slightest mistake is unacceptable.
Where and how do they make these monsters? The largest propeller manufacturers are in Japan, South Korea, China, Germany, and the Netherlands. The most famous include Japan's Nakashima, Germany's Mecklenburg Metallgas, and the Dutch Works4. They have foundries the size of a football field and cranes that can lift 200 tons. The process starts with design. Engineers calculate blade shapes on supercomputers. Angle of attack, curvature, thickness, everything affects efficiency. The propeller needs to create maximum thrust with minimal cavitation, the formation of water bubbles that destroy metal. The tiniest miscalculation and the propeller becomes inefficient or wears out fast. After the calculations, they create a full-size wooden model of the propeller. Yes, wood, 31 feet in diameter. Master craftsmen carve it for weeks using blueprints and templates, precision down to a millimeter. This wooden model becomes the foundation for creating the casting mold.
They coat the wooden pattern with a special compound and place it in a massive flask, a steel box the size of a room. Around the pattern, they pack in molding sand, sand mixed with binding agents. The mixture gets packed layer by layer. Each layer is compacted through vibration and pressure. The process takes several days. Once the flask is full, they split the mold into 2 halves and carefully remove the wooden pattern. What remains is a cavity shaped like the propeller, a negative. They coat the interior surface of the mold with a refractory compound so the molten metal won't damage the sand. Then they bolt both halves back together. The mold has to withstand the pressure of 130 tons of liquid metal. They install the gating system, channels that'll feed metal into the mold. It's calculated so the fill happens evenly, without air pockets or cold joints. The mold is ready. Now comes the really impressive part, melting the metal. In the foundry, there's a massive induction furnace, a steel crucible holding 40 cubic meters wrapped in electromagnetic coils. They load it with bronze or alloyed steel stock, bars, ingots, scrap. 140 tons of metal. That's with a buffer. Some will stay in the gates and risers. They flip the switch. Powerful electromagnets induce eddy currents in the metal. The metal starts heating from the inside. Temperature climbs to 1600 degrees Celsius. The metal melts, glows orange, then white. The surface churns. The crew skims off slag, oxides and impurities floating to the top. They add alloying elements, manganese, nickel, aluminum, for strength and corrosion resistance. They pull a sample of the melt, analyze the composition. When everything's ready, they start the pour. The furnace tilts with a special mechanism. Molten metal flows into a massive ladle suspended from an overhead crane. The ladle holds 140 tons. This is the most critical operation. The metal has to be uniform in composition and temperature. The crane moves the ladle toward the mold. The metal glows a blinding white, so bright you can't look at it without dark glasses. The temperature around it climbs to 140 degrees, even though the ladle's 30 feet away. Workers in silvery heat-resistant suits control the pour. They open the ladle gate. Molten metal flows into the gating system, first as a thin stream to preheat the channels. Then the flow gets stronger. The metal fills the mold from bottom to top, pushing air out through special ventilation channels. The pouring process takes about an hour. 300,000 pounds of liquid metal transfer from ladle to mold. When the mold is full, they close the ladle gate. The metal surface in the mold forms a crust of oxides. They dust it with a special powder that creates a protective layer. Now the waiting begins. The metal has to cool and solidify. But at this size, that's not quick. 260,000 pounds of bronze or steel cool slowly, very slowly.
Two weeks, 14 days the mold sits untouched. Inside, crystallization slowly occurs. Molten metal transforms into solid. Temperature drops at a rate of a few degrees per hour. Cooling too fast leads to cracks from uneven shrinkage. Too slow, large metal grains form, reducing strength. Engineers monitor the process with thermocouples, temperature sensors embedded in the mold. After 2 weeks, they break open the mold. A crane lifts the flask, opens it up. The molding sand pours away, revealing the casting. Before their eyes, a giant propeller, covered in black scale. Weighs 150 tons, 20 tons more than the finished product. Excess metal has solidified in the gates, risers, and allowances. The propeller moves to a special stand. Machining begins, transforming the rough casting into a perfect ship's propeller. And that's another 3 weeks of work. First, they cut off the sprues and risers, solidified metal feed channels. They use gas torches and heavy-duty bandsaws. The cut-off chunks weigh several tons each. They'll go back to the melt shop too. Then rough machining begins on turning and milling machines. These are giant machines, a bed 20 meters long, a milling head weighing 10 tons. The propeller is clamped on a rotating table. Cutters remove the stock, excess metal left for machining. Chips fly off in spirals as thick as a finger. Tons of metal are removed per shift. They mill the hub, the central part of the propeller that fits onto the shaft. A hole about 3 to 5 feet in diameter has to be perfectly round and concentric, precision, tenths of a millimeter. Then they machine the blades. Each blade is milled to a complex profile, leading edge, trailing edge, face, back. The profile changes from root to tip. It's a three-dimensional, doubly curved surface. The machine runs on computer control from a program based on design data.
After roughing comes finishing. Fine-toothed cutters pass over the blade surfaces, removing fractions of a millimeter. The surface becomes smooth. Then polishing. Abrasive wheels buff the blades to a shine. This is critically important. Surface roughness increases water resistance and promotes cavitation. A perfect surface cuts a ship's fuel consumption by percentage points. For a supertanker, that's millions of dollars in savings per year. After machining, the propeller is weighed and balanced. The center of mass must lie exactly on the rotation axis. Otherwise, vibrations will develop during operation, destroying bearings and potentially damaging the ship's hull. Balancing is done by drilling small cavities in specific locations. The final operation, non-destructive testing. The propeller is X-rayed, checked with ultrasound, examined using magnetic particle inspection. They're looking for internal defects, voids, cracks, inclusions. If they find a critical defect, the propeller is scrapped. 287,000 pounds of metal and a month of work go to waste. The cost of such a propeller, $1 to $3 million.
And just like that, making the journey from a wooden model through the hellish heat of 1600 degrees and 140 tons of molten metal, through 2 weeks of cooling and 3 weeks of machining on giant lathes, a propeller is born.
the heart of a supertanker, the pulse of an ocean giant. A solid piece of metal the size of a house, weighing 130 tons, capable of transmitting 100,000 horsepower. It's a triumph of engineering brilliance and metallurgical mastery. Every time you spot a container ship on the horizon or an oil tanker in port, know this: beneath the water spins a titan, born in fire and honed to perfection. A monolith of bronze or steel, every square inch of which withstands tons of pressure. A propeller that drives forward half the world's trade. 90% of all cargo moves by sea. This is a story about giants created by humans, about how humanity learned to cast metal the size of a house and machine it with precision down to a millimeter. A propeller isn't just a chunk of metal. It's a symbol of man's dominion over the oceans, a symbol of the technology that connected continents. From wooden model to steel reality, a journey spanning 5 weeks and millions of dollars. A journey repeated hundreds of times a year in foundries across the world, so the planet's fleet keeps pushing forward.
A plane that looks like a whale flies through European skies. It doesn't carry passengers, it carries other planes. Wings 100 feet long, fuselage sections as tall as a house. This is the Airbus Beluga XL, Europe's biggest cargo plane. 112 tons of freight, a cargo hold 29 feet across. Inside, it can fit 2 Airbus A380 wings at once. Without the Beluga, Airbus production would stop in a week. Today, we'll see how this giant is born, from an aluminum sheet to the first roar of its turbines. The Beluga XL is a puzzle made from parts created at 5 points across Europe. The base, an Airbus A330. Its lower fuselage, wings, and landing gear are assembled in Toulouse. But the nose section? That's made by Stelia at their plant in Mayotte, France. 40 feet long, 18 tons. Inside, the cockpit, avionics, hydraulics. All on a plug-and-fly principle. Panels from aluminum alloy 2024 with copper and magnesium are formed on presses capable of 1,300 tons of force. The frame is assembled from bulkheads and stringers, then the skin is riveted on top. 12,000 rivets, each about 1/6 of an inch in diameter for a single nose. The upper expanded fuselage, the heart of the Beluga, is produced by Premium Aerotech and De Hard. 3 sections, 2 side panels and a roof. 29 feet in diameter, nearly 6 feet wider than the previous Beluga. Sheet thickness ranges from 1/10 to 1/4 inch. Each panel is reinforced with 30 stringers. Bulkheads are placed every 20 inches. Everything's riveted and bolted with titanium bolts, torqued to 90 foot-pounds. The cargo door, an engineering marvel. Stelia Rochefort, France. 33 feet long, 26 feet high. Area nearly 1,500 square feet, like a basketball court standing vertical. Weight 3.1 tons. Frame made from titanium alloy, Ti6Al4V. Titanium handles the loads. 24 latches hold the door, 12 on each side. Each latch clamps down with 3 tons of force. The door opens with 4 hydraulic cylinders, piston diameter 4.7 inches, pressure 4,000 psi. 3 minutes to open, 4 to close. Inside the door, hundreds of yards of wiring and hydraulic lines. They shipped the door from Rochefort to Toulouse on a barge, the same one that carried A380 sections. By sea to Bordeaux, by river to Langon, then 125 miles by road. The tail section, modified by Spain's Aeronova in the Basque Country. The vertical stabilizer increases by 50%, from 33 to 50 square feet. The massive bloated fuselage creates serious drag. You need stability. They add vertical end plates to the horizontal stabilizer, plus 2 ventral fins under the tail. 5 vertical surfaces total instead of 1. Everything's made from composites, carbon fiber, layers of carbon fabric soaked in epoxy resin, laid in a mold and into the autoclave. 360 degrees Fahrenheit, 100 pounds per square inch, 8 hours. The composite fin weighs 1,300 pounds instead of 2,000 aluminum. December 2016, Toulouse. Line L34, a hangar spanning 130,000 square feet. Final assembly of the first Beluga. Lower fuselage with wings from an A330 goes on the jig. From above, a 50-ton crane lowers the expanded upper fuselage. They mate the perimeter. Hundreds of bolted connections. They drill quarter-inch holes through both sections at once, tolerance plus or minus 0.04 of an inch. Bolts get torqued with computer-controlled wrenches. The joint sealed with polysulfide compound works from -76 to +250 Fahrenheit. They mount the nose section, tail, vertical stabilizer. 3 months of work. Meanwhile, the guts. 50 miles of wiring in bundles of 50 to 100. 2,000 feet of stainless hydraulic lines. Pressure 4,000 pounds per square inch. 12 fuel tanks. 37,000 gallons of kerosene. March 2018. Engine installation. 2 Rolls-Royce Trent 700s. Each one weighs 12.3 tons. Thrust? 320 kilonewtons. 72,000 pounds of force. Fan diameter? 9 feet. 24 composite blades with titanium leading edges. The engine mounts to the wing through a titanium pylon with 4 bolts, each 1.9 inches in diameter. Torque? 2,950 pound-feet. 37 connections to each engine. Fuel, electrical, hydraulic, pneumatic. April through June, ground testing. 200,000 checkpoint inspections. Every sensor checked, every actuator verified. Flight control checks. Elevators deflect 25 degrees up, 15 down. Ailerons, 25 up, 15 down. Laser sensors monitoring. Accuracy to within 0.5 degrees. July 19, 2018. Blagnac, Toulouse. First flight, crew of 6, 150 sensors recording 200 parameters 1,000 times per second. Takeoff thrust 96%. Turbine exit temperature 2,700 degrees. Fuel burn 12 tons per hour. 120 knots, 222 kilometers per hour. Nose wheel liftoff. 140 knots, main gear liftoff. Climb rate 1,000 feet per minute. Flight level 350, 35,000 feet. Cruise speed 0.69 Mach, 466 miles per hour. 4 hours, 20 minutes airborne. Landing nominal. Next up, flight test program. 200 flights, 700 hours. Maximum weight with ballast, 51 tons. Single engine flight. Crosswind landing at 30 knots. -22 in Sweden, plus 113 in Spain. Everything works. November 13th, 2019. Type certificate. The Beluga cleared for flight. January 9th, 2020. First commercial flight. Toulouse, Bremen, Toulouse. Cargo? 2 A350 wings, each 105 feet long, 21,000 pounds. Before, 2 flights with the old Beluga. Now, 1. Loading 70 minutes. Wings roll in on a trolley along floor tracks. 24 tie-down points with straps. Flight 1 hour 40 minutes. In Bremen, they unload the wings, load A320 fuselage sections, fly to Toulouse. 3 to 4 flights a day, 6 days a week. 1,000 flights a year across 6 aircraft. Without the Beluga, Airbus wouldn't build a single plane. Wings made in Great Britain, tails in Spain, fuselages in Germany, final assembly in Toulouse and Hamburg. The Beluga, a flying assembly line. Europe's industrial artery. 1 billion euros program cost, 167 million per aircraft, 30 years of service, 60,000 flight hours. If this was interesting, hit like. Did you know about the Beluga? Write in the comments. Subscribe. Here we show you factories you never knew existed.
Every second, the world transmits over 3 billion gigabytes of data. But do you know that all of this is thanks to a thread thinner than a human hair? And that this thread begins with ordinary sand? Not beach sand, but perfectly pure quartz, where there's only 1 impurity particle per million particles. To create fiber optic cable that carries light at speeds exceeding 300,000 kilometers per second, you need to journey through chemical vapors, sterile laboratories, a furnace at 2,500 degrees, and lasers that monitor every microcrack. This process looks more like manufacturing a spacecraft than a cable, but it's precisely this that forms the foundation of the internet you're using right now. To create a thread capable of transmitting light at speeds approaching 300,000 kilometers per second, you must begin with sand. But not just any sand, only special, exceptionally pure quartz sand, where the primary substance is silicon dioxide. For fiber optic production, sand with a silica content exceeding 99.9% is used, which means that in 1 million particles, only 1 particle is an impurity. Just imagine, in every kilogram of raw material, no more than a few milligrams of impurities. And this is critically important, because even a tiny particle of foreign metal can cause light scattering or absorption. And then a signal that should have traveled nearly 100 kilometers without amplification simply vanishes. Raw material for fiber optics isn't simply washed or filtered, it's purified at the molecular level. Manufacturers often employ gas chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and precipitated as the purest vapor. And only then is it converted back into glass. Add to this strict temperature control, humidity, and airflow in clean rooms, and you'll get an idea of how far removed this is from an ordinary sandy beach. Production laboratories resemble NASA's sterile zones more than a glass workshop. And all of this to ensure that every meter of future fiber contains not a single defect. A large transparent glass cylinder, which will later be melted and drawn into an extremely thin thread, is the fiber optic preform. This enormous glass blank is made using a method called vapor deposition. In a large furnace, air is mixed with extremely pure gases. These vapors reach the inner surface of a transparent tube that's heated intensely. When the vapors touch the hot wall, they settle and transform into tiny glass droplets, like dew collecting on a leaf in the morning. Gradually, these droplets accumulate layer by layer until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it closes into a dense solid rod. This is our preform. The preform is placed in a special furnace where the temperature reaches approximately 2,600 degrees Celsius. This temperature is so high that the glass becomes soft and begins to melt, like caramel on a hob. When the preform's end melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and from it forms the finest thread. This thread, the optical fiber, is drawn at speeds of roughly 300 meters per minute. Imagine, that's faster than a cyclist moving through the city. It's important that the thread has the same thickness along its entire length. Optical fiber thickness is typically around 125 microns. This is very, very thin. For comparison, the average human hair has a thickness of around 100 microns. To keep this diameter under control, special instruments are positioned in the process. They monitor the thread in real time and measure its thickness. If the thread begins to become thicker or thinner, the system automatically changes the drawing speed or furnace temperature to correct it. After the optical fiber has been drawn and has become a thin, transparent thread, it needs protection. The fiber is extremely thin and fragile. Therefore, immediately after drawing, it's coated with a special protective layer. The thin thread is drawn from the furnace. After the furnace, it immediately enters a coating machine, a special device that dresses the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. This resembles a small tube or nozzle, inside which sits molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly poured onto it. This coating layer typically consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks. The secondary coating is harder and stronger, protecting from external influences, dust, and scratches. After applying the liquid coating, the fiber passes through special forming rollers. They regulate the layer's thickness and evenness. After the polymer has been applied and formed, the fiber passes through an ultraviolet light zone. Here, under UV lamp influence, the polymer instantly hardens. This process is called polymerization. Those of you who get manicures know how this works. Ultraviolet lamps activate chemical reactions in the polymer. Thanks to this, the coating quickly becomes hard whilst maintaining its elasticity. This is an extremely rapid process. The coating hardens literally in fractions of a second. This method doesn't heat the fiber so it doesn't damage it. The entire machine is equipped with sensors and control systems. They constantly measure coating thickness and fiber feed speed. At the end of all this technological wizardry sits a spool module, rotating with a hum resembling a jet engine sound in miniature. The fiber, resembling transparent silk, lays evenly and precisely coil against coil. The spool moves smoothly left and right with millimeter precision. Around it are sensors, lasers, cameras. They vigilantly monitor that the fiber lays evenly and doesn't twist. With every minute, more and more layers appear on the spool. Imagine, in just a few hours, there are already several kilometers of the finest, almost invisible fiber. And all of this without a single break, without a single scratch. Before assembly into cable begins, fiber from the spool is carefully rewound onto the production line. Since one cable typically contains several fibers, individual threads are combined into ribbons or modules. These ribbons or bundles are then placed into buffer tubes. These are thin, flexible plastic channels that provide the fiber space for micro-movements. This is important because when temperature changes or the cable bends, the fiber slightly expands or contracts. Inside these tubes, gel may also be added that repels water and absorbs vibrations. Around the buffer tubes, reinforcing elements are added. Fiberglass or Kevlar. These are extremely strong threads that protect the cable from stretching. Metal wire is needed for additional mechanical strength. The central rod is a rigid element at the center that maintains the cable's shape. All of this is wrapped with an outer sheath. This is a dense plastic or polyethylene tube resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. Each fiber's transmission capacity is checked, along with bending strength and moisture resistance. Then it's wound onto large drums, marked, technical documents are added, and it's ready for transport and installation.
Today we're at a facility they don't exactly advertise, but one the modern world can't live without. I'm standing in front of a massive complex where they produce TNT, that explosive material that blasts through rocks and quarries, sends rockets into the sky, and, when necessary, strikes back at the enemy. Everything here smells like chemicals, metal, and that industrial power that sends shivers down your spine. The territory stretches hundreds of yards in every direction. Concrete walls, pipes, tanks, and above it all, a low but constant hum of reactors. Let's walk through together. I just got my access pass, and we're heading into the production floor. Hold on tight, it's gonna get intense. TNT, or trinitrotoluene, showed up back in the 19th century when chemists started experimenting with toluene, a colorless liquid you get from coal or petroleum. 166 years ago, a German chemist named Julius Wilbrand heated toluene with a mix of acids and got a yellow crystal that detonates with monstrous force. Since then, TNT became the king of explosives, stable, powerful, won't blow up from impact or fire, only from a detonator. You can drop it, heat it, shoot it with a rifle, and nothing happens until a blasting cap goes off. That predictability is what made it indispensable. 1 gram of TNT, that's the benchmark unit for measuring explosive force, the standard all other substances get compared to. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant vessels made of stainless chromium molybdenum steel, because regular steel gets eaten away by acids in a matter of weeks. They pump in a mixture of nitric and sulfuric acids, concentrates that'll melt right through gloves. The reactor temperature is kept around 195 to 212 degrees Fahrenheit. Hot enough to keep the reaction going, but not so hot that it spins out of control. The nitration process happens in stages, taking anywhere from several hours to several days. First, you get mononitrotoluene, then dinitrotoluene, and finally trinitrotoluene, TNT itself. At each stage, another nitro group latches onto the toluene molecule, and with every step, the stuff gets more and more explosive. The acids circulate in a closed loop because they're regenerated and reused, not just dumped into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything stays locked down because the slightest slip and the reaction could go sideways. From the reactor, the mixture flows into coolers, long coiled tubes where the hot TNT crystallizes. Then it's into settling tanks. The heavy TNT sinks to the bottom while the lighter acids get skimmed off. What you're left with is a jelly-like mass, crude TNT, still damp with acid.
It gets washed with hot water at around 160 to 175 degrees Fahrenheit to neutralize what's left. The water changes 3 times. The first run comes out yellow with acid, the second is cloudy, and the third is clean as a tear. The spent water doesn't just get dumped. It's neutralized with lime and holding pools, filtered through a sand layer about 10 feet thick, and only then sent to treatment facilities. Ecology stays under control because acid is poison to anything living. Meanwhile, the crystals get unloaded. The mass is already solid, but still 6 to 10% damp. Now comes drying, one of the most fascinating stages. The vacuum drying chamber, a room where rotor drums hum, each about 6.5 feet in diameter. TNT gets loaded in batches of 200 pounds. They seal the drum, pump the air down to a pressure around 4 inches of mercury, and fire up the heat to 130 to 140 Fahrenheit. Fans push warm air around inside. The drum rotates, crystals tumble, dry evenly, no sticking to the walls. 2 hours, and out comes pure yellow powder at 0.5% moisture. Skip this step, and TNT would clump together or go unstable from the dampness. The powder color ranges from light yellow to deep orange, depending on purity. Here, they're producing top-grade stuff, 98% pure. Next up, granulation. They moisten the powder, press it into matchbox-sized bricks under about 3,000 pounds per square inch. These bricks come out hard as rock. Then they crush them in hammer mills, where shafts spin at 6,000 revolutions per minute, turning the bricks into granules between 1 and 3 millimeters in diameter. Why granules? Because they're easier to pack, don't create dust, and detonate uniformly. The dust gets sucked out by ventilation because breathing in TNT is bad news. The granules get poured into sealed crates holding 100 pounds each. That's the standard for quarries and the military. Every crate gets checked for moisture, no more than 0.7%. Otherwise, the TNT starts to sweat and becomes sensitive. There are special molds for underwater charges too. The pellets get mixed with paraffin so they don't get wet. The crates are sealed, labeled by batch, and sent to storage. From here, the TNT heads out to quarries, mines, military bases. One crate is enough to blast through 200 tons of rock. Now, about safety, because without it, they wouldn't last a day here. The plant is divided into zones. Reactors sit inside concrete shelters at safe distances from each other, with anti-detonation barriers between them, about 50 feet high, made of reinforced concrete. The logic is simple. If one reactor blows, the barrier absorbs the shock wave and keeps the detonation from jumping to the next one. No open flames, no sparks. They even hand over their cell phones at the entrance. All electrical equipment is explosion-proof, lights sealed in airtight housings. Personnel wear anti-static clothing, shoes with conductive soles so static doesn't throw a spark. Every 5 minutes, sensor checks for gas leaks. Emergency showers and CO2 fire extinguishers everywhere. Were there incidents? In the 19th century, explosions wiped out entire factories, but now, 0 accidents in the last 10 years. Why? Because of automation. Computers shut down the reactor in seconds at the slightest anomaly. One operator at a console monitors 10 processes simultaneously. Compare that to the old factories. Back then, everything was done by hand. TNT was packed with bare hands. Explosions happened regularly. Now, robotic manipulators, sensors, cameras. Evolution. Let's look inside the lab. This is where they test every batch. A sample gets placed in a bomb chamber, a thick-walled steel cylinder. They detonate a milligram and measure the detonation velocity, around 22,600 feet per second. If the velocity is below spec, that means there are impurities in the batch, or the crystal structure is compromised. Then they check stability. Heat it to 200 degrees Fahrenheit, drop it from 10 feet, it shouldn't crack or detonate. Then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, you're good. Lab techs check purity with a chromatograph. Toluene or acid traces, not allowed. Production here is massive, 1,000 tons per month. Power comes from their own gas turbines and steam boilers. Waste? They regenerate the acids, redistill the toluene, send it back into the cycle. Filters on smokestacks 200 feet tall. Wastewater cleaned until it's crystal clear. Nearest town is 10 miles out, so no complaints from the neighbors. Interesting fact, TNT isn't just for blowing things up. Melt it at 180 degrees Fahrenheit, it turns liquid like hot wax, and pour it into shell casings. Or mix it with other compounds for plastic charges. In quarries, 1 ton shatters a boulder the size of a 3-story house. In mining, you can't drill a mile-long tunnel without it. In the military, it's the backbone of torpedoes, mines, and aerial bombs. I'm standing in the granulation shop right now, hearing the press rumbling, watching granules pour into bins like golden sand. The air's clean, but there's that distinct chemical smell, a familiar scent to anyone who's been inside plants like this. Discipline here is ironclad. 8-hour shifts, every action by the book, every step under camera. The people here are like jewelers, except they're not working with gold. They're working with explosives. The factory's like a living organism, roaring, spinning, producing power. TNT isn't evil. It's a tool. It builds roads, digs mines, defends the nation. Without it, there'd be no 1,000-foot bridges, no tunnels carved through mountain ranges. From the yellow crystal discovered a century and a half ago to today's high-precision production with robots and computers, it's been a massive journey. But the essence remains the same, turning chemistry into controlled force.
Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems, known as Christmas trees, that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world. Every year in the world, only 21 mysterious B-2 Spirit aircraft are created, genuine ghosts of the sky. Its length is almost that of a multi-story building, whilst its wingspan is greater than a football pitch. But the main intrigue lies in the materials. Composites, titanium, and aluminum alloys make it lightweight, yet incredibly strong and almost invisible to radars. Radio waves become lost in the layers. Paint absorbs signals, and engines hide their thermal signature like a shadow in the night sky. This isn't simply an aircraft, it's an engineering myth about which legends have circulated for decades. Watch until the end, and you'll learn a secret not shown even in military archives. Everything begins with material selection, and here the B-2 Spirit is truly extraordinary. For its body, they don't use ordinary metal as in old aircraft, but take composites, titanium, and aluminum alloys. Composites are multi-layered sandwiches of fibers and resins that are lighter than steel yet significantly stronger. It's precisely thanks to these materials that the aircraft not only withstands colossal loads, but also remains almost invisible to radars. Radio waves simply become lost in the composite layers without reflecting back. Imagine, the B-2's length is almost 69 feet, whilst its wingspan exceeds 171 feet. It's like a football pitch, only instead of grass, there's black stealth gliding across the sky. The empty weight of the B-2 is over 71 tons, whilst maximum takeoff mass reaches 171,000 kilograms. But even with such dimensions, it appears elegant because its shape is pure aerodynamics. No superfluous protrusions, everything smooth as in nature. Every detail is manufactured with jeweler's precision. Titanium and aluminum are used where special strength is needed, for instance in engine mounting points or undercarriage. And composites cover nearly the entire surface. They're responsible for stealth and lightness. Incidentally, special body coating not only absorbs radio waves, but protects the aircraft from extreme temperatures at altitudes exceeding 50,000 feet. Next follows multi-stage processing, grinding, quality control, application of special layers. Every millimeter is checked with laser scanners, so there's not a crack nor the slightest gap. Here, everything is at high technology level. Robots and people work together, creating a genuine work of engineering art. It's precisely thanks to these materials and technologies that the B-2 Spirit can fly thousands of miles, remaining invisible both to radars and thermal imagers. In the B-2 Spirit, nothing is accidental. Every curve of the fuselage, every wing line is the result of thousands of hours of calculations and tests. Engineers literally draw the aircraft in air so that it doesn't simply fly, but merges with the sky. It's precisely thanks to this shape that the B-2 looks so futuristic. It's as though created not to challenge the air, but to become part of it. Every detail, even the slightest protrusion, is calculated on supercomputers. Imagine, even rivets and joints on the body are hidden so as not to create unnecessary reflections for radars. And there's also a secret weapon here: special paint. This isn't simply a black matte layer, but a multi-component coating that absorbs radio waves and doesn't allow them to reflect back. That's precisely why even powerful radars see the B-2 as a tiny dot or don't notice it at all in the sky. Assembly of the B-2 Spirit is a genuine engineering performance that occurs in enormous workshops accessible only to chosen few. Here reigns an atmosphere of maximum secrecy. People and robots work together like a single team. Robots lift and hold massive sections whilst engineers manually install the tiniest details. The aircraft body is assembled piece by piece like a gigantic three-dimensional puzzle, where every element must fit perfectly in its place. All joints are checked with lasers. This looks like a scene from a science fiction film. Enormous cranes, laser scanners, people in special clothing, robots moving with incredible precision. Every day in these workshops is another step towards creating an aircraft that changes the rules of the game in the aviation world. Next, engines enter the stage, the genuine heart of the B-2 Spirit. Designers hide engines inside the body rather than placing them outside as in most aircraft. Thanks to such integration, the B-2 appears maximally smooth, and this also helps hide thermal traces. The whole trick is in the exhausts. Hot gases that are usually clearly visible to infrared sensors here pass through special long channels. In these channels, gases cool, mix with cold air, and only afterwards exit outside. Therefore, even modern thermal imagers see the B-2 as a barely noticeable shadow in the sky. The aircraft cockpit is isolated, protected from noise and light, comfortable even during many-hour flights. Next, onto this foundation are applied layers of insulation so that inside it's always quiet and comfortable even if engines roar outside. The feeling is as though you're in a capsule that screens you from the entire world. Now, in the cockpit center are installed two seats. They stand side by side like in a modern sports car. Seats are soft but strong with numerous adjustments. Before is an enormous digital screen. All controls are to hand. Touchscreen panels, joysticks, buttons with different textures so they're easy to find even by touch. Around are panels with instruments. They don't protrude but smoothly transition one into another like waves. A folding rest area, a folding bed, space for food, even a small toilet. This is space where one can relax whilst one's partner holds the controls. Everything is made so that crew can remain focused and not tire even during flights lasting over a day. When the cockpit is ready, it's covered with special coating that protects from temperature fluctuations, from bitter frosts to heat. All joints are sealed so there's not a single draft or extraneous noise.
Have you ever seen what molten bronze looks like? I have. It's golden, almost like the sun, and flows slower than water, thick, heavy, with this inner weightiness to it. And when 70 tons of this metal get poured into a single mold all at once, it's a sight you can't look away from. Today we're at a factory that makes propellers for military ships. This is one of those places they don't run tours through and almost never film inside. And I'm going to show you the entire journey from molten bronze to a polished giant that will silently push thousands of tons of steel through the ocean. Let's start with a question I asked myself when I got here. Why bronze? A warship is a steel machine. Steel hull, steel superstructure, steel weapons. So why make the propeller from a different material? The answer is simple yet profound. Steel rusts in seawater. The propeller is constantly submerged, constantly spinning,
constantly in contact with an aggressive environment. A steel propeller would turn into a rusty hedgehog in just a few years, one that can't do its job anymore. That's why they use nickel aluminum bronze here, an alloy that sailors and metallurgists call nibral for short. Nibral is a mix of copper, aluminum, nickel, and iron in precisely calibrated proportions. Copper provides the base and corrosion resistance. Aluminum strengthens the alloy and reduces weight. Nickel adds hardness and erosion resistance, and iron refines the grain structure, making the metal uniform. Every element here is deliberate, the result of decades of research and real-world testing.
Nibral doesn't rust, resists erosion incredibly well, and has enough strength to handle the loads from spinning at full speed underwater. Now, about scale. A propeller for a destroyer or nuclear submarine, this isn't something you can pick up with your hands. The diameter of such a propeller reaches 20 feet or more, and each blade is comparable in size to a small car. The weight of the finished product, dozens of tons. And it all starts with 70 tons of liquid bronze that needs to be poured into a single mold in one continuous process. 70 tons. That's roughly the weight of 12 fully loaded pickup trucks. And all this massive metal at a temperature of around 2,000 degrees Fahrenheit has to get into the mold evenly, no pauses, no stops. The metal is melted in large induction or arc furnaces. Depending on the plant's configuration, there might be several of these furnaces, and they run in parallel to accumulate the necessary volume of molten metal by the time of pouring. When the metal hits the right temperature, lab techs take a sample, a small portion of the melt, and send it for rapid chemical analysis. If the element ratios check out, they greenlight the pour. If something's off, they adjust it right there in the furnace, adding whatever element is needed, then take another sample. The pour happens from a big ladle suspended from an overhead crane. They tilt the ladle, and metal starts flowing into the gating system of the mold. It looks like this, a thick golden stream with bright glow and a cloud of steam rising up. The air shimmers from the heat, and 30 feet away you can feel the hot wave hit your face. The foundry workers stand off to the side in protective suits and shields. Even several yards out, the heat hits your whole body. They control pour temperature by adjusting the ladle tilt. Too fast, and the metal churns turbulently in the mold, trapping air and creating voids. Too slow, and the first portion starts solidifying before the mold fills, leaving internal seams in the casting. So the pace stays steady, continuous, dialed in by experience. When the mold is complete, they leave what's called a riser at the top, an extra reservoir of metal that feeds the casting as it shrinks during cooling. Without it, shrinkage cavities form inside the propeller, voids that would render the blade useless. The riser gets cut off later, but during the pour, it's a critical part of the process. The mold for a propeller is a massive structure that takes up a significant portion of the foundry floor. It's assembled over weeks from special molding sand reinforced with binding resins. Each blade has its own complex geometry, twisted, uneven, with a precisely calculated profile. This geometry is built into the sand mold with high precision. The raw casting already needs to be very close to the final part. Worth noting separately are the cores. Cavities are designed inside the blades to reduce weight without sacrificing strength. To form them, sand cores are mounted in the mold on metal supports called chaplets. During the pour, the chaplets fuse with the base metal and become part of it, while the cores are later knocked out of the finished casting. Sounds simple, but in practice, it's precision work, carefully controlling the position of every rod. If a rod shifts under the weight of molten metal during the pour, the blade wall comes out uneven. An uneven wall means imbalance. Imbalance on a submarine propeller means vibration. Vibration means noise.
And noise underwater? That's a death sentence for a sub, because enemy hydrophones will pick it up. This brings us to the main theme of this facility: silence. A warship, and especially a submarine, must be as quiet as possible. The propeller is the primary source of underwater noise. There are two mechanisms: mechanical noise from imbalance and vibration, and cavitation noise. Cavitation is a phenomenon where microscopic vapor bubbles form on the blade surface due to pressure differences, then collapse with a distinctive crackle. Each pop is a micro-impact that, over time, destroys even bronze, leaving small pits on the surface. But the main problem isn't wear, it's sound. That crackling travels brilliantly through water and is easily detected by sonar systems. That's why blade surfaces must be perfect: no roughness, no waviness, no deviations from the calculated profile.
That's exactly why there's a 5-axis CNC milling machine standing here. If you've never seen one of these machines, picture something between an industrial robot and a building. The work envelope can handle parts up to 20 feet in diameter. The spindle and cutter move simultaneously along 5 axes, 3 linear and 2 rotational. This lets the tool approach any point on a complexly twisted blade at exactly the right angle and remove metal with micron-level precision. The price tag on one of these machines? A small fortune. But without it, achieving the required surface quality on parts this size is simply impossible. Machining a single propeller takes several weeks. Weeks, not hours. The machine strips away chips continuously, layer by layer, closing in on the final profile. Bronze shavings curl into golden spirals and drop into the catch pan, while beneath the cutter emerges a surface smooth as glass. Operators regularly pause the process to measure blade geometry using specialized probes and laser scanners. Any deviation from the theoretical profile? The program gets adjusted. The goal is to achieve a surface that matches the blueprint to within hundredths of a millimeter on a part that's 20 feet across. That's like drawing a perfect room-size circle without deviating from the line by more than the thickness of a sheet of paper. After machining comes balancing. The propeller gets mounted on a balancing stand and spun. Sensors detect exactly where the imbalance is and how much. Technicians manually remove metal from specific spots, literally just a few grams at a time, until the propeller reaches the required balance level. The process is painstaking. Shave off a tiny bit, measure. Shave again, measure again. Over and over until the sensors show it's within spec. On a civilian ship, this level of precision would be considered excellent. On a military vessel, it's the minimum acceptable standard. The final inspection includes complete measurement of every blade, surface roughness checks, and verification of the metal's chemical composition using samples taken during the melt. Each propeller gets a full documentation package, from the melt's chemical analysis to balancing protocols and laser surface scanning reports. This isn't just paperwork. It's a legal and technical passport for a product that'll go on a warship and serve for decades under the harshest operating conditions. I stood next to a finished propeller before shipping, trying to wrap my head around the fact that I was looking at something that had gone from liquid bronze to this golden, polished giant in just a few months, through the work of dozens of people and one very large machine. Somewhere out in the ocean, this propeller will spin in complete darkness, pushing thousands of tons of steel forward. And it'll do it silently. Because that's exactly what it was built to do. Your smartphone would weigh over 2 pounds and be an inch thick. A can of Coke would cost $5. A Boeing 747 couldn't cross the Atlantic. It'd run out of fuel halfway. And half the stuff in your house simply wouldn't exist. All because of one metal that humans didn't discover until 1828 and couldn't mass produce until 1886. Before that, the world ran on iron, steel, copper, and bronze, metals too heavy, too expensive, or too weak for modern life. Today, we're heading inside an aluminum plant, and I'll show you what properties emerge at each stage.
This aluminum plant sits right on the riverbank. That's no accident. It's been running non-stop for over 120 years. It's here because it has direct access to massive hydroelectric power. That's critical because making aluminum takes more electricity than almost any other industrial process on Earth. Walk onto the grounds and the first thing you feel, a low hum from the transformers. The smell of superheated metal hangs in the air constantly. The plant never stops, not for a minute. The raw material is bauxite, a reddish-brown powder that arrives on ships from tropical countries, Jamaica, Australia, Guinea. If aluminum had never been discovered, we'd still be mining iron ore for everything. Steel production needs coal. It gives off massive emissions. Aluminum here, it runs on clean hydropower. Without aluminum, global carbon emissions would be roughly 15% higher from metal production alone. The first stage is processing bauxite through the Bayer process. The ore is crushed and mixed with caustic soda, then heated to 347 degrees Fahrenheit under pressure in autoclaves. Under these conditions, aluminum oxide dissolves while iron and silicon remain as red mud, a thick, bright, rust-colored mass that's diverted to special storage facilities. The output? Pure white aluminum oxide powder, also known as alumina. To produce 1 ton of alumina, you need to process about 2 tons of bauxite. This is where aluminum's first critical property is established: incredible corrosion resistance. In air, aluminum instantly forms an ultra-thin oxide film that locks the metal into protection against further oxidation. If we use steel, every outdoor structure would need constant repainting. Steel ships require dry dock and repainting every few years. Aluminum boats serve for decades without maintenance. Without this property, coastal cities would burn billions on infrastructure upkeep. The alumina is moved to the electrolysis hall, and this place is impressive. A massive room with rows of reduction cells radiating waves of heat. These are glowing rectangular pools about 15 feet long, filled with molten cryolite at a temperature of around 1700 degrees Fahrenheit. The surface of the cells flickers orange, and the air shimmers from the heat. The alumina dissolves in this bath. Then, a current of 150,000 amps is run through each cell, enough electricity to power 15,000 homes. The current rips aluminum atoms away from oxygen atoms. Pure molten aluminum sinks to the bottom. Oxygen rises to the top. This is the Hall-Héroult process, invented in 1886, and it's still the only economically viable way to produce aluminum. Before it, aluminum cost more than gold. Napoleon III used aluminum plates for his most important guests, while everyone else ate from gold ones. Without the Hall-Héroult process, aluminum would cost hundreds of dollars per pound today, and a can of soda would set you back a fortune. After a full day of operation, the molten aluminum gets pumped out and poured into crucibles, 10 tons each. The liquid metal glows with a soft, silvery light, nothing like orange cast iron or golden bronze. This shimmering metal demonstrates aluminum's most critical property, strength-to-weight ratio. Aluminum's 3 times lighter than steel, but with the right alloying, nearly as strong. A Boeing 747 made of steel would weigh 1,200 tons instead of 400. You'd need engines 3 times more powerful, burning 3 times more fuel. But carrying that extra fuel adds weight, which demands even more fuel. The tyranny of the rocket equation makes long-haul flights impossible. Without aluminum, commercial aviation as we know it doesn't exist. Short flights on steel planes? Possible. But New York to London would need 2 refueling stops, turning 8 hours into 20, while ticket prices would shoot up to several $1,000s. Molten aluminum gets poured into molds, forming ingots weighing several tons. Then they're reheated to 850 degrees Fahrenheit and pass through massive rolling mills. The rollers press down with thousands of tons of force, and with each pass, The ingot gets thinner and longer, transforming into sheets ranging from 0.02 of an inch to several inches thick. Rolling aligns the grain structure, locking in specific mechanical properties. Here's where another critical quality emerges: electrical conductivity. Aluminum conducts electricity 60% as well as copper, but weighs only 30% as much. Every high-voltage power line uses aluminum around a steel core. The aluminum conducts the current while the steel carries the load. If we had to use copper instead, the wires would be 3 times heavier, the support towers would need to be 3 times stronger, and spaced closer together. Building power grids would cost 4 times more. Rural electrification would never have happened, and your monthly electric bill would triple. Every sheet undergoes the strictest quality control, and there's a concrete reason for that. On April 28, 1988, Aloha Airlines Flight 243 was cruising at about 24,000 feet above Hawaii when passengers heard explosive decompression. The entire upper section of the forward fuselage tore away, exposing nearly 18 feet of skin and opening the cabin to the sky. One flight attendant was killed, 65 passengers injured. The investigation revealed that the aluminum fuselage had developed microscopic fatigue cracks after years of pressurization cycles. With every takeoff, the fuselage expands under pressure. With every landing, it contracts. Thousands of these cycles, and invisible defects appear in the metal. Tiny cracks grew and connected until the structure failed catastrophically. The aircraft had completed 89,000 flight cycles, and technicians couldn't detect such small defects. This tragedy completely transformed how the aerospace industry inspects aluminum. Today, every single sheet goes through eddy current testing, which detects surface cracks as small as 0.004 of an inch deep, ultrasonic testing that finds internal defects, and X-ray examination for critical components. Plus fatigue testing. Samples get bent millions of times, simulating decades of flight cycles to verify the alloy's reliability. The rejection rate for aerospace aluminum is 12%. Every 8th sheet fails inspection and gets sent back for remelting. That number seems high, but after the Aloha disaster, the industry decided, better to lose metal than lives. Aluminum that passes inspection goes to manufacturers, who turn it into everything, from aircraft to soda cans. A major plant produces around 300,000 tons annually. And virtually all that rejected metal doesn't go to waste. Aluminum can be remelted infinite times without losing its properties, and remelting takes just 5% of the energy needed for primary production. Without aluminum, cans would be made of tin-plated steel, weighing 3 times as much. A 12-pack of Coke, 24 pounds instead of 9. Shipping costs triple, prices double. Construction would look completely different. Modern curtain walls use aluminum frames, strong enough for glass but light enough that buildings don't need massive reinforcement. Without aluminum, tiny windows in thick walls, or steel frames so heavy that buildings over 50 stories become impractical. Modern glass skyscrapers don't exist. Computers and smartphones would be different too. That aluminum laptop body would have to be plastic or magnesium. Plastic isn't rigid enough and cracks. Magnesium is light but catches fire during machining. The plant's been running for over 120 years, producing roughly 20 million tons of aluminum, turned into planes, cars, buildings, power lines, packaging, and electronics. Without the electrolysis process running in those reduction cells, none of this exists. We'd be trapped in a world that's heavier, more expensive, and far more limited.
Every year, the world produces over 500 million tons of glass. Without it, there'd be no windows, smartphones, cars, or skyscrapers. But few people know that the journey to this perfect transparency doesn't start with glass at all. It starts with hot sand, heated in furnaces to temperatures exceeding 1,600 degrees Celsius. This isn't just manufacturing, it's modern-day alchemy. Millions of tons of sand transformed into an ocean of molten glass, floating on liquid tin to create a perfectly smooth surface. You're about to discover the secrets of this process right here. Before hot sand becomes a transparent window, it all begins in a quarry. The primary raw material for float glass is high-quality silica sand. It must be almost perfectly pure, with a silicon dioxide content exceeding 99.5%. This sand is extracted from special deposits, typically deep underground. One of the most prized is Ottawa sand from Illinois. Pale white, fine as flour, and exceptionally pure. Quarries operate like giant anthills. Excavators tear through layers of earth, whilst lorries, 40-tonners, haul the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones and the slightest impurities. Besides sand, glass contains several other components. Soda ash lowers the melting temperature. It's transported from salt deposits, particularly from Wyoming, in 23-kilogram bags or in bulk. Limestone stabilizes the structure. It's supplied from quarries and ground to a dust with particles under 1 millimeter in diameter. The mix also includes dolomite, aluminum oxide, saltpeter, and glass waste, what's called cullet. Cullet reduces the energy consumption for melting by up to 25%. After initial cleaning, all components are mixed in precise proportions, which are kept as trade secrets. A giant mixer the size of a 2-story house prepares the glass flour mixture. The finished mixture is transported to production by lorry and sometimes by rail or even on barges. Storage temperature must be controlled, no moisture whatsoever. The warehouse resembles a sterile grain elevator with silos, each with a capacity of roughly 560 cubic meters. The mixture is then automatically fed into the glass furnace, where within just minutes, everything that was sand and dust yesterday transforms into a boiling ocean of glass. The mixture enters the heart of production, the glass furnace. It's a genuine industrial volcano, over 60 meters long, with temperatures reaching 1,600 degrees Celsius at the melting core. Raw materials are fed in automatically, several tons per hour. In the first 9 to 12 meters of the furnace, melting occurs. Components melt and merge into a glowing, viscous mass. Next comes the homogenization zone. The mass is stirred and matures until all bubbles and lumps disappear. And only then does it gently flow onto metal. This is where the magic begins. In the second stage, the mass enters a bath of molten tin heated to 1,100 degrees. The glass literally floats on the metal, spreading into an even ribbon. Thanks to surface tension and the perfect flatness of the tin, a mirror-smooth surface forms on both sides, without polishing, without presses. Thickness is controlled by stretching, special rollers, or electromagnetic fields either stretch or compress the glass ribbon. This way, the output can be glass ranging from 1.5 to 19 millimeters thick. The tin bath spans over 45 meters, and the glass slowly floats along it at speeds up to 7.5 meters per minute, cooling en route to 540 degrees Celsius. This is an absolutely critical moment, but even at this stage, it's not ready yet. Next comes the annealing zone. The glass ribbon passes through a long tunnel where it cools by several degrees per minute to relieve all internal stresses. Without this, the glass could later crack on its own. Its surface is like ice, smooth without a single scratch. The sheet size is impressive, up to 3 meters wide and over 9 meters long. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, searching for micro cracks, inclusions, stress points. Any find means that sheet's rejected. Cutting isn't mechanical anymore. Now it's laser or roller scoring. A microblade, similar to diamond, scores a line, and then gentle pressure snaps the glass precisely along that path. Sometimes sheets are cut straight to order, say 60 by 90 centimeters for construction glass or screen size for Tesla. Others go in standard formats to warehouses, where they're stored vertically on racks with rubber spacers. After cutting comes the calibration stage. Sheets are checked for thickness, geometry, straight edges. High-definition cameras scan every centimeter. Lasers analyze the corners. There are almost no human hands here, only at the final stage when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency, marking is its name, passport, and craftsman's signature all in one. It's in the marking zone that each piece of glass is given its identity: where, when, by whom, and for what purpose it was created. The most common method is laser engraving. A special laser burns microscopic dots onto the surface, creating an indelible frosted inscription. Font thickness is less than 2.5 millimeters. This inscription can't be removed without damaging the glass, which is precisely why it's often used as an anti-tamper code. Sandblasting is used for decorative or premium glass. Through a stencil, abrasive is applied to the glass under pressure, forming a raised frosted mark. Then there's marking with ceramic inks. This method is used at the stage before tempering. Special paint is applied by printing, then baked at temperatures exceeding 1100 degrees. This marking is colored, noticeable, and extremely durable. It won't wash off, won't wear away, and won't fade. Marking can be either technical or branded. For instance, windows in luxury homes often proudly display the manufacturer's logo. In some projects, marking is even used for authenticity verification. For example, glass for armored vehicles or government buildings receives a serial number and QR code. The final stage is documentation. Every sheet gets a record in the system, like in a hospital. What sort of patient it is, when it was born, what properties it has, and where it's heading. This matters because glass isn't always dispatched immediately. Some batches are stored for months until their time comes.
Every year, hundreds of oil platforms get installed in the world's oceans. Each one weighs tens of thousands of tons, and at some point, all that weight hangs from a single hook. Not a cable, not a beam, but a hook. A piece of forged steel that looks like a giant fishing hook from another dimension. Around it, the North Sea, a storm, 30-foot waves, a crane swaying on the deck of a ship, and the hook holds. It holds 8,000 tons. That's roughly the weight of 8,000 cars lifted simultaneously above the water's surface. One invisible microcrack half a millimeter wide, and a structure worth billions of euros plunges to the bottom, along with everything attached to it. How do you forge a monster capable of holding 10,000 tons in the middle of a raging ocean from molten steel, at temperatures exceeding 4,000 degrees Fahrenheit? And what critical moment do manufacturers carefully hide from prying eyes? Watch until the end. The answer will surprise you. It all starts with choosing the metal. For giant crane hooks, they use special structural steel where the carbon content doesn't exceed 1%, while chromium additives up to 2% and molybdenum up to 0.5% deliver tensile strength exceeding 145,000 pounds per square inch. These elements aren't chosen randomly. Chromium provides corrosion resistance for marine conditions, and molybdenum prevents brittleness at low temperatures because a hook might operate in the North Sea, where in winter the water barely stays above freezing and the air gets even colder. The raw material arrives as briquettes or ingots weighing 44,000 pounds each. They're loaded into powerful electric arc furnaces with a 440,000-pound capacity. Giant vessels 30 feet tall with graphite electrodes 24 inches in diameter. Steel for these hooks comes primarily from Scandinavia, where it's melted in vacuum furnaces with special composition control at every stage. The logistics are impressive even before production begins. 44,000-pound ingots arrive by barge right to the factory docks. If you're curious how things are made that human lives depend on in the open ocean, subscribe to the channel right now and hit that bell so you don't miss the next episode. When a current of up to 100,000 amps flows between the electrodes and the metal, it creates an arc about 20 inches long that heats the furnace contents to over 3,600 degrees Fahrenheit. This isn't just hot, this is the temperature where steel stops being a solid and transforms into glowing liquid. The furnace slowly rotates for even mixing, while gases are drawn off through powerful filters. The melting process takes 4 to 5 hours, during which the metal is purified through vacuum evaporation and argon purging. The finished melt, a bright yellow color, is poured into ladles lined with fire brick. The temperature at discharge, around 3,000 degrees Fahrenheit. Cranes lift the ladle and transport it to the casting line, where prepared molds are already standing. Massive steel structures weighing up to 200 tons each. The mold geometry is calculated accounting for 2% metal shrinkage. If you don't build in this allowance, the finished blank will come out smaller than required. They pour at a 45-degree angle to avoid air pockets. A stream of liquid metal about 20 inches wide fills the mold in 10 to 15 minutes. Then they seal it with a lid and move it into a controlled cooling zone. And this is where one of the most critical stages of the entire process begins. For the first 24 hours, the temperature drops only to around 1,500 degrees Fahrenheit. The next 2 days, down to 400 degrees. Full cooling to room temperature takes up to a week. Sensors continuously monitor temperature gradients at a depth of 4 inches. The slightest variation can cause thermal stresses that lead to internal cracks, invisible from the outside. During cooling, the metal crystallizes, forming a coarse structure that's later optimized through heat treatment. Workers in protective suits monitor the process through viewing panels, while automated systems record thousands of parameters every minute. The finished blank weighs between 100 and 200 tons, stretches up to 40 feet long, and measures up to 6.5 feet in diameter at the base. Once the lengthy cooling period is complete, the workpiece is pulled from the mold, using cranes rated for 300 tons and transported to the forging shop, a massive facility covering 22,000 square feet with ceilings 80 feet high. Here stand hydraulic presses capable of exerting up to 50,000 tons of force. That's not a typo. 50,000 tons of pressure on a single point. For comparison, the Eiffel Tower weighs about 7,000 tons. These presses push 7 times harder. The workpiece is cut into sections 20 to 26 feet long and reheated in gas furnaces to 2,200 degrees Fahrenheit. The metal glows bright red and becomes malleable. Workers in heat suits use magnetic grips to position a section under the press. First stage, rough deformation. The press descends with up to 10,000 tons of force, compressing the metal by 20 to 30% in a single cycle. Each strike lasts seconds, gradually transforming the cylindrical blank into the recognizable silhouette of a hook. Next comes intermediate forging. The metal gets stretched out, they shape cable holes up to 2 feet across and lugs 6 inches thick. The presses are equipped with complex dies made from high-strength steel, matching the exact geometry of the future hook. Total forging cycles, up to 50 per section, with breaks for reheating every 10 to 50 minutes. Between press strikes, they constantly flip and reposition the workpiece. This ensures even densification of the metal throughout the entire volume. Forging doesn't just shape it. It improves the internal structure of the metal, refining the crystalline grain and multiplying the strength compared to the cast state. The final forging stage, precision work on the working section. The main arc of the hook reaches over 3 feet in diameter, wall thickness, 12 inches, bend radius, 8 feet. The press dies work with accuracy down to a fraction of an inch, forming reinforcement ribs and flanges. After each strike, they blow off the scale with compressed air at 90 pounds per square inch. After forging comes heat treatment, a stage without which the hook would be just a pretty but unreliable hunk of metal. The piece is placed in a furnace for tempering at 1200 degrees Fahrenheit for 20 hours. This relieves the internal stresses built up during forging and gives the metal the necessary impact toughness. Then comes machining on milling equipment. Surfaces are ground to specified roughness. Mounting holes are drilled. Threads are cut into the attachment points. Each hook weighs between 50 and 150 tons depending on load capacity. Manufacturing takes anywhere from 3 to 6 months. The plant produces up to 20 of these units per year, and each one costs millions of euros. They go to crane companies that install oil platforms in the North Sea, the Persian Gulf, and off the coast of West Africa. Now here's where it gets really interesting: ultrasonic testing. This is where manufacturers hide a detail they'd rather not talk about. Every hook gets checked for hidden cracks. Sensors scan the metal with a 5 MHz wave, detecting defects as small as half a millimeter. If even one microcrack shows up, the part gets scrapped. No negotiations, no exceptions. Why is this so critical? Because these hooks work in conditions where failure isn't an option. An offshore crane lifts a platform section weighing 8 to 10,000 tons to a height of 100 to 130 feet above sea level. Waves slam the vessel's hull, the crane sways, the load cycles constantly, slackening slightly, then building again. These cyclic loads are especially dangerous. They make cracks grow even when the overall stress stays within design limits. Under these conditions, a microcrack that slipped past inspection turns into catastrophic failure within weeks. That's why every hook gets tested not once but multiple times. Ultrasound, X-ray, magnetic particle inspection, load tests up to 120% of rated capacity. After passing all inspections, the hook's surface is coated with an epoxy layer 200 microns thick to protect against saltwater corrosion. Then they apply the markings: serial number, steel grade, manufacturing date, and load capacity. This is the hook's passport, which will follow it throughout its entire service life. The global fleet of offshore cranes exceeds 4,000 units, of which around 1,200 are floating vessels with lifting capacities above 5,000 tons. Hook production for them is concentrated in Europe, primarily in the Netherlands, Norway, and Germany. And ASEAN total output across the entire industry comes to just a handful of units per year. The finished hook is loaded onto a specialized platform and shipped to the vessel. There, in the open ocean, they'll attach a cable to it, hook a platform section to that cable, and this piece of forged steel, born from molten scrap, will single-handedly hold the weight of several hundred railroad cars. Waves, wind, rolling seas, and it holds. Because every press strike, every hour in the furnace, and every pass of the ultrasonic probe were done with zero margin for error.
Every year, more than 50,000 tons of uranium are mined across the globe. But to extract just a few grams of its energy, mountains of rock must be moved. It's a journey that begins in a desert where the temperature hits 38 degrees Celsius and ends inside a reactor that powers New York City. It involves centrifuges that spin faster than a jet turbine and chemicals that can dissolve metal in seconds. But the most interesting part is something that even the safety manuals don't mention. Watch until the end and you will learn a secret that will change how you think about nuclear power forever. It all begins in the dust, literally. Uranium ore is mined in hot, arid regions: Arizona, Wyoming, Texas, New Mexico. Here, the sun is relentless, reaching 38 degrees Celsius in the shade, if you can find any. There are two main extraction methods: open pit mining, where the topsoil is stripped away, and underground mining, with explosives and hoists. There is also a third, more subtle technique: in situ leaching. Pipes are drilled deep into the earth. Special solutions are pumped down to dissolve the uranium directly from the rock, and the resulting liquid is then pumped back to the surface. The ore itself, a grayish-brown rock, looks unremarkable, but within it, the crucial isotope uranium-235 makes up just 0.7%. The rest is a vast, almost useless mass that is inert in a reactor. And to squeeze the required drop of energy from it, hundreds of tons must be processed. After mining, the ore is crushed, milled into a fine powder, and thrown into a chemical bath of acid or alkaline solutions. This is followed by filtration, precipitation, and drying at 260 degrees. The final product is yellow cake, a bright yellow uranium concentrate. Officially, it's known as uranium ore concentrate, but everyone at the plant just calls it yellow cake. It looks striking, a mustard-colored loose powder like a spice for a barbecue. But this is a substance you must not touch and must never inhale. It emits alpha radiation, has a long half-life, and its dust is dangerously toxic. The yellow cake is sealed in double-walled drums, loaded onto escorted trailers, and plastered with radiation warning signs for the journey to the enrichment facility. This is the start of the path that turns a poisonous dust into the clean white light from a lamp over your kitchen table, or the electricity that powers the tube deep beneath London. Right, the yellow cake has arrived. It's radioactive, dry, and sealed in its drum. The next step? Turn it into a gas. And not just any gas. This is uranium hexafluoride. The uranium concentrate is first dissolved in acid, purified, and converted into uranium dioxide. And here, the alchemy begins. The uranium dioxide is treated with fluorine gas in special reactors at 540 degrees. The reaction creates a volatile, transparent gas that boils at just 56 degrees. A little heat, and it turns from solid crystals into a vapor. But it's not that simple. This gas is extraordinarily toxic. It corrodes most metals, destroys human tissue, and on contact with humid air, it instantly transforms into hydrofluoric acid and uranyl fluoride, a lethal cocktail. That is why this entire process is conducted inside sealed, automated reactors. The substance is stored as solid, whitish crystals, formed by cooling it to room temperature. These crystals are kept in steel cylinders, each engraved with a serial number and a radioactive symbol. A single cylinder weighs almost 14 tons. You think your washing machine spins fast? You haven't seen a nuclear centrifuge. They can reach 70,000 revolutions per minute, more than 10 times faster than a jet engine turbine. and all for one purpose: to separate uranium isotopes. Uranium hexafluoride, that toxic gas we just created, is fed into a tall, narrow cylindrical chamber, which is then spun at an insane speed. Centrifugal force does the work. The heavier uranium-238 atoms are flung towards the outer wall, while the lighter, crucial uranium-235 atoms remain closer to the center. But one centrifuge isn't enough. They are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas and passes it to the next. This process is repeated, cycle after cycle, until the concentration of uranium-235 reaches at least 3 to 5%. This is the standard grade for reactor fuel. Okay, the gas is enriched, but you can't feed a reactor with the gas. So now it is converted back into a solid, this time a ceramic form. After a series of chemical reactions, the gas becomes uranium dioxide powder, a dark gray solid. This powder is pressed under 20 tons of pressure into small cylindrical pellets, just 8 millimeters in diameter. They look almost harmless. Next, the pellets are sintered in a furnace at nearly 1650 degrees, making them as hard as porcelain. They are then polished and ground to precise dimensions. The finished pellets are loaded into long metal tubes known as fuel rods, typically made of a zirconium alloy because it resists corrosion and can withstand intense radiation. Each rod holds over 300 pellets. The rods are hermetically sealed and then bundled together into modules called fuel assemblies. They look like a square frame holding a grid of several dozen rods. A single assembly can weigh over 680 kilograms and will operate inside a reactor for up to 6 years. The finished fuel is packed into armored containers for transport. The journey is made under guard, on a special route with a security escort and GPS tracking. Left over from all of this is the depleted uranium hexafluoride, known as tails. It's a mix of isotopes with a small amount of U-235 remaining, but not enough to be useful. These tails are stored in steel cylinders at designated secure sites. When a fuel assembly has served its 4 to 6 years in the heart of the reactor, it is no longer a shining star. It is removed by a robotic system and moved into a deep pool of water, over 6 meters deep. The water cools the assembly and shields the intense radiation because the fuel is still incredibly hot. It rests there for several years. After that, it has 2 possible futures: long-term dry storage in concrete and steel casks, or reprocessing. This usually happens in other countries, as the US and UK primarily store their waste rather than reprocess it. In a dry storage facility, the assemblies stand for decades, cooled by natural air convection, as if in a nuclear monastery. This isn't the end, but a new phase of life. A slow, controlled existence, but one deeply connected to the future of energy. Because even after its time in a reactor, this fuel remains a source of heat, a lesson in engineering, and a reason for profound respect.
Hey everyone, on this channel we go behind the scenes where cameras don't usually get access. If you're into these deep dives, hit subscribe and ring that bell so you don't miss new episodes. Today we're at a factory where strike drones are built from sheet metal. You know, standing in the middle of humming machinery, watching an ordinary piece of aluminum transform into a machine that can fly thousands of miles, you realize this isn't just manufacturing. This is an entire world where every single part has its own story. Just one look at the assembly line gives you goosebumps. Dozens of airframes at different stages, the smell of red-hot metal, the roar of presses and the crackle of welding. We're going to walk through every step, from cutting sheets to the finished drone, and I'll show you exactly how it all works. Buckle up, there's going to be lots of steel, bolts, and maybe a little adrenaline, because the scale here is seriously impressive. It all starts in the cutting shop, where stacks of aluminum and duralumin sheets sit waiting, roughly 1/10 of an inch thick. They arrive in massive bundles, wrapped in protective film to prevent scratches during transport, and are immediately laid out on the cutting equipment tables. Before cutting, every sheet goes through incoming inspection, checking thickness, surface flatness, absence of micro cracks. The laser cutter traces the contours of wings, fuselage, and tail with surgical precision. No crooked lines or jagged edges, because in flight, an error of a millimeter can cost you dearly. The drone needs perfect aerodynamics to fly stable and efficient. The laser melts the metal's edge, leaving a smooth cut, while the plasma cutter handles thicker material. Sparks flying, but both technologies deliver clean geometry without extra finishing. Then the blanks head to pressing. Massive hydraulic presses, thousands of tons of force, stamp out bends, stiffening ribs, and longerons. The sound is like thunder when the die drops and the metal beneath it crunches, taking its commanded shape. The output? Finished panels with precision geometry that'll later be joined into the fuselage. The aluminum here isn't your regular stuff. It's a special alloy with magnesium and copper that handles temperature swings from -58 to plus 194 degrees Fahrenheit without cracking from vibrations or friction. This material's lighter than steel, but strong enough for a structure that needs to endure hours of continuous flight. Next up, fuselage assembly. Different vibe here. Workers in protective suits, tables covered with blueprints, and a whole arsenal of tools. Every panel gets ultrasonic testing for hidden defects. Then they bend it, drill holes, and bolt it together. I watched them assemble the tail section, like a construction set, only full scale, a couple yards long. The bolts aren't ordinary either, titanium or high alloy steel, with threads that hold for years. There are automated lines too, where robots install rivets themselves, thousands per hour. No fatigue, no mistakes. While the fuselage takes shape, engines are already roaring on the next stand over. Here's everything about simplicity and reliability. A two-stroke gasoline engine, similar to those powering old mopeds or lawnmowers, but tailored for the sky. No complex turbines or compressors, just cylinders, a carburetor, spark plugs, and a pusher propeller in the back. About 15 horsepower, but for a drone weighing around 450 pounds, that's more than enough to cover thousands of miles at a cruising speed of 110 miles per hour. The simplicity of design is a deliberate choice. Fewer parts mean fewer points of failure during long autonomous flights. The engine arrives semi-assembled, already a complete unit with crankshaft, pistons, and exhaust system. First thing, it's mounted onto an aluminum frame, which then attaches to the tail section of the fuselage. A worker in gloves slides the engine into the groove, lines it up with the holes, and torques down the bolts with a calibrated wrench, each to a specific torque value spelled out in the documentation. Every bolt gets anti-vibration washers, because in flight, vibration can loosen any connection in a matter of hours. Then they hook up the fuel line. Thin rubber hoses run from the tank and the wing to the carburetor through filters, keeping dirt from clogging the jets. The fuel, regular aviation gasoline, a mixture with additives for stability on long-distance flights. The tank sits inside the wing, and its capacity is calculated so the drone can complete the entire route without refueling. As fuel burns off, the center of gravity shifts, and the autopilot accounts for this during flight control. Next up, the engine control electronics. The throttle valve connects to a servo that takes orders from the autopilot. It automatically adjusts RPM based on altitude, speed, and remaining fuel. The servo is small, like one from an RC model, but with metal gears for reliability. Plastic wouldn't survive here. The propeller goes on last, two-bladed, with a pitch that's dialed in on a special test stand. It's laser balanced to eliminate vibrations that could damage the shaft or wing structure. At idle, it sounds like a moped a half-mile away, but at full throttle, it roars like a miniature airplane. Next up, engine testing. They lock it onto a vibration stand, hook it up to a computer, and fire it up. First few seconds, light smoke from the oil, then steady RPM. The technician listens. Any metallic knocking? Exhaust running smooth? Cylinder staying below 203 degrees Fahrenheit? Sensors pull real-time data, temperature, oil pressure, rotation speed. They tune the propeller, adjusting blade angles to max out thrust while keeping fuel burn lean. Every engine runs on the stand for at least several hours straight, simulating actual flight loads. If everything checks out, they preserve the engine, wrap it in plastic, and set it next to the fuselage. Mounting it on the drone takes a few minutes. Slide it into the tail section, tighten the bolts, check the fuel line and wiring. Done. Ready to roll out to the flight range. Now the wings, that's a whole different story. Ribs and spars are stamped out of duralumin sheets, bonded with foam core to form the aerodynamic profile, then covered with fabric or plastic. Wingspan runs about 8 feet, and each one feels light as a feather to the touch, yet strong as a wooden plank. Hidden inside is a lot: fuel tanks, wiring, some of the electronics. The wings attach to the fuselage with quick-release fittings, so the drone can be disassembled for transport and put back together right in the field in a matter of minutes. The electronic guts deserve their own mention too. Surprisingly simple: navigation module, chip-based autopilot, altitude and heading sensors, barometer and accelerometer. Nothing extra, because the drone has to fly itself, along a preset path, thousands of miles over the ground without operator input. Programmers test the software on separate benches, punch in coordinates, and the virtual model on screen flies exactly along the planned route, hugging terrain and holding altitude. After final assembly comes painting and camouflage. The body gets coated with anti-corrosion primer, then covered with special radar-absorbing paint, gray-green matte finish so it doesn't glint in the sun. This isn't just cosmetic. That coating genuinely reduces radar signature. Then comes test stand evaluation. They check balance, vibration, fuel tank sealing. Interesting fact: drones aren't just tested under normal conditions, but also in vacuum chambers to see how joints and connections behave at high altitude, where pressure and temperature drop sharply. If everything checks out, the drone moves to flight trials. It launches from a catapult, climbs, gains altitude, runs its program, and returns. Quiet, almost smokeless, just dissolves into the sky like a ghost. The production scale is impressive. Dozens of machines being assembled simultaneously on the line, work running around the clock in 3 shifts. Metallurgists melting alloys, machinists turning shafts, electronics techs soldering boards, all in one complex where every stage syncs with the others. Quality control at every step, because one defective part can destroy the entire aircraft. Picture this: a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands, scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break, doesn't bend, doesn't crack. For decades. How does a 4 millimeter sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets, and I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes.
It all starts in the raw materials warehouse, and the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport,
chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts, with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part, forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method, shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a 3-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside, stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted. And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work, riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force. But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting.
When all the parts are ready, assembly begins. The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. 2 enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets. After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly. That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, this structure started as a flat sheet barely 1/6 of an inch thick, and every fraction of that journey, someone's work, someone's inspection, someone's craft.
The world's largest source of recycled steel isn't born in deep mines, but in bustling cities. They call it the car's second gateway. It's the vehicle recycling industry, the industry that transforms car graveyards into the most efficient steel mines of the modern era.
In the United States alone, more than 12 million cars vanish from the roads annually, beginning a remarkable journey. This isn't a story about the death of metal. It's a story about its immortality. How does steel, having completed its service, pass through fire and mechanical hell to be born anew? And what is the astonishing secret hidden in every old car that even its previous owner doesn't know? The answers will astound you. Behind every car rusting at the roadside lies a colossal $60 billion industry. This is a world where millions of old cars never truly die, they simply transform. This process provides employment for hundreds of thousands of people and deals a hefty blow to the costs of traditional metallurgy. Whilst iron ore represents a natural mine, limited and expensive, end-of-life vehicles are a man-made mine, practically limitless. Each recycling cycle saves up to 74% of the energy compared to the arduous mining of fresh ore from beneath the ground. That's enough to power a small town for an entire year. On average, up to 75% of each car's wheat can be recovered, from steel and aluminum to glass and plastic, and returned to service. As a result, hundreds of millions of tons of materials are regenerated annually, continuing their journey as skyscrapers, household appliances, and even gleaming bodywork for the next generation of vehicles. When a motor car reaches the end of its service life, its story doesn't simply end. Rather, it's only just beginning. The vehicle is transported to the reception area of a recycling facility, a sort of purgatory for automobiles, if you will. Here, technicians, rather like pathologists, meticulously examine each patient. They record the vehicle identification number, year of manufacture, mileage covered, and general condition. Every car is photographed, assigned a unique tracking code, and all data uploaded into a digital system that will monitor its fate through each subsequent stage. Particular attention is paid to components that might still serve humanity: engines, gearboxes, alternators, and electronic elements. These organs are carefully extracted to feed a used car parts market worth billions of pounds. Remarkably, in the United States, thanks to an incredibly sophisticated system, over 95% of scrapped vehicles pass through this process. This makes motor cars the most recycled consumer product in the world, more efficiently recycled than paper or glass.
After reception, the vehicle is transferred to the detoxification area. The first and most crucial step is neutralizing the hidden danger. The lead-acid battery is immediately extracted from under the bonnet. Its recycling rate reaches nearly the ideal level of 98%. Lithium-ion packs from hybrid and electric cars require far stricter procedures and are sent to specialist facilities, where they're dismantled almost entirely by hand. Only then is the electrically isolated vehicle lifted onto a platform for complete draining. Special installations resembling giant syringes pierce the tanks and pipes, pumping out all fluids: residual petrol, engine and gearbox oil, and air conditioning refrigerant. A written-off car still contains dozens of liters of flammable and toxic materials. Remarkably, nothing goes to waste here. Most extracted fluids are filtered and used to fuel the plant's own equipment, creating a nearly closed energy loop. Once all the fluids have been drained, the car transforms into a lifeless steel skeleton, and its anatomical dismantling begins. The wheels come off first. Old tires, which would otherwise decompose for centuries in a landfill, are sent for shredding into rubber crumb for tarmac and safe surfacing for children's playgrounds. The steel and aluminum discs go straight for remelting. Next comes the glass. Specialized robots with diamond cutters remove the windscreen and side windows. Then the doors are taken off. The steel frames are cut away, whilst the complex innards, electric motors, speakers, and miles of wiring, are stripped separately to extract valuable copper.
After that comes the interior, seats, dashboards, and carpeting. Finally, the climax arrives, the extraction of the car's heart and soul. The engine and gearbox, the heaviest and most valuable units, are carefully lifted out using hoists. Some will be restored, the genuine high-mileage survivors, and sold on. Others will be dismantled down to the last bolt to extract precious metals from catalytic converters, platinum, palladium, and rhodium. Before a car enters the final chapter of its life, it awaits harsh yet necessary procedures. Everything surplus is stripped away. Enormous mechanical arms, fitted with hydraulic shears capable of slicing through steel beams with forces of dozens of tons, tear off what remains of the doors, rip out exhaust systems from their roots, and crush radiators like paper cups. Plastic bumpers, upholstery remnants, and foam are cast aside. This stage serves as a crude filter, removing anything that might contaminate the pure steel. After just a few minutes of brutal yet effective cleaning, nothing remains of the car but its pure essence, a sleek steel shell. It's now sent to a hydraulic press. Under crushing force ranging from 150 to 200 tons, as though a blue whale had stepped upon the vehicle, the chassis is compressed into a compact metal block, merely 1/10 of its original size. Once the structure's been compressed, these dense steel blocks, rather like giant sugar cubes, are fed into the maw of a genuine monster, a high-performance shredding machine. This is the mechanical heart of the entire line. Inside its chamber, massive steel rollers fitted with hardened steel teeth rotate in opposite directions. With an ear-splitting roar that shakes the ground, they seize the compressed block and tear it to shreds. Within seconds, what was once a car occupying an entire parking space transforms into a stream of homogeneous scrap metal fragments roughly the size of a fist. A modern industrial shredder can process up to 150 tons of steel per hour. That's hundreds of cars every single day. After shredding, this mixture of metals and non-metals travels along the sorting line. Powerful magnets suspended above the conveyor pluck all the steel from the stream, whilst eddy currents, creating an invisible field of force, deflect the lighter aluminium and copper to one side. What was once a car's skeleton is now fed as pure steel billets into the electric arc furnace. Here, a fiery rebirth awaits. Massive graphite electrodes descend into the metal mass, unleashing currents of tens of thousands of amperes, creating a dazzling arc resembling artificial lightning. Within minutes, the internal temperature soars beyond 1,600 degrees Celsius, transforming solid scrap metal into a raging torrent of molten steel. Lime and flux are added to this fiery ocean, acting like chemical sponges, absorbing all remaining impurities and forming a layer of slag on the surface. From a chaotic mass of old car parts emerges a shimmering sea of pure molten steel. This blazing current is immediately directed to the continuous casting line, where it flows into water-cooled molds, solidifying and forming long, glowing blocks or billets. The moment it leaves the furnace, the red-hot glowing steel blocks head straight to the hot rolling mill. Here, dozens of massive rollers, spinning at tremendous speed, continuously press and stretch them, giving them a new form, whether that's a panel for a future motor car or reinforcement bars for a skyscraper. The freshly rolled steel must be cooled, but this must be done in a controlled manner. Spray nozzles envelop its surface in a white mist, rapidly reducing the temperature. Once the steel has cooled, each coil undergoes rigorous inspection. Ultrasonic sensors scan for any hidden internal cracks, invisible to the naked eye. From fiery glow to stable strength, this is how steel is reborn.
Every finished motor car feeds a multi-billion-pound industry, proving that recycling isn't merely an environmental solution, but also a hidden pillar of the modern economy. And the secret we mentioned at the start is simple. In every new car, in every skyscraper, in every bridge, there lives a part of a motor car that once traveled our roads. Metal doesn't die, it simply awaits its hour to return. Every year, humanity forges colossal anchor chains capable of withstanding a force of over 1,500 tons, enough to hold back an entire freight train loaded with coal. A single link can weigh more than 500 kilograms and be as thick as a tree trunk. But how is such immense strength born from a simple bar of red-hot steel? What brutal trials must every meter of this steel serpent endure before it is trusted to the depths of the ocean? Stay with us until the end to witness a process of fire, sparks, and true engineering alchemy. It all begins not in the forge, but at a steel mill, where a special alloyed steel is created from ore and scrap. This is no ordinary metal. To produce chains that can handle loads of thousands of tons, you need the highest grade of steel, one capable of resisting not only tension, but also the embrittlement that comes from the extreme cold of Arctic waters. After smelting and chemical analysis, the steel is cast into massive cylindrical billets. These billets, while still hot, are passed through rolling mills that, with incredible force, squeeze and stretch the metal, forming it into long, round steel bars with a diameter that can exceed 200 millimeters. The production hall is a kingdom of fire and metal. The air here is thick with the hum of machinery and the sharp, distinct smell of incandescent steel. It is here that the magic happens, transforming a straight bar into a curved, closed loop. First, the steel bar enters the infernal mouth of an induction furnace. In a matter of minutes, a powerful electromagnetic field heats it to 1200 degrees Celsius, making the metal plastic and malleable. The glowing bar is then immediately fed to a bending press. Hydraulic arms effortlessly bend it into its characteristic U-shape. Now comes the critical moment. While still hot, the U-shaped piece is threaded through the last, already completed link of the growing chain. This is how the links are interconnected. The two ends of the U-shaped piece are then brought together and clamped tightly in the giant copper jaws of a welding machine. The process of flash butt welding begins. An enormous electrical current is passed through the joint. The metal at the point of contact instantly melts, accompanied by a blinding flash and a fountain of sparks. At that exact moment, a hydraulic press with hundreds of tons of force squeezes the molten bands together, fusing them at a molecular level into a single seamless piece. The excess metal, known as flash, is immediately sheared off by special cutters. While the link is still hot from welding, a special stud is fitted into its center. This crosspiece not only gives the link additional rigidity, but, most importantly, prevents it from deforming and tangling during use. After the stud is set, the entire chain, or a section of it, undergoes heat treatment. It is reheated to a precise temperature and then rapidly cooled or quenched in a huge pool of water. This process makes the steel extremely hard, but also brittle. To remove this brittleness, the chain is heated again to a lower temperature and left to cool slowly in the air. This final step is called tempering. Not a single meter of a giant chain leaves the factory without undergoing a series of the most stringent tests. This is the guarantee that it will not fail at a critical moment. First, the entire chain is subjected to a proof load test. It is secured in a special testing machine, a colossal hydraulic bench dozens of meters long. The machine begins to stretch the chain with a force significantly greater than its nominal working load. Inspectors meticulously examine every link for any sign of deformation. But the most dramatic trial is the break test. A test sample of several links is cut from the finished batch. It is placed in the same machine and pulled until it shatters. The deafening crack of rupturing metal is not a sign of failure, but the ultimate confirmation of the entire batch's quality. After the mechanical tests, every single link is inspected with ultrasound to detect any hidden internal flaws. Only after successfully passing all these stages does the chain receive its quality certification. Loaded for transport, it looks like a sleeping steel leviathan ready to begin its silent service in the depths of the ocean. For the highest grade chains, this proof load can exceed 1,000 tons. This means the chain is stretched with a force equivalent to the weight of 3 Boeing 747s. The minimum braking load for such products often exceeds 1,500 tons. Behind every giant link is a world of impressive numbers. A single link of a top-grade anchor chain can be forged from a steel bar over 200 millimeters in diameter. The weight of such a link easily exceeds 500 kilograms, more than a grand piano. However, chains are not measured by the link, but in sections. A standard marine section, or shot, is 27.5 meters long. The complete anchor chain for a supertanker can consist of 12 to 15 of these shots, reaching a total length of over 400 meters. Its total weight can easily exceed 250 tons, comparable to the weight of 2 adult blue whales.
1,300,000,000 meters of submarine internet cables have already been laid on the ocean floors. And every year, this length grows. Also, we can send a message, watch a video, or make a call across continents. Over 95% of all intercontinental internet traffic passes through them every day. Stretched through the depths, they cross volcanic ridges, encounter sharks, ships, and even geopolitics. How are these gigantic infrastructures created? Who designs the routes? How are they laid on the seabed at depths of over 26,000 feet? And what happens when a cable is damaged?
For the internet to cross oceans, a cable is needed that can withstand pressure, salt water, marine life, and decades of operation without repair. It all starts with the central core, a copper or aluminum conductor, through which the main signal travels. Large ingots of purified metal are melted and passed through drawing machines, which repeatedly pull the material through narrowing dies, reducing the diameter to a few millimeters. At this stage, a perfectly round cross-section is formed, one that has no microcracks or air pockets. After drawing, the wire undergoes heat treatment. It is heated to a precisely set temperature to relieve internal stress and make it more flexible. Then it is cleaned of oxides, often by a chemical method, or using abrasive rollers.
The output is a shiny, smooth, almost flawless wire. It is checked automatically for diameter, resistance, flexibility, and surface purity. The wire must withstand kilometers of bending and work without failure, even at depths of several thousand feet. Depending on the type of cable, the wire is either used as a single solid conductor or is twisted from several thinner strands, which increases flexibility and protection against breakage. Once the copper or aluminum conductor is ready, it is immediately fed into an extrusion line, a long machine resembling a tunnel. Inside, polyethylene heated to 482 degrees Fahrenheit, which melts into a thick, viscous cream. The conductor moves along a conveyor and enters the extruder head, where the molten polymer precisely and evenly flows around the metal, like a second body. Every millisecond is important here. Too slow, and drips will form.
Too fast, the polyethylene won't have time to adhere. Immediately after this, the cable enters a bath of cooling water, where the polyethylene layer quickly solidifies, tightly enveloping the conductor. The entire surface must be smooth, without a single bubble or crack. This is the first line of defense against moisture. After cooling, inspection. Lasers measure the insulation thickness, and cameras check the surface. If anything is even slightly off, the cable is cut and reprocessed. The next stage is the application of a hydrophobic gel, which acts as an invisible protector. This thick, viscous compound fills all the voids inside the cable, envelops the optical fibers, and creates an internal shield against moisture. In a special chamber, the cable passes through a system of nozzles or rotating heads that evenly apply the gel to the central part and in the space between the fiber elements. The gel resembles a transparent lubricant. It doesn't dry out, freeze, or dissolve in water, even at a depth of 26,000 feet under a pressure of hundreds of atmospheres. Its main property is to repel water. If the cable sheath is ever breached, the gel instantly spreads and prevents moisture from penetrating inside, not letting it reach the sensitive fibers. At this stage, it's also important that there isn't too much gel, otherwise it complicates the further laying of layers, and not too little. Then the protection efficiency drops. Computers precisely regulate the dosage, and operators visually check the filling and uniformity. After application, a short cooling and stabilization. Now the cable is ready to receive its optical heart, the fiber threads that transmit light from one continent to another. These fibers, usually from 4 to 12 of them, are first grouped into modules. Each module is a flexible capsule with several fibers inside, providing additional protection. The modules are very carefully arranged in a spiral around the central conductor. This configuration allows the fibers to bend without tension, especially during winding and laying the cable at sea. To keep the fibers in place, they are fixed in a bedding of gel that was applied earlier. There is no glue, only a tight fit and a flexible structure. It's important that no fiber crosses another, breaks, or shifts from its place. The work is almost like jewelry making, although it's done on a conveyor. Afterward, a continuity check of each fiber. A laser beam is sent through them. Even a microcrack or a bend will cause a failure, and the fiber won't pass inspection. If everything is fine, the structure moves on to the next stage, additional insulation and reinforcement. First, an additional polymer layer is applied over the optical fiber structure. Often it's high-density polyethylene, or another flexible waterproof material. It protects against mechanical damage, friction, and moisture. This is again done in an extruder, similar to the one where the first insulation layer was applied. The cable passes through molten polymer and immediately enters a cooling bath. After cooling, the cable enters the steel wire braiding section. Machines evenly lay steel rods or tapes in a spiral around the already insulated core. In shallow water areas, this armor is thicker to protect against anchors, fishing nets, and shark teeth. At depth, the armor is thinner or absent altogether. After reinforcement, another outer polymer sheath may be added, which seals the entire structure. Operators carefully inspect the cable surface, checking for uniform thickness, no abrasions, burrs, cracks, or armor misalignments. Then, automated tests. Lasers scan the thickness. Cameras capture every millimeter. Light pulses are sent through the fibers again. The signal must pass without delays or losses. If a defect is found at this stage, it is cut out and both ends are joined using a special technology, creating a sealed splice joint.
After inspection, the cable enters the marking section. Here, information about the batch, production date, cable type, and its purpose is printed on the outer sheath. Often, every few feet, so it's easy to identify the cable even during laying on the seabed. And finally, winding onto spools. These are giant drums with a diameter of up to 13 or 16 feet, which can hold up to 8,200 feet of cable. Each turn must lie flat, without twists, and with uniform tension. Automatic systems regulate the speed and tension force, and operators monitor each stage. If the cable is intended for installation at sea, the drums are immediately sent to ships where they are installed on the deck. If not, they're stored in special warehouses with humidity control, because even minor corrosion can be fatal.
Each year, humanity produces over 400 million tons of plastic, of which 23 million tons end up in the oceans, forming gigantic rubbish islands the size of entire countries. Consider the Great Pacific Garbage Patch alone, which covers an area 3 times that of France. Just imagine, this isn't merely rubbish, but a threat that kills millions of marine creatures annually. And by the year 2060, the oceans will be drowning in 141 million tons of plastic. But would you believe that this blot doesn't actually exist in the form we imagine it? It's an invisible trap concealing a secret. How an ordinary teenager invented a method to clean the oceans without engines, using only the forces of nature? And if you watch to the end, you'll discover revolutionary robots sorting rubbish faster than lightning, and the Interceptor, which blocks plastic in rivers using solar power. A secret that will forever change your perception of the planet's future. The waste management sector is undergoing a technological revolution thanks to the introduction of artificial intelligence and robotics. At modern waste processing facilities, robotic arms controlled by sophisticated algorithms sort refuse at remarkable speed and with exceptional precision. Computer vision systems identify different types of materials, enabling a significant increase in recycling rates. Along a wide conveyor belt moves a continuous, chaotic stream of what we've discarded. Plastic bottles, crushed cardboard boxes, aluminum cans. To the human eye, it's simply rubbish, whilst for workers it represents arduous and hazardous labor. And there, above this flow, rather like a relentless predator, it hovers, the sorting robot. This isn't a humanoid android from science fiction films, but rather a high-tech industrial manipulator resembling a giant steel arm. Yet all its magic lies within. Its eyes aren't merely cameras, but complex, multispectral sensors that perceive the world quite differently from us. They can distinguish materials by how they reflect light and analyze their chemical structure in fractions of a second. The heart and brain of the system is artificial intelligence. Before being deployed on the job, this AI underwent intensive training. It was shown millions of images of various types of waste until it learned to recognize them flawlessly. In this way, the robot learned to identify PET plastic, from which drinks bottles are made, denser plastic for canisters, paper, cardboard, various types of metals, and glass. And so the action begins. The conveyor belt races onwards. The camera scans the flow continuously. Artificial intelligence analyzes the image in real time. Target identified, aluminum can, it sends the signal. And a steel manipulator makes a lightning-fast, almost imperceptible lunge. A pneumatic suction cup or mechanical gripper gently but firmly seizes the can, and with a precise movement, drops it into the appropriate container. Before the can has even landed, the robot's eye has already spotted a water bottle, and the arm flies towards the new target once more. Speed? A human cannot compare with it. Some models are capable of making 100 manipulations per minute. That's more than 1 grab per second. Accuracy? The robot doesn't tire and doesn't get distracted. Its sorting efficiency reaches more than 95%, which significantly improves the quality of recyclables. This isn't simply a replacement for manual labor. It's a qualitative leap, which transforms the problem of rubbish into a genuine resource. The sorted materials, heaps of rigid plastic, cumbersome metal structures, wooden pallets, lie in separate mountains. They've already been sorted, but they're still far too large. It's here that the real heavyweight of the recycling industry enters the arena, a machine whose work is controlled, brutal force. This is the hammer mill. Outwardly, it resembles an enormous steel box, but its heart is a massive, heavy rotor, studded with rows of exceptionally robust, hardened steel teeth or hammers. Its task is simple, yet critically important: to shred. When material is fed into its vast maw via conveyor, be it an old car bumper or an entire pile of plastic drums, a spectacle of unstoppable power begins. As it rotates, the rotor's teeth seize hold of objects, dragging them inwards, and with a deafening roar and grinding, tears them to pieces. Rigid plastic cracks, metal bends and rips, wood transforms into splinters. This process is a demonstration of pure physical force. But what purpose does this destruction serve? It isn't senseless obliteration, but rather a crucial preparatory stage. Firstly, the shredded materials become uniform in size, which makes them far more convenient for transport and subsequent processing. Secondly, it's a process of liberation. The shredder breaks down complex objects into simpler components, facilitating the separation of different materials from one another. And most importantly, it creates ideal feedstock for further recycling. A heap of small plastic fragments melts far more readily in a granulator than intact bumpers.
Vast accumulations of plastic in the world's oceans, such as the Great Pacific Garbage Patch, represent one of the most pressing environmental concerns. Incidentally, do you believe this patch doesn't exist? Nevertheless, through bold engineering solutions, hope emerges for cleansing our marine spaces. The problem is so enormous it appears insoluble. How does one remove something the size of several countries? Most simply threw up their hands, but not Dutch teenager Boyan Slat. In his mind was born a daring yet brilliantly simple idea, which grew into one of the most ambitious environmental projects of our time, the ocean cleanup. The project's principle is not to chase the plastic, but rather to make the ocean itself deliver the rubbish into the trap. For this purpose, giant U-shaped barriers were created. The most intriguing aspect is how this system moves. It has no engines. It drifts passively, caught by the same forces that carry the plastic: wind, waves, and ocean currents. But owing to its design, the system moves slightly faster than the plastic. This creates a small but constant difference in speed. The barrier, rather like a giant shepherd, slowly but inexorably gathers its plastic flock within its U-shaped arc. The path to success wasn't straightforward. Early prototypes fractured under the onslaught of ocean storms, but after a series of trials and errors, the system began working effectively. Now, from time to time, specialized vessels approach the laden barrier and offload the collected tons of plastic. This plastic, from old fishing nets to minute fragments, is brought ashore, where it's sorted and sent for recycling, closing the loop. Realizing that cleaning the ocean without stopping the flow of rubbish is rather like bailing water from a leaking boat, the ocean cleanup team asked themselves a logical question. Couldn't one simply plug the leak? After all, research shows that the overwhelming majority of plastic enters the ocean through only a small number of the world's most polluted rivers. Thus was born the Interceptor, a technology designed to tackle the problem at its source. It resembles an elegant, futuristic catamaran, anchored mid-river. It is entirely autonomous and runs 100% on solar power, courtesy of the panels covering its upper portion. Its design has been thought through to the smallest detail, so as to be maximally effective whilst not interfering with shipping.
Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures. Mountains of scrap metal, remnants of cars, construction frames, old machinery, sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace. Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, so the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine, where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, And these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock? To do this, it's sent to a heating furnace where its temperature is brought back up to that perfect plastic state, 2300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill. This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them. And here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder. And the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod, or mandrel, is fed in to meet it. It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round. They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides.
Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide, and the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal.
A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section? That'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stresses hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision.
Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision, Then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot micro cracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse. And just like that, traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story, from fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry.
Every hour, somewhere in the world, a metal component weighing over 50 tons is manufactured. And a single microscopic error in its machining can trigger a multi-million-dollar catastrophe. Picture a crankshaft as long as a bus that must survive a billion cycles of explosive force. Or a cylinder block where a deviation the thickness of a human hair means scrapping a multi-ton giant entirely. But here's the mystery. How do engineers achieve micron-level precision when machining parts heavier than a tank? What happens in that secret quality control room, where a computer measures thousands of points and can shut down the entire process? And most importantly, stick around until the end, because I'm going to show you the final operation where one tiny slip turns months of work into scrap metal. This is manufacturing where every thousandth of an inch is a matter of engine life and death. Ready to look inside? The first thing that hits you at this facility? The sheer scale. Forget your average car engine. Take this cylinder block, for example. It can weigh dozens of tons. This isn't just a casting, it's a complex, multi-layered masterpiece of foundry art, requiring special grades of steel or cast iron that can withstand unbelievable loads, temperatures, and pressures. And here's the crankshaft. In big engines, this thing can be as long as a small bus and weigh just as much. This component is probably the most critical. It has to endure the explosive force of fuel combustion, converting it into rotational motion. The blanks often arrive as massive forgings where every pound of metal already has its own story. The process starts with incoming inspection. Specialists check the chemical composition, scan for internal defects using ultrasound and X-ray equipment. Because even the tiniest hidden flaw in a part this massive could lead to catastrophe during operation. It's like a health checkup for a steel giant. Only after a thorough inspection does the blank get clearance to enter the machine shop. Moving these blanks takes serious muscle. That's why the shop is equipped with powerful overhead cranes capable of lifting loads that outweigh most ordinary machine tools. Mounting the part onto the machining center is a precision operation requiring coordination and experience. This is the first step in turning metal into might. Now we move to the heart of the shop, the cylinder block machining zone. This is where multi-axis machining reigns supreme. Before you stands a gantry-type milling machining center. It looks more like a small house than a machine tool. Its spindles, fitted with ultra-hard cutting inserts, can remove up to several hundred pounds of metal per hour. The first operation is roughing. The goal, remove excess stock, eliminate surface casting defects, and give the part its basic geometry. The speed and sheer aggression of this cutting process? absolutely mind-blowing. Those streams of hot chips tell you everything you need to know about the energy being dumped into this transformation. But the real magic happens later, during finishing operations. Remember when we talked about precision? For diesel engines, perfect cylinder geometry isn't just important, it's critical. That's where boring and honing come in. Boring creates the cylinder holes with micron-level accuracy. The slightest geometric error means uneven wear, compression loss, and ultimately engine failure. And honing, that's the final touch. A specialized tool with abrasive stones creates a micro-texture on the cylinder's inner surface, what we call crosshatch. This crosshatch is essential for holding oil and ensuring perfect lubrication of the piston rings. We're talking about polishing at nearly molecular level, guaranteeing engine life measured in decades. These machines operate under strict temperature control. Any temperature fluctuation can cause thermal deformation in a part weighing several tons, which means losing precision. That's why the shop floor maintains a constant microclimate, and the machining itself can run for days. Up next, meet our next hero, the crankshaft. This component works under the most demanding conditions. It needs not only colossal strength, but perfect balance. Manufacturing it, an engineering masterpiece. First up, preliminary journal machining. On specialized CNC turning milling machines, the connecting rod journals and main journals take shape. Given the weight and length of the shaft, unique support systems are used here to prevent sagging and vibration during machining. The critical stage, grinding. The shaft journals must have minimal surface roughness because that's exactly where friction with the bearings occurs. The smoother the surface, the less friction, and the longer the engine lasts. Special cylindrical grinding machines with highly sensitive sensors handle this job. Now, for the critical part, heat treatment and surface hardening. After grinding, the crankshaft journals undergo induction hardening or nitriding. What does this do? It creates a super hard, wear-resistant layer on the journal surface while maintaining the core's toughness and strength. This is essential so the shaft can withstand billions of load cycles. Think of it as armor for the engine's most vital component. Final stage, balancing. Given the massive weight, even a tiny imbalance can destroy the engine. That's why every crankshaft goes through dynamic balancing. If the machine detects a deviation, counterweights are added, or material is removed from the flywheel sections until the shaft achieves perfect balance. It's like tuning a violin, except instead of music, we get harmony of rotation and power. How do you achieve that kind of precision when working with such giants? The answer lies in the tooling and quality control. The tool itself is a high-tech product. Every cutter, every mill is equipped with carbide inserts or even synthetic diamonds. They have to withstand enormous temperatures and cutting pressures. Special coatings extend the life of these tools while keeping machining quality consistently high. In a dedicated tool room, there's constant monitoring of their condition, resharpening, and replacement. But the most important thing is quality control. After every key operation, the part undergoes rigorous measurement. Coordinate measuring machines help us with this. These machines, equipped with high-precision probes and laser scanners, can measure up to 1,000 points on a part's surface with accuracy down to a few micrometers. They create a three-dimensional map of the part and compare it to the perfect computer model. If the error exceeds the tolerance, the process stops, and the part gets sent back for rework or, worst case, scrapped. No part leaves the shop floor until the computer gives the green light on its perfect accuracy. And then, when all the components, the block, crankshaft, cylinder heads, connecting rods, have passed strict inspection and achieved perfect precision, they're ready for the final stage: assembly. This is a different shop, where sterile cleanliness reigns. Assembling an engine like this is no less precise a process than machining. All parts are thoroughly washed, removing even microscopic traces of metal chips and dirt. Specialists use torque wrenches to tighten thousands of bolts to a precisely defined spec. A mistake in torquing the cylinder head, for example, can lead to a blown gasket and engine failure. Every stage of assembly is tracked and controlled by electronic systems. Not a single bolt gets tightened without computer confirmation. After assembly, the engine heads to the test stand. Here it's fired up and gradually brought to operating conditions. Sensors measure temperature, oil pressure, vibration, power output. Any deviation from the norm, and the engine goes back for rework. Only after successfully passing all tests does the engine receive its quality certificate. These giants get installed on ocean vessels, locomotives, mining dump trucks, power plants. One of these engines can run for decades, churning out thousands of horsepower. And behind every hour of its flawless operation stand months of work by engineers, machine operators, quality inspectors. Manufacturing these engines is the pinnacle of mechanical engineering, where metallurgy, precision mechanics, and computer technology converge. And just like that, starting from a multi-ton forging, through rough and finish machining, through honing with precision down to microns, through heat treatment and balancing, through sterile assembly and rigorous testing, an engine is born, capable of running billions of cycles without a single failure. This is the story of how humanity learned to create steel hearts for the most powerful machines on the planet. Every crankshaft, every cylinder block, it's a symphony of engineering thought where an error of 1 micron means failure, and success means decades of flawless operation. When you see a massive ship crossing the ocean, or a locomotive pulling thousands of tons of cargo, remember, at its heart beats an engine, every part of which has passed through the hands of master craftsmen and the scrutiny of computers. This isn't just metal, it's the embodiment of humanity's drive for perfection, where precision is measured in microns and reliability in decades of impeccable service.
Today we're at one of Europe's largest oil extraction plants, where ordinary sunflower seeds become the very same oil sitting in your kitchen. The facility sprawls across dozens of acres, silos towering overhead, pipelines everywhere, tanks as far as you can see. And hanging over everything, this warm, slightly oily air with a nutty undertone. You'd think it's simple, just squeeze and done. But when you see the scale of this operation, you realize, between a seed from the field and that clear bottle on the store shelf, there's an entire chain of processes where temperatures hit 570 degrees Fahrenheit, pressure reaches hundreds of atmospheres, and raw material flows in at thousands of tons per day. Come on, let me show you how it all works. It all begins in the fall, when one grain truck after another rolls up to the plant from the fields. Each semi brings in 20 to 25 tons of sunflower seeds. At peak season, the plant receives up to 300 trucks a day. That's about 7,000 tons of raw material, every single day. But before a seed gets anywhere near production, it has to pass inspection. The lab at the entrance takes a sample from every truck with a long probe,
stabbing into the grain pile at different depths. They check moisture, oil content, debris, and damaged seeds. Moisture can't exceed 7%, or the seeds will start rotting in storage.
Good sunflower seeds have an oil content of 45 to 52%, meaning almost half the seed is pure oil. If the parameters check out, the truck heads to unloading. The seeds pour into underground hoppers, where elevators lift them into silos, massive concrete towers up to 130 feet tall, where the raw material is stored under controlled temperature and ventilation. From the silos, seeds move along conveyors into the prep area. First step, cleaning. Seeds pass through separators that remove rocks, twigs, stem fragments, and other junk that hitched a ride from the field. Magnetic traps pull out stray metal bits, bolts, wire scraps, anything that could wreck the equipment. After cleaning comes cracking. Special mills split the hull and free the kernel. Think of it like cracking sunflower seeds with your teeth, except at tens of tons per hour. The hull, that's the shell we spit out when we snack on seeds, here they don't toss it. Hulls get pressed into pellets and burned in the plant's boilers, generating heat and steam for production. The facility basically heats itself with its own waste. The clean kernels get crushed on roller mills. Heavy steel rollers flatten them into thin flakes about 12 thousandths of an inch thick. That's called conditioning. The thinner the flake, the easier it is to extract oil later. Surface area multiplies. The meats get sent to roasters, massive multi-tiered vats where they're heated with steam to 200 to 230 degrees Fahrenheit while constantly stirring. This process is called moist heat treatment. It softens the cell walls and lets the oil flow out more easily. The smell in this room is incredible. Thick, nutty, warm, makes you instantly hungry. From the roasters, the hot meats feed into screw presses, powerful machines that look like giant meat grinders. Inside, a steel auger spins, forcing the mass through a narrowing channel. Pressure builds to 4,400 to 5,000 psi, and the oil literally gets squeezed out of the meats, dripping through slots in the press housing into a catch tray. A hot golden stream pours continuously. It's mesmerizing to watch. This is pressed oil, dark, cloudy, with a strong roasted seed smell. Many people think this is the final product, but actually, the press only extracts about 60 to 65% of the oil. The rest hides in the cake, a dense compressed disc that comes out of the press hot and hard as wood. To grab the remaining oil, the cake gets sent to extraction, and this is where the real chemistry begins. The cake is crushed, flattened again into flakes, and loaded into an extractor, a long horizontal unit that looks like a slowly rotating carousel. Inside, the flakes get washed with a solvent, usually hexane, a volatile liquid that dissolves fats but doesn't mix with water. Hexane flows through the layer of cake, soaking up the oil, and comes out the other end as micella, a blend of solvent and oil. The process takes about an hour, and during that time, hexane pulls out virtually all the remaining oil from the cake. The fat content in the spent meal drops to 1%. Meal is what's left of the seed after the double pressing. It's protein-rich, up to 46%, and goes into livestock feed. Essentially, from a single seed, the plant gets oil for people, protein feed for animals, and fuel from the hulls. Zero waste production at its finest. Now we need to separate the oil and hexane. The micella is heated in distillers to 200 to 220 degrees Fahrenheit. The hexane evaporates, its vapors are captured, condensed, and returned back to the extractor. It runs in a closed loop with almost no losses. Solvent losses per ton of oil, just about 2 pounds. The rest goes back into the cycle. What remains is crude extracted oil, dark with a specific smell and tons of impurities. Phospholipids, waxes, free fatty acids, pigments. You definitely shouldn't drink it yet.
Refining begins, a multi-stage purification that transforms this murky, dark liquid into the clear oil we're used to. First step, hydration. Hot water is added to the oil, and the phospholipids swell and precipitate out as a sediment, which is separated in a centrifuge. The centrifuge spins up to several thousand revolutions per minute and splits the oil and sediment in seconds. This sediment, lecithin, is a highly valuable product used in the food and pharmaceutical industries. Next up, neutralization. They pump an alkaline solution into the oil that binds up free fatty acids. The result? Soap. Yes, actual soap. A centrifuge spins it out, then they rinse the oil with water to get rid of leftover alkali. After that comes bleaching. The oil gets mixed with bleaching clay that soaks up pigments like a sponge, pulling out the dark color. The clay settles, gets filtered off, and the oil turns pale yellow, almost clear. The final and most delicate step of refining is deodorization. The oil gets heated to 440 to 480 degrees Fahrenheit in a vacuum column at just 2 to 4 millibars of pressure, basically the vacuum of space. They blast live steam through the hot oil, and it carries away every last volatile compound responsible for smell and taste. The whole process takes an hour to an hour and a half. What comes out? Completely neutral oil. No taste, no aroma. That's exactly what we buy at the store with the label refined, deodorized. The finished oil is cooled and passed through polishing filters, ultrafine membranes that remove the last microscopic particles. The result? A crystal clear liquid that won't cloud even when stored in the fridge. From the filters, the oil flows into stainless steel storage tanks holding up to 5,000 cubic meters, where it's kept under a nitrogen atmosphere, so oxygen can't oxidize the product. The bottling line is a spectacle in itself. Machines blow plastic bottles from preforms right there on the factory floor, then immediately fill them with oil, screw on caps, slap on labels, and pack them into boxes. Speed? Up to 12,000 bottles per hour on a single line, and there are several lines. In a day, the plant can bottle over 500,000 bottles. Every batch goes through lab testing: acid number, peroxide number, moisture content, clarity, taste, and smell. If even one parameter falls outside spec, the entire batch gets sent back for re-refining. The scale is staggering. A major European plant processes up to 2 million tons of sunflower seeds per year and produces around 800,000 tons of oil. Europe is one of the world's largest producers of sunflower oil, and a significant chunk of production gets exported to dozens of countries. When you're standing on the factory floor, watching that golden stream of oil continuously pouring into bottles, and outside another grain truck pulls up for unloading, you realize what a massive industry stands behind that simple bottle on your kitchen shelf. From a seed in the field to oil in a bottle, dozens of stages, hundreds of pieces of equipment, and thousands of people making sure every single drop meets the standard. And it all started with an ordinary sunflower that turned its head toward the sun somewhere in a field.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go. Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood. In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries. Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70. Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid.
Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off.
The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible. But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead.
This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries.
Every year, Japan produces millions of tons of steel, but only a fraction of it becomes the heart of what is considered a modern engineering miracle, the rails for the Shinkansen bullet trains. Imagine a furnace larger than a 5-story building, heated to over 1,500 degrees Celsius, where iron and carbon boil. This ocean of fire is transformed into rails the length of a football pitch, so perfectly straight that the smooth glide of a train at 320 kilometers per hour depends on them. But the real secret lies in how Japanese engineers fuse these rails into a continuous ribbon, up to 1.5 kilometers long. Do you want to know how they created the illusion of an endless rail without a single click-clack? Watch until the end. We are inside a vast Japanese steelworks. The atmosphere is heavy, thick with a mixture of intense heat, the smell of steel, and the deep hum of powerful machinery. Before us stands the main character of this scene, a steel-making furnace the size of a 5-story building. It resembles the mouth of a volcano, glowing a blinding white. Inside, a boiling mixture of iron and carbon churns at over 1,500 degrees Celsius. With a roar, the molten metal is poured into special molds, like a brilliant orange river of lava flowing down a mountainside. Against the scale of these immense machines, the workers look tiny. After the steel is cast, it begins to cool, transforming from a liquid into a solid, yet still intensely hot block of metal. The rolling mill is a colossal machine, something like a giant meat grinder. But instead of blades, it has heavy steel rollers that crush and stretch the metal. The deep rumble intensifies as the machine grips a red-hot billet. With a sound like a low groan, the hot steel begins to elongate, like dough for pasta, but dense and heavy. Gradually, this billet becomes longer and straighter until it finally emerges as a single continuous rail, almost 100 meters long, the length of a football pitch. The surface of such a rail must be absolutely flawless, without the slightest ripple. because if it is even minutely uneven, a Shinkansen train will not glide smoothly over it. After rolling, the rail is still incredibly hot. Steam rises from it, and you can hear a crackling sound, like water hitting a scorching hot plate. But this is its almost finished form: long, heavy, smooth, ready for inspection, grinding, and its future life. To reduce the number of joints, Japan uses a method of continuous welding, where several rails are fused into one extremely long ribbon. The welding of rails for high-speed trains like the Shinkansen is a high-precision process, with the goal of turning individual sections into a seamless track up to 1.5 kilometers long. It is this type of joint that eliminates the traditional click-clack sound as the train passes over it. The welding process occurs in several stages. The most common method is thermite welding, a reliable and visually spectacular technique. Two rails are positioned end to end, with a gap of just a few millimeters between them. The surfaces of the future joint are meticulously cleaned of any rust or contaminants. A special mold made of a heat-resistant material is then clamped around the joint. A small crucible above the joint is filled with the thermite mixture, a powder of aluminum and iron oxide. When it is ignited, a chemical reaction occurs, generating a temperature of over 2,500 degrees. The result is molten iron, which flows down and fills the gap between the rails, fusing them at a molecular level. The reaction lasts several minutes, accompanied by a hissing, crackling sound as a brilliant flame erupts above the joint. It looks like a miniature volcanic eruption. After the metal solidifies, which takes about 10 minutes, the mold is removed, and the excess metal is sheared off. The joint is then ground down to a perfectly smooth surface so that the train wheel feels no transition. The finished weld is inspected with laser measurements and ultrasonic sensors which search for any potential micro cracks. In a world where every second counts, Shinkansen engineers discovered the secret to permanence, the slab track. Instead of traditional stone ballast, they created monolithic giants from concrete. These Titan slabs can reach a thickness of 66 centimeters, the height of 2 footballs stacked on top of each other. Japanese masters also invented an ingenious solution: encapsulation units. Imagine a metal cradle that embraces the rail like a mother holds a child. These cradles not only secure the steel tracks, but also isolate them from vibration and electricity. But the most brilliant part of the system is what you cannot see. Between the concrete slabs and the foundation, the Japanese placed resilient layers that act as giant shock absorbers. Transporting the sleepers to the installation site is done in several ways. For short distances, special crane-equipped lorries are used. For longer routes, railway flatbeds. Safety during transport is critical. A single concrete sleeper must be lifted by 4 workers, highlighting their significant weight, roughly 75 kilograms per worker. For mechanized lifting, special grabs and cranes are used. On the construction site, the installation process begins with the preparation of the base. For the slab track, which is predominantly used on the Shinkansen, the sleepers are installed onto precast concrete slabs. Each sleeper is positioned with an accuracy of 6 millimeters, as even the slightest deviation can cause problems at speeds of 320 kilometers per hour. The installation is carried out by specialized crews using precision equipment. First, support points are set every 60 centimeters, the standard interval for high-speed lines. Each sleeper is then fixed to the base with special anchor bolts, 2.5 centimeters in diameter, which are driven 15 centimeters deep into the concrete slab. The process is further complicated by the need to integrate with the power supply and signaling systems. The final stage involves installing vibration insulating pads between the sleepers and the base. These rubber steel elements significantly reduce the transmission of vibrations from the trains to the surrounding structures. After the installation is complete, the entire section is tested by a special inspection train. Despite more than 120,000 trains running on the line annually, the average delay is just 36 seconds. Over half a century, the top speed has increased from 210 to 320 kilometers per hour, and the line now carries 1 million passengers a day. A new line is expected to operate at 500 kilometers per hour, with a projected journey time between Tokyo and Osaka of just 67 minutes.
Picture a warship that served for decades, armed, deployed on long voyages, drills, maybe even wars, and then one day it's no longer needed. What happens to a giant like that after its service ends? At first glance, you might think an old naval vessel just gets cut up for scrap, and that's it. But in reality, its disposal is one of the most complex and dangerous industrial operations out there, where military secrecy, environmental concerns, heavy metallurgy, toxic materials, logistics, and massive costs all collide. Because a warship isn't just tons of steel. Inside, you'll find fuel, oils, cables, electronics, hazardous materials, weapon components, specialized equipment, and in some cases, even a nuclear reactor. So decommissioning a ship after service isn't like tearing down a shed or scrapping a regular hull. It's a tightly planned industrial process where every step follows strict safety, control, and accountability protocols. Today, we're breaking down how military ships go from fleet retirement to recycled metal, and why this undertaking is so complicated and expensive. It all starts not with the cutter or shipyard, but with official fleet decommissioning. The vessel stops being an active combat unit and enters an entirely different status. But scrapping hasn't begun yet. First, the ship is prepped for transport and dismantling. Hull inspections, stability checks, towing plans, and assessments of internal compartments and external structures are completed. A key task? Preventing flooding, listing, or accidents before breakdown starts. The ship may be technically dead as a combat unit, but it's still a massive, complex structure that must reach a specialized facility safely. Only then does the transition begin from military asset to industrial recycling object. Right here, it becomes clear. Ship scrapping isn't a one-time event, but a lengthy project involving military personnel, engineers, contractors, environmental agencies, and metal recycling plants. Before they start cutting into the hull, the ship is stripped bare from the inside out. Equipment gets pulled, anything reusable is removed, and anything sensitive gets destroyed. Weapons, classified electronics, special communication systems, combat control elements all go through mandatory demilitarization.
That doesn't just mean removal, they're deliberately deformed or destroyed according to strict protocols to prevent future use. Meanwhile, some equipment might get sent to warehouses and reused on other active ships if it still holds value for the fleet. This selective dismantling saves money, but it massively complicates the whole process because the ship can't just be sent straight to the scrapyard. It has to be carefully inventoried and taken apart like one enormous collection of systems. Basically, before you can recycle the metal, you first have to separate it from an entire world of military technology that's been accumulating inside that ship for decades. Once the equipment's stripped out, one of the most critical phases begins: removing hazardous materials. Warships are packed with substances that would be serious environmental and safety threats in civilian life. We're talking residual fuel, oils, hydraulic fluids, bilge water, asbestos insulation, heavy metals, old paint, cable materials, and, on older vessels, compounds like PCBs. You can't just leave that inside and start cutting the hull with torches. First, all fluids get pumped out because cutting could trigger fires, explosions, or contaminate surrounding water. Then, specialists in protective gear remove toxic materials while constantly monitoring air quality. On large vessels, these operations are done zone by zone, section by section, keeping the process under control. In other words, the ship first gets cleaned like a hazardous industrial site, and only then becomes a candidate for mechanical dismantling. At this stage, mistakes cost dearly. Now we're talking not just about metal, but about people's health and environmental risks. Once a ship's been stripped of its dangerous guts, the actual dismantling of the hull begins. But it's not just chaotic cutting. The hull gets carved up in stages to keep the structure stable and prevent multi-ton sections from collapsing uncontrollably. The process breaks down into tiers. First come the primary cuts. The hull and superstructure get divided into large blocks, sized based on crane capacity and yard layout. Then those blocks move to protected zones and get cut further into panels, beams, and smaller pieces. After that comes tertiary processing, sorting and prepping the steel for sale, melting down, or direct reuse. All of this demands precise sequencing because a ship is a massive hollow structure where shifting loads can trigger collapse. So scrapping is essentially controlled demolition, governed by engineering math. What matters isn't just the force of the cut, but understanding how a multi-thousand-ton hull will behave as the structure weakens. The whole economic point of this operation is recovering materials, steel above all. A warship is basically a giant stockpile of metal, and most of its mass can be recycled. The bulk is steel, hull plating, bulkheads, structural members, superstructure. Beyond that, there's non-ferrous metal, copper wiring, brass and bronze fittings, aluminum parts, cable runs, and other valuable components. Non-ferrous metals are pulled out with extra care because they fetch way more than ordinary scrap steel. Some plate and sections go straight back into manufacturing or get reworked at rolling mills. The rest goes to the smelter. From an industrial standpoint, it's a major source of secondary raw material, since recycling shipboard steel takes far less energy than making fresh steel from ore. So, scrapping ships isn't just about retiring the old fleet. It's a huge channel for putting metal back into the economy, even though the process itself stays extremely expensive and labor-intensive. Nuclear-powered vessels, mainly nuclear submarines and certain large warships, occupy a category entirely their own and can't be scrapped like conventional ships. First, spent nuclear fuel is removed from the reactor and placed in specially shielded containers and storage facilities. Then, the reactor compartment itself isn't cut open like ordinary scrap metal. It's cut out in one piece, sealed, and transported to long-term storage or controlled burial sites. This isn't just heavy industry anymore. It's where nuclear safety, government oversight, and extremely expensive specialized infrastructure all intersect. If the sub had missile compartments, their disposal may also fall under separate international restrictions tied to arms control treaties. In the end, a nuclear vessel after service becomes not just a disposal job, but a highly complex government project where metallurgy is only a small piece. Everything else is nuclear safety, transportation, storage, and oversight, stretching decades into the future. So why is this industry considered one of the toughest and most dangerous? Because it combines nearly every industrial hazard at once. There's fire and explosion risk from cutting into old fuel systems, collapse risk from multi-ton sections shifting unexpectedly, toxic exposure from asbestos, heavy metals, and decades-old chemicals, environmental contamination of soil, groundwater, and air without proper controls, plus serious legal complexity, international hazardous waste regulations, documentation requirements, site certification, material tracking, and safe transport logistics. That's why modern disposal programs need far more than just cutters with torches. They need full infrastructure. Detailed hazardous substance inventories, sealed containment pads, drainage and filtration systems, continuous reporting, and strict government oversight. Even then, scrapping military ships often loses money or barely breaks even on scrap metal sales alone. Too much investment goes into prep work, safety protocols, careful dismantling, and regulatory compliance. When you look at the whole process from start to finish, one thing becomes clear. Scrapping warships after their service isn't the end. It's the ship's final industrial transformation. First, it's decommissioned from the fleet, then stripped of weapons and classified equipment, cleared of fuel, oils, and toxic materials. Then the hull is cut down piece by piece, metal sorted and returned to industrial circulation. And if we're talking about nuclear vessels, you add decades of monitoring reactor compartments and radioactive materials. Essentially, scrapping a ship is civilization in reverse. Everything built as a symbol of strength and military power now safely broken down into raw materials, waste, hazardous fractions, and reusable components. And that's where the real weight of this industry lies. It doesn't deal with new products. It deals with massive machines from the past, turning them into resources for the future. That's why scrapping warships isn't just cutting steel. It's a complex industrial finale to an entire era of service for each combat vessel.
Deep beneath southwestern Poland, in the Lower Silesia region, lies one of the planet's largest copper deposits. 1.5 billion tons of ore, 21 million tons of pure copper, enough reserves to last several more decades. Here, at depths reaching 4,600 feet, that's 140 stories down, operates the company KGHM Polska Miedź. Every year, it brings to the surface nearly 400,000 tons of copper, the only European mine in the global top 10 of largest copper producers. But that's not all. Along the way, they extract silver in such volumes that KGHM is the world's #1 producer of this metal. Gold, nickel, lead, rhenium, selenium, platinum from a single ore. Today, we're descending into this underground world, following copper's entire journey, from black rock nearly a mile down to shining wire, without which every factory, every phone, and every electric vehicle on the planet would grind to a halt. Poland's copper story begins in 1957. Geologist Jan Wojciechowski was drilling a borehole near the town of Złotorysia when he hit an ore body so massive he didn't trust his own instruments at first. 43 miles long, 12 miles wide, the Legnica Głogów copper belt turned out to be one of the largest deposits on Earth. By 1961, they'd sunk the first shaft. Today there are 3, Rudna, Lubin, and Polkowice-Sieroszowice. Rudna is the biggest. Its levels stretch underground across 36 square miles. That's roughly the entire center of Warsaw. The ore sits in 3 types of rock: sandstone, shale, and dolomite. Layers of copper mineralization, chalcocite, bornite, chalcopyrite, plunge downward like pages of a giant book, tilted at an angle to the horizon. Average ore body thickness, 3 to 10 feet. Copper content, 1.5%. Which means, to get 1 ton of metal, you need to haul up and process 67 tons of rock. Before mining can start on a new level, you need to sink shafts, vertical tunnels about 26 feet across. Here's where things get tricky. Aquifers. When they drilled the first shafts back in the 60s, the rock was saturated with water under massive pressure. Standard drilling? Instant flooding. KGHM engineers developed a unique solution: freeze the rock solid. Around the future shaft, they drilled 8-inch boreholes in a circle, pumped in calcium chloride chilled to -22 Fahrenheit. 3 to 6 months later, the water in the rock around the shaft turned to ice, creating an ice wall several yards thick. Only then could they start drilling the shaft. Today, the new GG1 shaft in Polkowice, commissioned in 2024. Depth, 4,416 feet. That's the deepest mining structure in Poland and the largest underground project in European non-ferrous metallurgy. At 4,400 feet down, the rock temperature hits 104 degrees Fahrenheit. Without air conditioning, people wouldn't survive. KGHM built a massive underground cooling system. Refrigeration units pumping over 50 megawatts chill air down through ventilation shafts. Miners work at the face in temperatures around 82 to 86 degrees. The mining method? Room and pillar. Miners use specialized low-profile drill rigs, just 5 feet tall because the ore seam is the same thickness, to drill holes into the roof and walls of the working face. These holes, up to 13 feet deep, get packed with explosives. After the blast, rock collapses into the chamber. But it's not that simple. Rock pressure at 4,400 feet? That's 8,000 tons per square meter. Rock under that kind of pressure behaves unpredictably. KGHM created a unique seismic monitoring system. Hundreds of sensors throughout the mine detect the slightest tremors. A computer analyzes data in real time and warns of rock burst risk minutes before it happens. Over 60 years, this system has saved thousands of lives. The blasted ore is loaded by load haul dump machines, massive diesel-powered scoops with remote control. The bucket capacity is 10 cubic meters, about 25 tons of ore in a single scoop. The machine hauls the ore to a transfer point, where it's dumped into an ore pass, a vertical shaft 5 feet in diameter, through which the ore falls downward by gravity to a level with conveyors. The conveyor system in the Rudna mine spans over 300 miles of belts. The ore moves toward the shafts at 13 feet per second. At the base of the hoist shaft, it accumulates in a bin with a capacity of 1,000 tons, from which it's loaded in batches into the hoisting vessel, the skip. The skip, with a 30-ton capacity, rockets upward at 52 feet per second. That's almost 40 miles an hour. The climb from a depth of 3,300 feet takes 70 seconds. Each hoist shaft delivers between 25 and 30,000 tons of ore to the surface every day. On the surface, the ore is hauled to the processing plant. Here's where the first bit of magic happens. Copper content in the ore? 1.5%. That's way too low for smelting. We need to bump it up to 23%. The ore gets crushed in cone crushers down to half-inch chunks. Then it heads into ball mills, horizontal drums about 16 feet across packed with steel balls. The drum spins, the balls tumble, and they grind the ore into powder. Particles smaller than 0.04 inches. This finely ground slurry gets pumped into flotation machines, rectangular tanks holding up to 26,000 gallons each. Special reagents get added, xanthates and frothing agents. Compressed air bubbles up through the slurry from below, creating millions of tiny bubbles. The reagents make the surface of copper minerals hydrophobic. They repel water. Air bubbles stick to the copper particles and drag them to the surface as foam. The waste rock sinks to the bottom. Scrapers skim off the foam. That's copper concentrate with 23% copper content. One flotation cycle pulls out 88 to 90% of the copper from the ore. The concentrate ships to the copper smelter in Guoguf, one of KGHM's 2 plants. They use a single-stage flash smelting technology. The concentrate gets dried to 0.3% moisture and fed through a burner into the smelting furnace shaft. At the same time, they blast oxygen in. Not air, but pure industrial oxygen at 95% purity. Suspended concentrate particles ignite in the oxygen stream instantly, in fractions of a second. Temperature in the reaction shaft hits 2,550 degrees Fahrenheit. Copper sulfides oxidize, releasing massive amounts of heat. The reaction's nearly self-sustaining, requiring very little additional fuel. At the bottom of the settling chamber, 2 melts separate. Matte, a molten copper sulfide at 65% copper content, and slag, a silicate melt with waste rock. The slag gets drained and processed separately. They still extract copper from it using additional flotation. The matte goes to the converter. Oxygen gets blown into the converter with the molten matte. A second oxidation happens. Sulfur burns off. Iron oxidizes and shifts into slag. What's left is blister copper, 98.5% pure. But we're not done yet. The blister copper gets cast into anodes, plates 3 feet wide, 3 feet tall, 2 inches thick, weighing 660 pounds each. They're hauled to the electrolytic refining shop. Here, tanks 20 feet long, filled with a solution of copper sulfate and sulfuric acid. Into each tank they hang alternating anodes and thin stainless steel starter sheets. A direct current runs through the solution, about 60 amps per square foot. Copper dissolves from the anode, travels through the electrolyte, and deposits onto the starter sheet. After 12 to 14 days, a cathode builds up on the sheet, a plate of pure copper weighing 130 pounds at 99.99% metal content. That's grade A, the highest category of exchange copper on the London Metal Exchange. Everything else, gold, silver, platinum, palladium, selenium, settles to the bottom of the tank as anode slime. It gets collected and sent to the precious metal shop. From this slime, KGHM pulls 1,200 tons of silver every year, more than any other producer in the world. Some of the cathodes get remelted and rolled at the Sardinia plant into copper wire rod, wire about 1/3 of an inch in diameter. This is the key intermediate product for the cable industry. The wire rod gets wound into coils weighing 5 tons and ships out to cable factories across Europe. All told, nearly 400,000 tons of copper flow from Polish mines through all these stages every year. 24 million tons of ore hauled up from below. 34,000 workers. All of it, for a metal without which modern civilization simply couldn't exist. Where does all this copper go? First, power. Every cable, every wire, every transformer winding, copper. The entire electrical infrastructure of the planet runs on this metal. Without it, you can't transmit a single watt of energy from the power plant to your outlet. Second, construction. Every modern home hides between 220 and 440 pounds of copper pipes and wiring. Water supply systems, heating, air conditioning, copper everywhere. Third, electronics. Your smartphone contains about 1/2 ounce of copper. Not much? Except the world sells 1.5 billion phones a year. Computers, servers, circuit boards, the copper traces are visible to the naked eye. Fourth, transportation. A typical gas-powered car contains 51 pounds of copper. An electric vehicle? 132 to 183 pounds. Power cables, motor windings, battery bus bars. Fifth, renewable energy. One 3-megawatt wind turbine uses about 4 tons of copper. Solar panels, copper bus bars collecting current. The world is shifting to green energy, and every step of that transition increases copper demand. Forecasts predict demand will grow 70% by 2050, which means those KGHM mines beneath Polish soil will keep running non-stop for decades to come. I'm standing at the shaft of the Rudna mine. The hoist roars as it delivers another skip full of ore. 30 tons of black rock that'll become wires inside Danish wind turbines in a few weeks. Cables under the English Channel. Windings in Berlin subway motors. Connectors and servers storing your cloud photos. Copper is the blood of technological civilization. It flows invisibly through everything that runs on electricity. And every single gram of this blood begins its journey right here, in the darkness beneath Polish soil, where people in hard hats work a mile underground to make our lives possible. If you found this interesting, hit that like button. Drop a comment and let me know. Did you know Poland is the world leader in silver production? And subscribe. This is where we open up the industries behind every object in your life.
Every year, millions of components, tons of alloys, and hours of high-precision calculations come together in one deadly symphony. This missile isn't simply metal. It's a moving brain, an engine, and coded death that flies over 1,000 miles whilst hiding from radars. How is a secret capable of changing the course of battle born from hundreds of metal sections? Stay until the end. I'll reveal one production secret that few people know. Want to know what's hidden inside? Imagine lasers, press forming, robots welding components in clean rooms with tolerances of 1/100th of a millimeter. All of this for a single flight. Designing the Tomahawk missile is a symphony of formulae and calculations. Engineers don't simply draw a body. They solve equations that must allow it to cut through air with centimeter precision. Every surface and curve is calculated in computer-aided design systems and undergoes aerodynamic modeling. The goal is to create a body that will fly over 1,000 miles, remaining almost invisible and stable at an altitude of 100 feet or 160 feet above ground. In digital simulations, they test wind force, resistance at speeds of 550 miles per hour, and the effects of rain. One mistake, and instead of a precise strike, the missile will hit a barn on the outskirts. Body components, electronics, payload, all of this fits into nearly 20 feet of length and 20 inches in diameter. It's genuine artistry, packaging death with such elegance. Only after dozens of virtual tests does the missile move to the production phase. After the calculation stage, drawings are transferred to the real world, to factories with high-precision equipment. Here, not a single crack nor an extra micron can be permitted. The missile body, over 18 feet long, is assembled from sections manufactured from high-quality aluminum alloys, sometimes with titanium added. This is an aerodynamically refined cylinder that must withstand overloads, vibration, and temperature fluctuations. Blanks are cut with laser or water jet installations with tolerances up to 1/100th of a millimeter. Then press forming. Large hydraulic machines bend metal like fabric. Welding is conducted in an inert atmosphere, often by robotic arms, to avoid even the smallest oxygen inclusions. Technologists check welds hourly with ultrasound and apply special anti-corrosion coatings. Even the inscription Tomahawk isn't applied as decoration, but as a marker of version and the missile's history. For the cruise missile, a compact Williams F-107 turbofan engine is used, similar to a small aircraft engine but adapted for high maneuverability. Turbine blades are manufactured from nickel alloys in a form resembling sculpture more than a technical component. They're cast using precision casting methods, then polished to mirror finish to give air minimal resistance. The compressor and combustion chamber are a complex mosaic of dozens of elements. Each component is checked for seal integrity because any micro leak and the missile simply won't launch. The nozzle is manufactured from heat-resistant alloy capable of withstanding flame temperature without deformation. Engine assembly occurs in clean zones similar to laboratories. Workers in sterile suits, stable temperature and humidity. After assembly, each engine undergoes individual ignition testing in a test chamber. The engine simulates genuine flight, but not in the sky, on a concrete table with sensors. Tests last for hours. They check stability of revolutions, temperature, fuel consumption, and even noise, because volume could betray the missile's position. And only when the engine has sung its song is it integrated into the Tomahawk's body, as though breathing life into it. When the body is ready and the engine installed, the missile still isn't ready to fly. It knows nothing yet. It must be taught. Inside is a genuine brain, a node of microprocessors, sensors, antenna, and memory blocks. But the moment it receives its first power signal, a machine consciousness awakens within it. Its navigation is an entire ensemble of systems. Inertial sensors maintain course even if the signal disappears. GPS correction helps prevent deviation from the route. But most important is its ability to see. Special cameras analyze terrain, comparing every hill or bridge with the map stored in memory. If there's forest beneath it when there should be field, it knows something's wrong. It makes decisions. The control system works like nervous tissue, flexible and infallible. Small stabilizers and control surfaces respond to every tilt and altitude change. And finally, the most important thing, that which transforms the missile from an engineering creation into a weapon, its warhead. It looks simple, a cylinder hidden in the body. But inside is explosive capable of penetrating concrete and destroying equipment. It's manufactured separately under conditions of absolute sterility. Not a single spark. This is work where mistakes aren't corrected, they're not permitted. Before final assembly, each component undergoes inspection, X-ray, vibration tests, electronic diagnostics, and then assembly. Quietly, step by step, as though someone's assembling not a weapon but an antique clock that must strike just once. And when everything's connected, the missile silently settles into its container. It doesn't glow, doesn't flash, it simply waits. Its flight lies ahead, but it's already ready.
Imagine a part so perfect it can spin for 30 years without stopping. From tiny balls just 1/8 of an inch across to giants 30 feet tall holding up wind turbines, bearings are a $120 billion a year industry. But their life begins in absolute chaos. Massive explosions, hellish fire, pressure that could crush a tank. How does raw metal become the heart of perfection? Today you'll follow the complete journey, from a quarry blast to the perfect ball spinning at 10,000 revolutions per minute. If you want to see how chaos turns into precision, subscribe to the channel. Here we show the manufacturing that builds our world. It all starts with a roar that shakes the ground for miles around. In the giant quarries of Australia and Brazil, iron ore hides in layers of rock hundreds of feet thick. Geologists turn the quarry into a chessboard. They drill boreholes 60 to 100 feet deep. Borehole diameter, 10 inches. Distance between boreholes, 16 feet. 1 square mile, 1,000 boreholes. Into each they pour explosives, a mix of ammonium nitrate and diesel fuel. Ratio 94 to 6%. Charge weight per borehole, 650 pounds. Detonation happens with millisecond delays. First borehole explodes. 20 milliseconds later, the second. 40 milliseconds, the third. The wave rolls across the entire field. In 10 seconds, they detonate 200 boreholes. They blast 3.5 million cubic feet of rock, energy equivalent to 110,000 pounds of TNT. But this isn't random chaos. This is planned destruction. Chunks of rock shoot 150 feet into the air. They fall. Dust rises over half a mile into the sky. When it settles, instead of a mountain, there lies 2 million tons of crushed ore. Giant excavators roll onto the site. The excavator bucket? 1,400 cubic feet. That's the volume of a small apartment. The bucket weighs 28 tons. One scoop? 100 tons of rock. They load it into dump trucks. Hauling capacity of each truck, 360 tons. Wheel height, 13 feet. Diameter, 11.5 feet. Weight of one wheel, 5 tons. Engine, 3,500 horsepower. Fuel consumption, 35 gallons per mile. The dump truck hauls ore to the crusher. Distance, 9 miles. Speed, 25 miles per hour. Travel time, 20 minutes. In one day, a single truck makes 30 trips, hauls 10,000 tons. 20 excavators and 60 dump trucks work the quarry. They move 300,000 tons of ore per day. That's 100 million tons a year. Crushing. Ore enters the jaw crusher. The crusher's mouth, 13 feet wide. The jaw weighs 120 tons. Jaw stroke, 12 inches. Oscillation frequency, 200 strikes per minute. Drive power, 1.5 megawatts. The crusher pulverizes yard-wide rocks into 8-inch chunks. Throughput, 2,000 tons per hour. From the jaw crusher, ore moves to the cone crusher. The cone spins inside the bowl at 150 revolutions per minute. Gap between cone and bowl, 1 inch. 8-inch pieces become 1-inch pieces. Then the ball mill. Cylinder 20 feet in diameter. Length 26 feet. Inside steel balls. Ball diameter 4 inches. Weight per ball 9 pounds. Total balls 50,000. Combined weight 200 tons. The mill rotates at 18 revolutions per minute. Balls drop from 6.5 feet. Impact grinds ore to powder. Particle size after milling, 0.04 inches. The thickness of a human hair. Thickness. Flotation enrichment. Ore powder gets mixed with water, creates a slurry. Solid concentration, 30%. Add reagents. Potassium xanthate, 7 ounces per ton of ore. Pine oil, 1.8 ounces per ton. Xanthate makes iron particles hydrophobic. They repel water. Pour the slurry into the flotation machine. Tank volume, 13,000 gallons. Air pumps in from below. Pressure, 30 pounds per square inch. Flow rate, 10,000 cubic feet per hour. Air forms billions of bubbles 0.2 inches across. Bubbles stick to iron particles. Lift them up. Foam forms on the surface. Reddish gray. Dense. Iron content in the foam, 67%. Waste rock sinks to the bottom. Gets pumped out and dumped in tailings. Foam scraped off with blades, sent to filtration. Vacuum filter sucks out the water. Leaves a damp mass. Moisture content, 9%. That's concentrate. Gets turned into pellets. Pelletizing. The concentrate goes to a disc pelletizer. The disc is 15 feet across, tilted at 45 degrees, spins at 15 revolutions per minute. Powder feeds onto the disc. Water's added, 3% by weight. Centrifugal force rolls the powder into balls. Pellets come out half an inch in diameter, give or take a 1/16 of an inch. The pellets roll off the edge onto a conveyor. Output? 300 tons an hour. 1,000,000 pellets every hour. The pellets head to the kiln. Firing temperature, 2450 degrees Fahrenheit. 20 minutes in the heat. The pellets turn rock hard. Crushing strength, 3,500 psi. Now they're ready for the blast furnace. Blast furnace smelting. Pellets are loaded into the blast furnace. The furnace stands 105 feet tall. The throat diameter, 40 feet. The hearth diameter, 26 feet. Furnace volume, 42,000 cubic feet. Loaded in layers. Pellet layer, 3 feet. Coke layer, 20 inches. Limestone layer, 8 inches. Hot air blasts in from below. Temperature, 2,200 degrees. Pressure, 60 pounds per square inch. Flow rate, 100,000 cubic feet per minute. The coke burns, carbon monoxide releases. It strips the iron from the pellets. Temperature in the hearth, 3,600 degrees. The iron melts, flows downward, pools in the hearth. Every 4 hours they tap the pig iron. They open the tap hole. Pig iron pours out like a river of fire. Temperature at 2,700 degrees. Color, bright orange. One tap, 300 tons. In 24 hours, the furnace produces 2,000 tons of pig iron. The pig iron contains 4% carbon. That's way too much. Pig iron's brittle. Needs converter smelting. Steel production. They pour pig iron into an oxygen converter. The converter holds 350 tons. A lance descends from above. The lance is 20 inches across. Pure oxygen blasts through the lance. Pressure hits 175 pounds per square inch. Flow rate, 18,000 cubic feet per minute. Jet velocity, 1,300 miles per hour. That's twice the speed of sound. Oxygen oxidizes the carbon burns. Turns into carbon dioxide. Flame shoots out the converter's mouth. Flame reaches 30 feet high. Temperature hits 3,600 degrees. The process takes 20 minutes. Carbon content drops from 4% down to 0.7%. This is bearing steel. Grade designation SAE 52100. Chromium content 1.5%. Chromium provides hardness and wear resistance. They pour the steel into a ladle, from the ladle into molds. Out come ingots, blanks weighing 5 tons each. Ingot dimensions, 3 feet by 3 feet by 6 feet. Rolling and machining. Ingots are heated in a furnace to 2,200 degrees Fahrenheit. Rolled on a mill. Rollers 40 inches in diameter. Rolling force 2,000 tons. The ingot becomes rods 4 inches across. Rod length 20 feet. Rods are cut into blanks 8 inches long. Blanks are heated to 1,560 degrees. Stamped into rings on a press generating 1,200 tons of force. You get a ring with an outer diameter of 4 inches. Inner diameter, 3.1 inches. Height, 0.8 inches. Rings undergo heat treatment. Heated to 1,540 degrees. Held 30 minutes. Quenched in oil at 140 degrees. Cooling rate, 540 degrees per second. Tempered at 360 degrees for 2 hours. Hardness after heat treatment, 62 Rockwell. Then, grinding. The ring is clamped in a lathe chuck. The abrasive wheel spins at 100 feet per second. Removes a metal layer 0.004 inches thick per pass. Surface roughness, 0.08 millionths of an inch. That's 10 times smoother than glass. Deviation from roundness, no more than 0.08 thousandths of an inch. Balls are made by cold heading. Wire 1/2 inch in diameter is cut into 1/2 inch segments. Each segment is clamped between two dies. Pressure, 2 tons. The segment deforms into a sphere. You get a rough ball? It's ground between 2 cast iron discs. The discs rotate toward each other. Speed, 200 revolutions per minute. Between the discs, abrasive paste. Grit size, 40 micrometers. Grinding takes an hour. The ball shrinks by 0.012 inches. Final diameter, 0.46 inches. Deviation, plus or minus 0.004 hundredths of an inch. Sphericity, 0.08 thousandths. Roughness, 0.02 millionths of an inch. Bearing assembly. Inner ring, outer ring, 17 balls. Brass separator, lithium grease. Bearings done. It'll spin for 30 years, 1 billion revolutions.
The metal that powers the planet. Every second, 3 electric cars are sold worldwide. Every hour, 50,000 smartphones roll off production lines, and all of them depend on one element: lithium, the white gold of the 21st century. The lightest metal on Earth, which you'll never see in its pure form because it instantly explodes on contact with water. But it's what fires up your phone, drives electric vehicles, and will power humanity's future. How do salt lakes high in the Andes transform into an energy source for billions of devices? You'll discover why lithium is called white gold, how giant evaporation pools the size of a city work, and why a real geopolitical war has erupted over this metal. Watch until the end. The finale will reveal what's behind every percentage point of your smartphone's battery. This is the story of a metal that changed the world in just 20 years.
Lithium's story began in 1817 on a tiny Swedish island called Uto. A young chemist, Johann August Arfwedson, was analyzing a rare mineral called petalite when he discovered something strange. This was a metal, but incredibly light, lighter than water. Arfwedson named it lithium from the Greek word lithos, stone. Ironic, right? A stone that floats. In 1821, British chemist William Brand first isolated pure metallic lithium through electrolysis of molten salt. What he saw blew his mind. A silvery white metal so soft you could slice it with a knife like butter, and so light that a chunk of lithium actually floats on water. But that contact with water, it lasts maybe a second. Lithium instantly explodes into a violent reaction, hissing, smoking, and it can catch fire. For 150 years, lithium was just a lab curiosity. They used it in medicine to treat mental disorders, in glass and ceramic production. But everything changed in the 90s. In 1991, Sony released the first commercial lithium-ion battery. It was a breakthrough. Before that, batteries were heavy, short-lived, drained fast. Lithium-ion batteries turned out to be 3 times lighter and held their charge way longer. The portable electronics revolution began. Cell phones became compact, laptops became light, cameras became long-lasting. But the real explosion in demand happened in the 2010s when electric vehicles hit the market. Tesla, Nissan, BMW all built their cars on lithium-ion batteries. One electric vehicle requires 130 to 175 pounds of lithium. For comparison, a smartphone contains just 1/10 of an ounce. Demand for lithium jumped from 30,000 tons in 2010 to 550,000 tons in 2023, and that's just the beginning. Forecasts predict 3 million tons by 2030. Lithium transformed from a rare lab element into a strategic resource more important than oil. But where do you get that much lithium? On Earth, lithium isn't rare. It's the 33rd most abundant element.
But here's the thing, concentrated deposits, not so common. There are two main sources, hard rock and salt brines. Hard rock means spodumene, a rare mineral mined in Australia, Canada, Zimbabwe, but the future? It's in the brines. High up in the salt lakes of South America, at 10 to 13,000 feet above sea level, lie the planet's largest lithium reserves. It's called the Lithium Triangle, Bolivia, Chile, and Argentina. Bolivia's Salar de Uyuni is the biggest salt flat on Earth, 4,000 square miles of blinding white salt under an endless sky. Looks like a massive frozen lake. Beneath that salt crust, brine, containing about 9 million tons of lithium. That's half the world's reserves. Chile's Atacama, the driest desert on the planet. Here too, massive lithium deposits hide in underground brines. Now, let's break down how lithium is actually extracted from these salt lakes. The process looks almost magical. First, they drill wells anywhere from 65 to 330 feet deep. Powerful pumps suck up brine from these wells, a salty liquid similar to seawater, but way more concentrated. A single liter of this brine contains anywhere from 300 to 1,500 milligrams of lithium. For comparison, seawater has just 0.17 milligrams per liter. The pumped brine gets channeled into massive evaporation ponds. Picture this, artificial lakes covering dozens of hectares. From above, they look like giant colored squares, blue, turquoise, green, yellow. The color depends on mineral concentration and microorganisms. These ponds are arranged in a cascade, like giant steps. The brine flows from one pond to the next, and at each step, the magic of evaporation happens. Under the scorching sun of the high-altitude desert and relentless winds, the water evaporates, slowly, month after month. The Atacama receives less than a millimeter of rainfall per year, but the sun shines 300 days a year, perfect conditions for evaporation. The lithium concentration in the brine gradually increases. First, unwanted salts precipitate out of the solution, sodium chloride, sulfates. They're collected and removed. The process takes 12 to 18 months. Yeah, you heard that right. Over a year just waiting for the sun to do its work. During this time, the lithium concentration grows by roughly 20 times. What started as a weak brine transforms into a thick, oily solution containing about 6% lithium. The brine turns amber yellow, almost like honey. It's pumped into specialized tanks and shipped to a chemical plant. Here begins the final stage of transforming salt water into white gold. At the plant, concentrated brine is treated with sodium carbonate, basically baking soda. A chemical reaction happens and a white precipitate crashes out of solution, lithium carbonate. It's not the metal yet, but it's a crucial compound. The precipitate gets filtered, washed, dried. What you end up with are fine white crystals, like powdered sugar. That's why lithium's called white gold. It actually is white. Lithium carbonate gets bagged up and shipped all over the world. Most of it goes to China, Japan, South Korea, wherever batteries are made. But that's not the end of the road. To make batteries, you need lithium hydroxide. Lithium carbonate gets dissolved in water, treated with calcium hydroxide. You get a solution of lithium hydroxide, which then gets evaporated. What remains are white crystals of lithium hydroxide, the final product, ready for manufacturing battery cathodes. The whole cycle, from pumping brine to getting the finished product, takes about 2 years. There's another method for extracting lithium, from hard rock deposits. In Australia and China, they mine spodumene, a mineral that contains lithium. They blast the rock, crush it, grind it into dust. Then they heat it to 1900 degrees Fahrenheit in massive rotating kilns. At that temperature, the spodumene changes its structure, becomes more reactive. The roasted rock gets mixed with sulfuric acid.
a violent reaction kicks off, releasing heat and toxic gases. The lithium moves into a lithium sulfate solution. This solution gets purified of impurities, treated with sodium carbonate. Lithium carbonate precipitates out, the same product as from the brines. But this method is way more energy intensive and expensive. You need high temperatures, massive volumes of chemicals, tons of waste gets generated. That's why the future belongs to brines. Even though right now about 60% of the world's lithium comes from hard rock, the balance is gradually shifting towards salt lakes.
Now let's look at where all this extracted lithium goes. 75% of global production goes into batteries. A lithium-ion battery is a complex device. Inside are two electrodes, a cathode made of lithium oxide with cobalt or manganese, and an anode made of graphite. Between them is an electrolyte containing lithium salts. During charging, lithium ions move from the cathode to the anode and slide between the graphite layers. During discharge, they move back, and this flow creates an electrical current. Brilliant simplicity. Lithium is ideal for this because it's the lightest metal capable of giving up electrons. A single lithium atom weighs just 7 atomic units. For comparison, lead weighs 207. That's why lithium batteries are so light and energy dense. A modern Tesla Model 3 electric vehicle contains about 24 pounds of pure lithium in its 1,060-pound battery. This battery can travel over 300 miles on a single charge. Beyond batteries, lithium is used in ceramics and glass production. It lowers melting temperatures and makes materials stronger. In metallurgy, lithium gets added to aluminum alloys, makes them lighter and tougher. In nuclear power, lithium produces tritium. In medicine, lithium carbonate is still used to treat bipolar disorder, stabilizes mood. Global lithium production in 2023 hit around 130,000 tons of pure metal equivalent. The major producers, Australia, 40%, Chile, 25%, China, 14%. Lithium prices rocketed from $5,000 per ton in 2020 to $80,000 in 2022, then crashed to $30,000. The market's volatile because demand is growing faster than supply. A real geopolitical battle has erupted over lithium. China's buying up deposits worldwide. The US is trying to build its own supply chain. Europe's hunting for alternative sources. And just like that, having journeyed from salt lakes high in the Andes through 18 months of evaporation under the merciless desert sun, through chemical plants and the most complex purification processes, lithium emerges into the world, the white gold of the 21st century, the lightest metal that powers modern civilization. This is the story of how humanity learned to turn salt water from ancient lakes into energy for billions of devices. Every time you charge your smartphone, get into an electric vehicle, or fire up your laptop, remember, inside beats a heart made of lithium, the metal for which we mine deserts and drain salt flats. The metal behind the energy revolution and the move away from oil. The metal without which the future of humanity is unimaginable. White gold extracted from snow-white salt lakes to power the planet with the energy of tomorrow. Lithium isn't just an element on the periodic table. It's the key to a future that's already here.
Every rock you hold in your hands could be hiding miles of wire. Sounds insane, but it's true. Copper ore, this gray-green boulder, holds millions of tons of metal that powers every city on the planet. Every wire in your home, every cable underground, every power line stretching across continents. It all started with a chunk of dull rock that got blasted, crushed, and melted at 2200 degrees. Humanity extracts 25 million tons of copper every year. That's the weight of 4,000 Eiffel Towers. Each ton requires blasting 100 tons of rock, drilling hundreds of feet deep into the earth, processing mountains of stone, And all for a metal that makes up less than 1% of the ore's mass. How do you extract red metal from gray rock? Metal that conducts electricity better than anything else on Earth. How do pits nearly a mile deep give birth to wires that light up megacities? Stick around till the end. You'll see how rock becomes the energy of civilization. Chuquicamata, northern Chile. The Atacama Desert, the driest place on Earth. Home to the planet's largest open-pit copper mine. Depth, 3,300 feet. Width, 2.5 miles. Length, 3 miles. A wound in the Earth's crust, visible from space. Excavators the size of a 3-story building gnaw at rock around the clock. Each bucket, 700 cubic feet. In 1 hour, a single excavator tears out 1,000 tons of ore. Bell AZ dump trucks with wheels 13 feet high haul 300 tons per trip. The road out of the pit, a serpentine stretch 12 miles long. Trucks spiral upward for an hour just to reach the surface. Chile produces 6 million tons of copper a year. That's 28% of the global market. Peru delivers 2.5 million tons. China mines 1.5 million but consumes 14 million. The rest it buys. The US produces 1,200,000 tons. Russia, 700,000. Copper is a strategic resource. Without it, no power grids, no communications, no electronics. Countries fight over deposits more quietly than they do over oil, but no less fiercely. Mining starts with explosions. 100-foot-tall drill rigs bore 12-inch diameter holes 65 feet deep. The well pattern is calculated to the inch. Distance between holes, 16 feet. Each one gets packed with ammonium nitrate mixed with diesel fuel. ANFO, the cheapest explosive there is. One charge, 650 pounds. A single bench takes 400 tons of explosives. Detonation controlled by electronic timers. Each hole blows with a 10-millisecond delay. That creates a destruction wave that fractures the rock without throwing it far. The blast lasts 3 seconds. Sound like an earthquake carries 20 miles. The ground heaves. A 1,000-foot column of dust rises from the pit. When the dust settles, you're looking at 2 million tons of fractured rock. Excavators move in. 24 hours to haul it all out before the next blast. The conveyor never stops. Blast, haul, drill new holes. Blast again. The pit grows 65 feet deeper every year. "6,000 years ago, on the island of Cyprus, people found a strange stone. Green, heavy, with a metallic sheen on the break. When they threw it into the fire, the stone melted and a red liquid flowed out. As it cooled, it turned into metal, soft, flexible, shiny. The ancients called it cuprum, after the island of Cyprus. They made knives, axes, jewelry from copper. But the major discovery happened in 1831. Michael Faraday created the first electric generator. Turns out copper conducts electricity better than any affordable metal. 6 times better than iron. 1.5 times better than aluminum. Only silver beats it, but that's way too expensive. Copper became the perfect conductor. In 1879, Thomas Edison built the first power station on Pearl Street in New York. Copper wires stretched through the streets. Cities began to glow at night. The era of electrification had begun. Demand for copper exploded. What was once used for coins and statues became the backbone of energy. Quarries expanded. Mines went miles deep. Humanity started devouring copper by the ton. The 20th century transformed copper into civilization's circulatory system. Every house requires 440 pounds of copper. Wiring, pipes, radiators. One car, 50 pounds of copper in the alternator, starter, wiring. One wind turbine, 9,000 pounds of copper in the generator windings. A Tesla factory for battery production, 22 million pounds of copper annually. A power transmission line across Siberia, 660 million pounds of copper and thousands of miles of wire. By the start of the 21st century, humanity was mining 33 billion pounds a year. By 2020, 55 billion, a 60% increase in 20 years. The reason? Electrification of developing countries. India's building new cities. China's laying high-speed rail. Africa's installing solar panels. Copper's needed everywhere. The problem is rich ores are running out. Ore used to contain 5% copper. Now, 0.5%. To extract 1 ton of metal, you need to process 200 tons of rock. Pits are getting deeper, processes more complex, cost higher, but demand's growing faster. Ore from the pit heads to the processing plant. This is where chemistry and physics kick in. First step, crushing. Jaw crushers grind refrigerator-sized rocks down to 4-inch chunks. Cone crushers pulverize them to gravel. Ball mills turn gravel into sand. The mill's diameter, 26 feet, length, 40. Inside, steel balls weighing 110 pounds each spin around. They pound the ore, grinding it to powder. After 8 hours of rotation, the ore becomes dust. This dust gets mixed with water, creating slurry. It flows through flotation machines. These are giant tanks with air pumped in from below. Air bubbles get coated with flotation reagents, chemicals that stick to copper particles. Copper floats to the surface in foam. Waste rock settles to the bottom. The process runs through 10 stages. Each stage increases copper concentration. At the input, 0.5%. At the output, 25%. That's concentrate. From 100 tons of ore, you get 2 tons of concentrate. The remaining 98 tons? Waste that gets stored in tailings ponds the size of a lake. The concentrate heads to a copper smelter. Here it's turned into pure metal. First stage, roasting. The concentrate is heated to 1300 degrees Fahrenheit in the presence of oxygen. Sulfur burns off as sulfur dioxide gas. What's left is sinter, a mix of copper and iron oxides. The sinter gets loaded into a reverberatory furnace. Temperature, 2200 degrees. Silica flux is added. Iron bonds with the silica and floats up as slag. Copper settles at the bottom as matte, an alloy that's 50% copper. The matte is poured into a converter. Pure oxygen is blasted in under pressure. Remaining iron and sulfur burn away. Temperature climbs to 2370 from the exothermic reaction. After 6 hours of blowing, what's left in the converter is blister copper, 98% pure. But that's not enough for wires, you need electrolysis. Blister copper is cast into anodes 2 inches thick. They're submerged in tanks filled with copper sulfate solution. A current of 2 volts runs through. Copper dissolves off the anodes and deposits onto cathodes. After 3 weeks, the cathodes are coated with a layer of pure copper 4 inches thick. Purity, 99.99%. This is market-grade copper, ready to become wire. And just like that, after a journey from an explosion in a half-mile deep quarry through crushing, flotation, smelting at temperatures above 1800 degrees Fahrenheit, and electrolysis, gray rock transforms into red metal that carries electricity to every home on the planet. Without copper, there'd be no light in cities. No internet. Every data center runs on copper bus bars. No electric cars. A single Tesla contains 175 pounds of copper. No renewable energy. Solar and wind farms need 3 times more copper than coal plants. Every year, humanity lays down 6 million miles of copper wire. That's the distance from Earth to the Sun and back 7 times. 25 million tons of metal connecting continents into a single electrical grid. Copper is civilization's nervous system. Electrical impulses race through copper veins like thoughts through neurons. Factories operate, hospitals save lives, homes glow in the night. All thanks to metal that was once just green rock in the ground. Every time you flip a light switch, remember, between your finger and that bulb, miles of copper wire born from an explosion in a desert quarry on the other side of the world. It's the magic of turning stone into energy. And this magic won't stop as long as cities shine. You believe that in the United States alone, the electrical wire industry pulls in tens of billions of dollars in revenue every single year? These seemingly small spools of wire carry the entire flow of energy that keeps modern civilization running. Behind every foot of wire lies rigorous engineering. Copper is drawn through a series of steel dies to hit precise dimensions, then coated with layers of insulation designed to withstand heat and resist moisture. A deviation of just a few thousandths of an inch can lead to overheating, short circuits, and serious safety hazards. In this documentary, we're going inside the manufacturing process of electrical wire, the invisible foundation of modern life. From a thin strand of metal that seems almost fragile, electrical wire becomes the silent foundation of modern life. At a diameter of just about 0.08 inches, a single copper conductor can carry enough current to light up an entire house. Inside its thin insulation layer flows a constant stream of energy, transforming invisible motion into light, heat, and the continuous operation of the world around us. And when its mission is complete, electrical wire doesn't reach the end of its life. Copper can be reborn almost infinitely. The plastic insulation is stripped away, the metal is cleaned, melted down, and drawn again into new wire. Each recycling cycle consumes far less energy than mining and refining new ore, reducing waste and preserving natural resources. It's a closed loop, where technology and sustainability coexist in something as small and unassuming as a single wire. The journey of an electrical wire begins deep underground, in massive copper mines, where the red metal is extracted from ancient layers of rock. Copper ore doesn't exist in pure form. It's locked tight inside stone, soil, and mineral compounds. To reach it, people must drill, blast, and remove layer after layer of geology, hauling thousands of tons of rock to the surface every single day to recover just a tiny amount of copper. On average, producing a single pound of refined copper requires processing anywhere from 200 to 1,000 pounds of raw ore, depending on the metal content in each deposit. This shows that copper's value comes not from abundance, but from the precision required to extract it from an enormous mass of material. Most modern copper mines are giant, open-pit operations, hundreds of feet deep and miles wide. Seen from above, they look like colossal funnels carved into the Earth's surface. Every day, hundreds of ultra-heavy dump trucks, each hauling over 300 tons of rock, move continuously between the pit and the processing facilities. Once ore leaves the mine, it's still nothing more than solid rock with metal locked inside. To reach the copper, the first critical step is primary crushing, breaking down the rock's structure and freeing up the mineral particles. At the crushing plant, ore gets reduced through multiple stages, from large rocks to gravel and finally into a fine powder. The finer it becomes, the more efficiently copper-bearing minerals separate from the surrounding waste rock, preparing the material for the next stage of separation and concentration. Then the powdered ore goes into the flotation process. Water, air, and very small amounts of chemicals combine to create countless microscopic bubbles. Copper-bearing mineral particles attach to these bubbles and rise to the surface, while the heavier, worthless rock sinks to the bottom. This is the first true separation step, where the metal begins to be recognized and isolated from the rest of nature. The result is copper concentrate, containing 25 to 35% copper, a dramatic increase from the initial 1 to 5% found in raw ore. Though this isn't pure copper yet, this concentration stage is crucial. It transforms mountains of seemingly worthless rock into a metal resource with real industrial value. After crushing and flotation, the concentrate still isn't metal. At this stage, copper remains locked inside mineral compounds and requires one decisive step to be fully liberated: smelting. The concentrate is fed into furnaces operating at extremely high temperatures, often exceeding 2,300 degrees Fahrenheit. Under this intense heat, sulfur compounds and impurities begin to break down. They burn off, vaporize, or separate into slag, while the heavier metal settles at the bottom. This is the moment when mineral ore truly transforms into metal. After smelting, the resulting copper is known as blister copper, with a purity of 98 to 99%. Its surface shows a characteristic dark red color. The metal is dense, heavy, and conducts electricity far better than any mineral form before it. From rock and powdered ore, copper emerges for the first time as an industrial metal. Once copper is in its molten metallic state, it must be shaped into a form that can be transported and further processed. Here begins the casting stage. A stream of liquid copper, glowing red like lava, is drawn from the furnace and poured into heat-resistant steel molds where the metal's shape is first controlled with precision. Within minutes, the temperature drops and the copper solidifies into dense metal blocks known as billets or ingots. After casting into rough copper plates, the metal is still not pure enough to serve as an electrical conductor. Tiny impurities remain inside, small enough to escape the eye but significant enough to reduce transmission efficiency. To meet electrical industry standards, copper must go through an almost absolute purification step: electrolytic refining. Rough copper plates are suspended in large tanks filled with electrolytic solution. When electrical current flows, the metal surface slowly dissolves. Each copper atom separates from the rough plate and moves through the solution. On the opposite side, these atoms settle on cathode plates, forming a new layer of copper that is brighter, purer, and more uniform in structure. The result is copper sheets with purity up to 99.9%, the level required for electrical power systems. After refining, high-purity copper is remelted and cast into large round rods called wire rod. These rods are about half an inch in diameter and serve as the starting point for all subsequent wire drawing processes. Wire drawing is the process of gradually pulling metal through a series of progressively narrower steel dies, each one slightly smaller than the last. When the copper rod is pulled through the first die, its diameter decreases slightly while its length increases. The process repeats through the second, third, and each subsequent die until the wire reaches the required thickness. Throughout this process, the wire is coated with a special lubricating solution to reduce friction, limit heat buildup, and protect the metal surface. Wire drawing doesn't happen in one step. It's a sequence of gradual reductions. A single wire typically passes through 10 to 30 different dies before reaching its final size. For example, from an initial diameter of about half an inch, the wire can be drawn down to around 0.08 inches, and even much smaller for electronic wires. As the copper is continuously stretched, its internal crystalline structure becomes harder and loses its natural ductility. For this reason, after a certain number of drawing passes, the wire must be lightly annealed at temperatures from 600 to 800 degrees Fahrenheit to soften the metal again. After the wire is drawn to the right size, the individual copper strands are still too thin and too stiff to be used on their own. To become the flexible, durable conducting core in real-world applications, they have to go through a twisting process. Copper strands are fed into a twisting machine, where dozens of spinning spools work simultaneously, twisting each strand around a central axis at a precisely calculated angle. This twist angle directly determines the flexibility and bend strength of the wire. A tighter twist creates a stronger, more compact core. A looser twist makes the wire more flexible. That's why every type of electrical cable, from household wiring to industrial power lines, has its own specific twist structure. A single conductor can be made from 7, 19, 37 strands, or even more. These numbers aren't chosen randomly. They follow geometric patterns that allow the small wires to fit tightly together, forming a round, uniform core with minimal empty space and even distribution of electrical current across the entire cross-section. Thanks to the twisted structure, mechanical stress is distributed among many small wires, significantly reducing the risk of cracking or metal fatigue. At the same time, microscopic gaps between the strands help dissipate heat more efficiently as electrical current passes through the conductor. Once the copper core has been fully twisted, it still can't be used safely. Bare metal conducts electricity too powerfully. Even the slightest point of contact can cause short circuits or pose serious danger to people. That's why the conductor must move to the insulation stage. The twisted core runs continuously through an extrusion system, where insulating materials like PVC, PE, or cross-linked polyethylene are melted and pressed tightly around the entire metal surface. The molten plastic flows evenly in tubular form, wrapping tightly around the copper core and forming a completely sealed layer. This becomes the protective sheath that prevents electricity from leaking and isolates the conductor from the environment. The thickness of this insulation layer is controlled with extreme precision. If it's too thin, safety is compromised. If it's too thick, the cable becomes stiff, difficult to install, and wasteful of material. For this reason, diameter sensors work continuously during extrusion, ensuring the plastic coating remains uniform along the entire length of the wire. Immediately after coating, the cable passes through a cooling system using water or air, allowing the plastic to harden quickly and hold its precise shape. Once the insulation layer has completely cooled and stabilized, the wire feeds directly into the winding machine. Before reaching the spool, it passes through a tension control system that keeps the cable in a perfectly balanced state. It can't be too loose, which could cause tangling, and it can't be too tight, which could stretch the copper core or deform the plastic insulation. The spool rotates smoothly while a lateral guide mechanism moves back and forth, laying the wire in parallel, tightly aligned loops. Each turn is placed neatly beside the previous one, building layer by layer into a uniform, perfectly formed coil. Throughout the winding process, wire length is continuously measured by sensors. When the preset number of feet is reached, the system automatically stops, cuts the wire, and secures the end of the spool. After winding, the wire moves to the packaging area for protection against dust, moisture, and physical damage. Each spool is wrapped in plastic film or shrink wrap, and larger spools are additionally secured with plastic straps or steel bands to maintain their shape. Next, technical information such as wire type, cross-section, length, voltage rating, and production date is clearly marked on the packaging. From deep copper mines beneath the Earth's surface, the red metal embarks on a long journey through science and industry to become electrical wire. Every single stage, from refining and forming to drawing, twisting, insulating, spooling, and packaging, demands extraordinarily high technical precision. What appears to be a simple product is actually the result of ancient geology, modern engineering, and a massive manufacturing system operating without pause. If you're fascinated by the hidden stories behind everyday objects, where industry and science unite to shape the world we live in, subscribe to the channel. Every video is a journey into how humanity transforms raw resources into the foundations of modern civilization.
On a shipyard floor that stretches farther than the eye can follow, a machine nearly a third of a mile long takes shape. Tall as a skyscraper, built to carry an entire small city sealed inside metal boxes. The modern container ship is one of the most complex and staggering objects heavy industry has ever produced. It does not merely move cargo between continents, it carries the weight of global trade itself. Electronics, clothing, spare parts, appliances, the machinery of everyday life, all of it can at some point cross the deck of a giant like this. Yet the most extraordinary part of the story begins long before the hull ever touches water. Building a container ship is not simply the welding of steel. It is a project measured in years, where shipbuilding, heavy metallurgy, digital modeling, immense logistics, power plants of colossal output, and a precision without which no floating city of thousands of separate parts could ever be assembled, all converge into a single effort. What follows is how these giants are built, why their assembly ranks among the hardest industrial tasks on Earth, and how flat sheets of steel are transformed into a true ocean titan. It all begins long before the first piece of steel is ever cut. The creation of a container ship starts with design, and it is here that the fate of the future vessel is sealed. Engineers and naval architects calculate cargo capacity, stability, speed, fuel consumption, the behavior of the hull in a heavy sea, the arrangement of the containers, the operation of the engine, the trade routes, and compliance with international rules of safety. A modern container ship is not simply a large vessel. It is a balanced system in which a single change ripples through dozens of other parameters. Even at the stage of digital design, the loads on the hull are modeled, along with the methods of lifting the blocks, the order of assembly, the distortions that welding will introduce, and the way the ship will one day operate at sea. This work can stretch across many months. In a very real sense, the ship is first built in its entirety inside a computer, and only then begun in steel. The approach reduces the risk of errors that, on a real shipyard, would cost millions of dollars. That is why modern shipbuilding begins not at the dock, but inside engineering software, where the future giant is assembled before it is ever physically born. After the design comes what can only be called the birth of the ship out of metal. Enormous sheets of shipbuilding steel arrive at the cutting bay, where automatic plasma and gas cutting systems turn them into the future elements of the hull, the decks, the bulkheads, and the structural members that bind it all together. A single sheet can run longer than a city bus, and any error in its geometry will echo through the entire project that follows. But the modern shipyard abandoned hull-by-hull construction long ago. Today, the giants are built on the block principle. From the cut pieces, workers first assemble panels, then sections, and finally large blocks that already represent substantial fragments of the future ship. Such blocks can weigh tens of tons, and at times, a great deal more. At this stage, much of the piping, the cabling, the internal passageways, and the equipment is often installed in advance. This is known as pre-outfitting, and it saves enormous time, because fitting out a single block on the ground is far simpler than carrying out the same work later, deep inside an already assembled hull. It was block assembly that made it possible to build today's ocean giants within any reasonable span of time. Rather than raising a ship piece by piece directly in the dock, the yard builds it like a colossal industrial construction set. Individual blocks are joined into even larger mega sections, which are then moved to the place of final assembly. But the larger the block, the harder the task of lifting and setting it in place. Here, the heavy infrastructure of the shipyard comes into play, the colossal cranes, among them the famous Goliaths, capable of raising hundreds of tons in a single lift. With their help, mega sections the size of an apartment building are moved with a precision that seems almost impossible to believe. The slightest tilt, an error in the points of grip, or a single distortion can turn an expensive operation into catastrophe. For that reason, long before the lift, engineers calculate how the structure will behave while in motion, and the assembly itself proceeds in a strictly defined sequence. Here the ship at last begins to take on its true scale, as separate parts gradually become a hull that surpasses in size most of the objects a person ever encounters on land. When the megasections arrive in the dry dock, the moment begins that can rightly be called the true birth of the container ship. It is here that the blocks are welded into a single monolithic hull. A dry dock is an immense protected basin that can be flooded and drained, allowing these giants to be built almost as though on solid ground. Inside the dock, the keel line is laid, the supports are set in place, and then, step by step, the hull takes form. The vast sections are fitted to one another, aligned, locked, and welded. At this stage, precision and the control of distortion become critical, because welding on such a scale always drives stress into the metal. In parallel, the ship continues to fill with its systems, as additional mains, engineering runs, the structures of the superstructure, and the internal compartments are installed. The container ship is, in effect, assembled like a steel organism, where every section has its appointed place and every error accumulates along the entire length of the hull. That is precisely why assembly in the dock is among the most demanding phases of all, for here the project, drawn from a digital model, is finally transformed into a real and living vessel. But the hull is only the shell. The true heart of a container ship is its power plant and its engineering systems. These giants are driven by enormous marine diesels that are, in their own right, marvels of heavy machinery. Yet the engine alone is not what matters most. It must be correctly tied to the propeller, the cooling system, the air intake, the exhaust, the fuel system, and the entire operating logic of the vessel. Engineers have long understood that a great many failures arise not from the engine itself, but from the poor integration of its supporting systems. A marine engine is, in essence, a giant air pump, one that demands a colossal volume of air and conditions tuned to perfection. If the ventilation of the engine room is poorly calculated, if the load of the propeller does not match the characteristics of the engine, if the logic of the cooling is broken, the entire system begins to wear itself down. The installation of the engine is therefore not the mere mounting of a heavy unit. It is the delicate engineering union of the ship's entire power network, and on it depends the vessel's survival in the open ocean. When the hull is at last watertight and able to float, one of the most spectacular moments of the whole construction arrives: the launch. For giants of this size, the dry dock method is most often used. The dock is simply allowed to fill with water, and a hull weighing many thousands of tons gradually lifts from its supports and begins to float. From the outside, it appears almost serene, but behind that apparent simplicity lies an enormous body of calculation. There must be precise understanding of how the distribution of loads will change, how the hull will behave at the instant it passes from resting on its blocks to being held by water, how the tugs will work, and how swiftly the vessel will reach a position of safety. After the launch, the container ship is still not ready for service. It is moved to the fitting out quay, where the work continues on the cable runs, the pipelines, the navigation equipment, the radars, the communication systems, the internal compartments, the insulation, the automation, and everything else that turns an empty steel shell into a real and working ship. It is at this stage that the future giant receives its brain. The final stage is the sea trials. This is the moment when the container ship first goes out to sea, not as an unfinished hull, but as a complete vessel, one that must prove that all its systems work together as a single whole. Tested are the maneuverability, the operation of the engine, the stability, the vibrations, the safety, the electronics, the navigation complexes, the communications, the power supply, the emergency modes, and a great many other parameters besides. Only after this can the ship be formally handed over to the customer. And it is here that one sees most clearly why the building of a container ship is reckoned among the most difficult assemblies in the world. This is no mere large ship. It is a floating industrial system, where thousands of tons of steel, miles of pipe and cable, an immense power plant, digital control systems, demands of safety, economy, endurance, and the capacity to withstand ocean storms for decades, all must be brought together as one. A container ship must be more than gigantic. It must be reliable, because all its power is worth nothing without absolute soundness in the open sea. Seen whole, the birth of a container ship makes one thing clear. Here stands one of the summits of modern heavy industry. First, the vessel exists as a digital design. Then sheets of steel become panels. Panels become blocks. Blocks become megasections. And the megasections become a colossal hull that receives its engine, its systems, its electronics, and at last goes out to sea. All of it demands years, thousands of specialists, immense cranes, dry docks, and shipyards the size of separate industrial cities, together with an engineering precision without which such an object simply could not be built. And in this lies the true magic of shipbuilding. The container ship appears to be nothing more than a carrier of boxes. Yet in truth, it is one of the most complex machines ever made by human hands. It is born of metal, of calculation, and of discipline, only to become a part of the global economy. And every time one of these giants leaves port, behind it stand not only the ocean and the trade it serves, but the colossal industrial machine that proved capable of creating it.
Every year, over 27 billion square feet of drywall are produced in the United States. That's enough to build a road from the Earth to the Moon and almost halfway back, or to cover the entire state of Delaware twice. But how does an ordinary stone, formed millions of years ago at the bottom of ancient seas, turn into the smooth sheets that become the walls of our homes today? In this video, we'll take a look behind the factory doors, where tons of stone pass through furnaces, mills, and conveyors to become the symbol of modern American construction. Watch until the end, and you'll see secrets that are rarely shown publicly.
The numbers behind drywall production in the United States are not just big, they are astronomical. And they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the US produced approximately 27 billion square feet of gypsum board panels. This number is so colossal that it's hard to comprehend. Try to imagine, if you were to lay out all this amount of drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or, with this number of sheets, you could completely cover the entire state of Delaware twice and still have some left over. This endless stream of building material is not only a physical product, but also a powerful economic indicator.
The market for these panels in the US is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and in construction. It all begins not in the workshop, but much earlier, in a quarry where gypsum is mined. This is a natural mineral, a stone that was formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of the primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, the size of a fist. This is just the beginning. Then, this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, rotating at an insane speed, break these pieces into even smaller fractions, turning them into something resembling coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine, powder-like dust. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be revealed. The next step is one of the most important and interesting. It's a process called calcination, and essentially, it's the controlled drying of gypsum. The fact is that in the crystal structure of natural gypsum, water molecules are locked in.
For drywall to harden, this water must be temporarily driven out. To do this, the white powder is fed into a huge, slowly rotating kiln. It looks like a giant drum tilted at a slight angle. Inside this kiln, a very precise temperature of about 300 degrees Fahrenheit is maintained. The gypsum powder, slowly tumbling inside the drum, heats up and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but to put it simply, it becomes thirsty. Now this powder, which is already called building plaster or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a hard gypsum stone. It is this property that is the basis of the entire production. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line.
And now the most spectacular part begins, the creation of the sheet itself. In the workshop is a huge conveyor, hundreds of feet long. At its beginning stand two giant rolls of special dense paper, or paperboard. One roll for the face side, it's perfectly smooth white. The other for the back side. It can be a bit darker, grayish. The ribbon from the bottom roll, the face side, is unwound and lays on the conveyor, forming an endless track. In parallel with this, in a giant mixer, resembling an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it. Each additive plays its role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid, so it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to stick better to the paper liner, and fiberglass adds strength. This mixture, called slurry, resembles a thick gray porridge. It is poured in a continuous stream directly onto the paper ribbon moving on the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded up, forming the sides of the future sheet. And at this moment, the second ribbon of paper, from the back roll, is laid on top like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between two rollers or under a forming plate, which compress it to a precisely specified thickness, for example, 1/2 inch. The newly formed, still soft and damp sheet of drywall continues its journey on a very long conveyor called the setting line. Its length can reach several hundred feet.
While the sheet slowly moves, a real miracle is happening inside it. The gypsum powder reacts with water, the same rehydration reaction occurs. The gypsum turns back into a hard stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife.
This is a huge blade that moves in sync with the belt, and at the right moment makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor doesn't stop for a second. The cut sheets are now hard, but still very damp. They contain excess water that did not participate in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most massive structure in the factory, a multi-deck drying kiln. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, traveling a path of several hundred feet inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is very carefully controlled. Only the free water needs to be removed without damaging the crystal structure of the gypsum itself. This process can take about an hour. At the exit of the dryer appears a product we are familiar with, a perfectly dry, light, and strong sheet of drywall. But this is not the end. The final stage is finishing. 2 finished sheets are stacked face to face, their edges are perfectly trimmed to be straight and clean. A paper tape with information about the manufacturer and product type is glued to the end. After this, robotic manipulators with superhuman precision and grace lift the finished sheets and stack them in perfectly even stacks on pallets. Each stack is wrapped in protective film, labeled, and sent to the warehouse. From there, it will go to construction sites to become part of someone's home, transforming from a simple gray stone mined from the earth into a smooth and cozy wall. Drywall production is like a barometer of the construction industry's health. When the economy is booming, people actively build new houses and renovate old ones, and the demand for drywall soars. The factories that produce this product operate at full capacity, and the stream of trucks delivering the finished sheets across the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall factories are located throughout the country to be closer to large construction markets, the extraction of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa.
But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydroturbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydroturbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining, but the foundation of its strength, that's laid right there on the press. $80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys: titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons. A huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees.
The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then the upper plate of the press begins its descent, slowly, almost ceremonially. But behind that calm lies 80,000 tons of force.
Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans. Excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure.
Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing.
China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it. the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
What if I told you there's a metal that flows like water at room temperature, killed thousands of workers during the colonial era, and without which gold mining would be impossible? A metal that vaporizes at 1100 degrees Fahrenheit and condenses back into liquid silver? Every year, the world produces around 1,300 tons of mercury, but that's nothing compared to historical scales. Over the last 500 years, humanity has extracted about 1 million tons of mercury from the Earth's depths. Half of that million was used before 1925. Mercury is obtained from red ore, cinnabar, by heating it to 900 to 1100 degrees Fahrenheit. During this process, mercury sulfide breaks down, releasing mercury vapors and sulfur dioxide gas. China dominates production, 95% of the world's mercury. In 2022, China produced 2,000 tons of mercury. A standard flask holds 76 pounds of mercury. These were the exact flasks used to ship it to gold mines during the gold rush. Stick around till the end. You'll discover a secret that even those who work with this metal won't talk about. Picture an underground mine somewhere in China, Kyrgyzstan, or Mexico, the world's biggest mercury producers. Deep beneath the surface, in the dim glow of miners' lamps, red streaks appear in the rock. This is cinnabar, mercury sulfide, a bright red mineral that humanity has known for thousands of years. The ancient Romans mined it both as a pigment and for mercury. The ancient Egyptians were using mercury as far back as 1500 BC. Greek philosopher Aristotle in 350 BC described how cinnabar was heated to extract mercury for religious ceremonies. Cinnabar forms in veins associated with volcanic activity and hot springs. About 90% of deposits require underground mining with tunnels. The remaining 10% can be extracted through open-pit methods. Cinnabar is separated from the surrounding rock through drilling and blasting or using powerful machinery. The ore is hauled out of the mine on conveyor belts or in trucks. Because cinnabar is a relatively concentrated ore, it can be processed directly without intermediate steps to remove waste rock. The ore is first crushed in one or more cone crushers. A cone crusher consists of an inner cone rotating on an eccentric vertical axis inside a stationary outer cone. When ore is fed into the top of the crusher, it gets squeezed between the two cones and breaks into smaller pieces. For concentrating low-grade cinnabar with a specific gravity of 8 to 8.2, gravity and flotation methods are used. Grinding to -48 mesh is the economically viable liberation point for the mineral. Some operations use mineral jigs to recover coarse heavy mineral and any metallic mercury that might be present in the ore. Flotation with one or more cleaning stages is used to produce a high-grade concentrate. It's not uncommon to obtain concentrates containing 40 to 50% mercury from ores containing 5 to 15 pounds of metal per ton. The concentration ratio is therefore high. The dewatered concentrate from flotation is combined and stored for roasting and recovery of metallic mercury. Now comes the most critical and dangerous stage, roasting. Cinnabar concentrate gets loaded into specialized furnaces. These can be multi-hearth furnaces, where ore mechanically moves down through a vertical shaft from one level to another via slowly rotating rakes, or rotary kilns, where ore tumbles along the length of a long rotating cylinder, tilted a few degrees from horizontal. Either way, heat comes from burning natural gas or other fuel at the bottom of the furnace. Heated cinnabar reacts with oxygen in the air at temperatures ranging from 930 to 1110 degrees Fahrenheit. A chemical reaction occurs. Mercury sulfide breaks down into sulfur dioxide gas and mercury vapor. Mercury rises as vapor. This is called roasting. Mercury vapors rise upward and exit the furnace along with sulfur dioxide, water vapor, and other combustion products. Significant amounts of fine dust from the crushed ore also get carried away and must be separated and captured. Next comes condensation. Hot gases containing mercury vapor pass through a cooling system. A condensation column is used, a special device where the vapors cool down and mercury condenses back into liquid metal. Pure mercury separates from sulfur in this process and evaporates easily. The condensation column collects the liquid metal. Thanks to mercury's high specific gravity, impurities gather on the surface and can be easily removed. The liquid mercury gets poured into standard iron flasks. Each flask holds 76 pounds of mercury. That's the standard unit of sale. These exact flasks shipped mercury to gold mines during the gold rush in California and Nevada in the 18th and 19th centuries. The process is simple in essence, with one drawback: toxic fumes. If roasting is done incorrectly, mercury vapors, which are highly toxic, can get released into the atmosphere. This was catastrophic for workers in the colonial era. The history of mercury production is full of tragedies. In 1564, cinnabar mining began in Huancavelica, Peru. With a local source of mercury, the amalgamation process was adopted for refining silver in Potosí, Bolivia, in the early 1570s. As a result, massive quantities of mercury were released into the environment. Between 1564 and 1810, approximately 17,000 tons of mercury vapor were released into the atmosphere in Huancavelica and 39,000 tons in Potosí. In 1604, an advocate for indigenous people described how fumes, dust, and candle smoke in the mine caused coughing and Huancavelica disease, and argued that forcing people to work in mercury mines meant sending them to a slaughterhouse. In 1630, a contemporary described the mines as a living image of death and a dark shadow of hell. The Jesuit José de Acosta, around 1590, wrote about the roasting process. If the smoke or fumes reach the people opening the pots, they get mercury poisoning and die, or are left in very poor condition or lose their teeth. The largest mercury deposit in history? Almaden in Spain. It was worked from Roman times until 1989, the world's biggest producer. In 2000, Almaden yielded 236 tons of mercury. Other major deposits: Khyder in Kyrgyzstan, 550 tons, Algeria, 240 tons. During World War II, mercury production was critical. Mercury fulminate was essential for bullet primers, and the biggest producing region in Spain was under dictator Franco's control. The U.S. ramped up domestic production from 1941 to 1944. The price per flask during the war years averaged around $380 in 1960 prices. Today, global mercury production has plummeted. In 2016, they produced 4,500 tons, but in 2023, just 1,200 tons. China dominates with 95% of world production, 1,000 tons in 2023. Mercury has diverse applications, but its use is declining due to toxicity. Mercury easily forms amalgams with other metals, making it useful for extracting gold and silver. Much of the incentive to develop mercury deposits in the United States arose after the discovery of gold and silver in California and other western states in 1800. When mercury mixes with gold slurry, it triggers a reaction that separates gold from ore. This amalgam is then heated to vaporize the mercury and leave behind gold nuggets. Artisanal and small-scale gold mining is the largest source of anthropogenic mercury emissions, accounting for 38% of global releases. Other applications include chlorine and caustic soda production in mercury cell electrolysis plants. Until recently, this was a major consumer. In 2023, only one such facility was operating in the U.S. electrical devices, fluorescent and mercury vapor lamps, mercury batteries, switches, and relays. Measuring instruments, thermometers, barometers, pressure gauges. Dental amalgam, a mixture of mercury with silver and other metals for fillings. But because of its high toxicity, mercury use has dropped sharply over the last 20 years. Inhaling mercury vapor is especially dangerous for the kidneys, central nervous system, respiratory and cardiovascular systems. Inhaling mercury vapor also causes neurobehavioral disorders like hand tremors and mental impairment. Exposure to other forms of mercury, particularly methylmercury, which accumulates in fish, can also lead to kidney problems, lung issues, and central nervous system damage, as well as arthritis, reproductive problems, memory loss, psychosis, and in some cases, death. The United States banned the export of elemental mercury on January 1, 2013, under the Mercury Export Ban Act of 2008. Global mercury resources are estimated at around 600,000 tons, mostly in China, Kyrgyzstan, Mexico, Peru, Russia, Slovenia, Spain, and Ukraine. And so, having traveled from red cinnabar ore through roasting at 1100 degrees Fahrenheit, through evaporation and condensation, through the tragedies of thousands of workers in the colonial era, through the gold rush and world wars, emerges a liquid metal that flows at room temperature, without which gold mining would be impossible, but which has killed more people than any other metal in human history.
Every year, enough glass fiber rebar is produced worldwide to challenge the dominance of steel itself. This isn't science fiction, it's modern manufacturing. The world spends billions fighting rust, repairing bridges and car parks destroyed by corrosion. But there is a solution. A composite material that is twice as strong as steel, 4 times lighter, and simply does not know the meaning of the word rust. The market for this material is growing at 12% a year, and today you will see how hundreds of bobbins and a barrel of resin give birth to the building material of the future.
It all begins at one end of a vast workshop, in front of a structure that looks like a giant library for thread. It's called a creel. On a wall several meters high, hundreds, sometimes thousands of huge bobbins are mounted in neat rows. Wound onto each one is a fine glass thread, or roving. This isn't the glass from your windows. It's a special glass fiber produced by melting glass and drawing it through microscopic holes.
The result is a thread thinner than a human hair, but with incredible tensile strength. This will be the skeleton. From each of these hundreds of bobbins, a single separate thread is drawn, and they all converge into one thick, fluffy bundle. This